we now have a rock-solid Travis CI deployment process, or maybe pre-deployment, I guess would be the best way of saying it. It's our build pipeline of sorts. Anytime that we make a change to our GitHub repository, Travis is going to automatically pull down our repo and build out a new set of production images, and then push them off to Docker Hub. So now we need to start thinking about how we're going to use these images and actually deploy them in production. So for that, we're going to again be using Amazon Elastic Beanstalk. Now, as a quick reminder, back when we had a single Docker container in our last project, something was kind of going on automatically behind the scenes anytime that we pushed our code over to Elastic Beanstalk. You might have noticed that you and I did not have to set up any custom configuration or anything to tell Elastic Beanstalk that, hey, you need to take this Docker file and build it and run the image that comes out of that. That was an automated process. We didn't have to add any configuration. We essentially just took our project directory with the Docker file in the root directory, threw it over to Elastic Beanstalk, and Elastic Beanstalk said, well, you know what? They got a Docker file. I guess I might as well build it and try running the image that comes out of that. So now, this time around, we're in a very different situation. We don't have a single Docker file anymore. We have a couple of different folders, and each of them has a separate Docker file. And so if we just toss this entire project directory off to Elastic Beanstalk, it would probably say, hey, look, I know you got these Docker files. I don't know which one you want me to run. So anytime that we want to run multiple separate containers on Elastic Beanstalk at the same time, we have to go through an extra little step of configuration to tell Elastic Beanstalk exactly how to treat our project. So here's what we're going to do. Inside of our project directory, we're going to create a file with a very special name. This file is called dockerrun.aws.json. This is going to be a JSON file, so it's going to contain some JSON data that's going to tell Elastic Beanstalk exactly where to pull all of our images from, what resources to allocate to each one, how to set up some port mappings, and some associated information. In fact, when you think about the purpose of this Docker run AWS JSON file, it's going to very quickly remind you of exactly how our Docker compose.yaml file is set up. Remember, Docker Compose is primarily meant for use in development environments, and you can kind of think of it as a single file that encodes a lot of directions that would normally be passed directly to Docker run. Inside of our current Docker Compose file, we list out a bunch of different services. And then with each service, we tell Docker how to build the image, what ports to open, environment variables, and a bunch of stuff like that. So we're going to do a very similar thing with this Docker run AWS JSON file. The only difference is that rather than referring to these as services, like they're called over on Docker Compose, the Docker run file refers to them as container definitions. The biggest difference that you're going to see between these two files is that in the Docker Compose file, it's going to contain some information about how to build an image using a Docker file, right? That's what we were doing inside of Docker Compose. If you go open up the Docker Compose file right now, you'll see that in each service, we have the different build directions. But in the case of the AWS JSON file, we already have a set of images. So rather than saying, oh, here's how to build a client, or here's how to build Nginx, we're just going to say, go and pull the image from Docker Hub with the name of your Docker ID / multi-client. We just say, go pull this image. Elastic Beanstalk is going to and use it for each of these different container definitions that we're going to add. So again, I really want you to think of these two files as being rather similar. The Docker run file is really just customized to work directly with AWS. And the big difference between the two is that the Docker Compose file has directions on how to build an image. But with the Docker run file, we have already built the image, no build required. We're just going to specify the image to use. So let's take a quick pause right here. In the next section, we're going to start putting together our container definition file, the dockerrun.aws.json file. So I'll see you in just a minute. In the last section, we spoke about how we make a dockerrun.aws.json file to tell Elastic Beanstalk how to work with our multiple containers. Now, before we start working on this file, I want to show you a little piece of documentation that's going to be very valuable when you start making use of Elastic Beanstalk on your own projects. First, a little bit of behind-the-scenes action. So Elastic Beanstalk doesn't actually know how to work with containers, especially a multi-container environment. Behind the scenes, when you tell Elastic Beanstalk to host a set of containers, it's actually delegating that hosting off to another service that is provided in Amazon called the Elastic Container Service, which is abbreviated very frequently as ECS. You work with Amazon ECS by creating files that are called task definitions. And a task definition is essentially a file that tells ECS how to run one single container. Each of these task definition files are very similar, almost identical to the container definitions that you and I are going to write inside of our Docker run aws.json file. And so the piece of documentation that I want to show you is the documentation around these task definitions. Essentially, it's a really confusing thing to understand here, or to figure out, I should say. But if you look at the documentation for the Docker run file, it's not going to tell you a lot about the different options that you can pass to these container definitions, because it actually kind of wants you to go and look at the documentation for a task definition as defined by Amazon ECS. So that's why I'm showing this documentation, because it's not immediately clear when you start reading the stuff that you need to go and read about this completely different service that AWS is running if you want to figure out how to customize your Docker run file. So long story short, let's pop open a new tab. We're going to pull up the documentation for a task definition, which is essentially what you and I are writing inside of that Docker run file. So I'm going to do a search for Amazon ECS task definition. And then one of the first results you'll see here is at docs.aws.amazon.com. You're looking for Amazon ECS task definitions. So hopefully you'll see a page that looks something like this right here. If you scroll down just a little bit, you'll see a topic of task definition parameters. You'll come to this page, and then on the right-hand side, you're going to look for container definitions. And so what you and I are going to write inside of our docker run.aws.json file is essentially going to follow the format that you see right here. So this is the documentation that you can refer to if you want to get a better understanding of what we are writing inside that file. So we're going to add in properties like name, image, memory, all this other stuff to that file. Okay, so now that you know where to look if you want to get some documentation around this stuff, let's take a quick pause right here, and then we'll get started on that file in the next section. In the last section, we took a look at some of the documentation that is going to be used to write our docker run.aws.json file. So without further ado, let's get to it. I'm going to flip over to my code editor, and then inside of my root project directory, I'll make a new file called docker run.aws.json. Now I'm going to blow up the size of my editor here just so you can see the name very easily. Notice how it is the word Docker and then the word run. So there's two R's in there. Now the file type we're going to be working with here is a JSON file. So we have to enter JSON file throughout this entire thing. So to get started, we're going to put down one wrapping object with a set of curly braces like so. And then we're going to tell Elastic Beanstalk what syntax we are using inside this file. So we're going to place AWS EB Docker run version is 2. So as you might imagine, there was a version 1 of this file, or the syntax used within this file. We're using version 2, which is going to have this file be interpreted in a very specific way. We'll then put a comma on the very end, and then we'll start to list out all the different container definitions. Now, container definitions is very purposefully done as a plural. So definitions, we have many definitions. So we're going to put an array in here, and then we're going to list out a number of different container definitions. For every entry that you and I put into this array right here, we're going to have one distinctly separate container created inside of our application. So at the end of the day, you and I have 4 custom images that we want to be hosted by Elastic Beanstalk, so we're going to add 4 separate entries inside of this container definitions array. For the first one we put together, let's write out the configuration block for our client to get started. So I'm going to put a new object inside of here with a set of curly braces, and then I will provide a name for this container. The name does not have to be identical to the project name or the folder or anything like that. This is the name of your container that's going to eventually show up on a dashboard so that you can identify it. Now, just to stay consistent in all things, we are going to use the same name of our subproject. So we're going to give it a name of client. Next up, we're going to list out the image to use for this container. So again, remember every record inside of container definitions, so like this record right here, corresponds to an actual container that is going to be created along with our deployment. So right here, we're going to specify the exact image that will be used to represent this container. So the image we're going to use is going to be the multi-client image that we just pushed to Docker Hub. So multi-client, this one right here. Now to specify that image, this is what I was talking about nonstop in the last couple of sections when I was saying, oh yeah, Docker Hub is great because it's like the central repo for all these different deployment services. So in order to specify that image on Docker Hub, all you have to do is write out your Docker ID and then the name of that image. So for me, it's multi-client. Chances are that for you it's the same. So when AWS sees this string right here, it's going to say, oh, they must be talking about Docker Hub. And so they're going to go off to Docker Hub. They're going to look up your Docker ID and then see if you have a repo in there or an image with the name of multi-client. And if you do, it'll then pull down that image and use it as the basis for this container right here. So like I said, really easy to use Docker Hub with a lot of these different hosting services. Now the next thing we're going to do is set up a host name. Now the host name is a little bit more complicated. Let's fill out the entry here and I'll tell you a little bit more about what it's for. So we're going to say that it's going to be client. Okay, so quick reminder here. Remember that back inside of our Docker Compose file, I'm going to open it up here really quickly. Inside this file, we had the list of services, and every service had a different name. So for example, our client was called client. By setting up this name right here, it essentially created a new host name that could be accessed by any other container that was created by Docker Compose. And so the end result of that was, for example, inside of our nginx folder, if you look at that default.conf file, remember that inside of here, we were able to reference another container simply by writing out like, oh yeah, HTTP client. So client right here, you would normally write something like google.com, but we were able to just write out client, and that was resolved as that other container inside of our grouping of containers. And so with the Docker Compose file, we kind of set up that host name by just defining the name of the service right here. But in the world of the Docker run aws.json file, we have to specify a very distinct host name. And so when we say host name right here, we're essentially giving every other container in this group of containers the ability to access this container right here by trying to make a request with a host name of client. So if you really wanted to mess things up, you could do something like google.com. And then if you ever tried to make a request to google.com from one of your containers, rather than going to the real google.com, it would go to this container right here. And obviously that's not what we want. So we're going to give it a host name of client instead. Okay, let's take a quick pause right here, and we'll continue working on the Docker run file in just a moment. In the last section, we started putting together our container definitions inside of the docker run.aws.json file. We're now going to continue with two other important parameters that are going to be added to our client container right here. So the next one that we're going to put on is a flag called essential, and we're going to set it to false by default. The essential flag is something that we've not seen before in any other Docker concept. The essential flag essentially means that this container right here is not considered to be, as you might guess, essential. So what would it mean if we marked this thing as essential true? If we marked a container as essential true, and this container ever crashes for any reason whatsoever, then all the other containers in this group of containers will be closed down at the same time. So in other words, if we end up with some other containers inside of here, like let's say container 1, and notice this is not valid syntax. I just mean to say that there are some other containers in here. Now, if client was marked as essential and this thing crashed for any reason, container 1 and container 2 would be automatically shut down as well, even if they are still running A-OK. Now, in the case of our client, if this thing crashes for any reason, that's kind of okay, and I would still want all the other containers or the other services in my group of containers to continue running. The only service that I have, or we have inside this list of container definitions that you and I really care about is the nginx routing server. Remember, that's the server that routes to either the client or the API, the Express API that we have. So if that thing goes down, it means that no one can access any of the different services in our group of containers. And so we're probably going to want to mark that one as our essential container to say, hey, if the Nginx server crashes, well, we can't reach any of the other services in our grouping of containers, so we better just shut everything down. Now, the one little bit of trivia that I want to share with you about essential right here is that at least one service in your listing of container definitions must be marked as essential. So at least one thing inside of here has to be essential. And like I just said, we're going to treat the Nginx container as our essential service. So I'm going to flip the client back over to false to say that, hey, if this thing crashes, that's kind of okay. We don't really care. Now, the last property that we're going to add on here, oh, actually, you know what? Excuse me, that was the last one. Okay, so that's it for our client definition. We're now going to skip over Nginx and take care of the server and the worker container definitions as well. Those are both going to end up being very similar to the client definition that we just put together. The Nginx one is going to be a little bit different. That's why we're going to save it for last. So after the client definition, I'll put in a comma and then open up another record. Remember, every one of these objects right here represents a different container that we want to create. So the next one is going to have a name, and we'll do the server. So I'll call this server. The image that we're going to use is multi-server. So we'll say your Docker ID / multi-server. And then the host name this time around, remember that when we put together our host name inside of the nginx default.conf file right here, if you open that file up, you'll recall that we actually renamed that endpoint or that host name to be API, because we have been calling that Express project server, but we very quickly realized that, if we called everything server, stuff was going to get really confusing really quickly, and it just didn't make a lot of sense. And so we ended up renaming this host as API instead. So for the host name over here, rather than making use of server, we're going to use API because that is what the Nginx server is going to look for when it tries to redirect traffic upstream. And then finally, we'll add on an essential to this one, and this will also be false because, yeah, it's not the best thing if our server crashes for any given reason, but if it does crash, well, there's not a good reason to shut down everything else as well. Okay. So now on to the next one. We'll move on to our worker container. So I'll do a name of worker. We'll do an image of your Docker ID / multi-worker. Our host name is going to be worker. And essential, as you might guess, yep, this one's also false. So out of all the services that we have, without a doubt, the worker crashing is the least of our concerns. If the worker crashes, our application can still be visited by users. Users can still enter in indices to be calculated, and they can still see values that have already been calculated by the worker in the past. So if the worker crashes, that just means that we're not going to calculate any values in the future. And I'm totally okay with that. If that happens, no big deal. We could definitely do a little bit of debugging, figure out why the worker crashed, and then figure out some way to start it back up in the future. Okay, so that's it for container definitions for the client, server, and worker. Now, we have to do the Nginx one last here, so let's take another quick pause. We'll come back in the next section, and we'll take care of that container definition. So I'll see you in just a minute. In this section, we're going to take care of our very last container definition, the definition for our Nginx container. And remember, this is the container that's going to do some routing of incoming requests to either the client or the backend API server. So inside my Docker run aws.json file, I'll add a comma, we'll put in our last configuration object. So we're going to give this a name of Nginx. For our image, we'll make use of your Docker ID / multi-nginx like so. Now this time around, we're not going to add in a host name because no other service in everything that we have here needs to directly access Nginx. The host name is actually an optional field, and because nothing needs to kind of reach out to Nginx and get a handle on it, we are not required to add in a host name. Now you definitely can if you want to, so if you want to be 100% complete, we could add in a host name of Nginx or whatever you might want to do. But it's not strictly required in this case. Now that I think about it, the worker hostname here is actually not required as well because nothing is actually reaching out to the worker as well. So you could probably get away with deleting that if you want to be a little bit adventurous, but I'm going to leave it in. Okay, so now we're going to add in our essential flag to the Nginx definition, and we're going to add in 2 additional flags on top of that as well. So we'll say essential is true. So like I said previously, at least one container must be marked as essential. If this container crashes for any reason, everything else, all these other containers, will be automatically shut down at the same time. And that definitely makes a lot of sense with our current architecture, because like we said just a moment ago, if the Nginx server crashes, well, that's pretty much it. Users cannot access the API, they can't access the client, and the worker can technically still run, but essentially this group of containers is now kind of dead, and we should shut everything down and try to fix it up at some point in the future. So that's why we are going to mark Nginx as essential true. Okay, now we're going to put in 2 other flags, so we did not add into any of the previous ones. Very quickly, I want to open up the docker compose.yaml file. You'll recall that to expose traffic to our group of containers, we had opened up a port for the Nginx service right here. And so we had said that if you ever try to visit our group of containers at localhost 3050, that would map up to port 80 inside the container, because Nginx by default is going to listen on port 80. And so we need to do that exact same port mapping process inside of our Nginx server configuration right here as well. So we're going to do a port mapping by saying port mappings. This is going to be an array because we could technically have several different port mappings. I'm going to put in a single record inside of here that will have a host port of 80 and a container port of 80 as well. So this means open up a port on the host or on the machine that is hosting all of our containers and map that to port 80 inside of the container, which again is the default port that Nginx listens to inside the container. So as you can see, setting up a port mapping is a little bit more typing than it was back inside of the Docker Compose file. Back inside of Docker Compose, we got away with just saying ports is, 3050:80. In the Docker run file, a lot more syntax goes into it, but at the end of the day, it does the exact same thing. It maps a port inside the container to a port on the host, or the machine that is running all these containers. Now, one last flag that we're going to add on to the Nginx configuration. So after the closing square bracket for the port mappings, I'll make sure I get a comma in there, and then I'm going to add on links. We'll talk about what links is in just a second, but first, let's fill out the definition for it. This is going to be an array, and it's going to have a string that refers to our server and our client. So here's the links array. We'll say client and server like so, in 2 separate strings separated by a comma. So let's talk about what this is doing. As a quick reminder, back inside of our Docker Compose file, we were very easily able to kind of communicate between different containers by making use of the different host names. So for example, when the API had to connect to Redis, we simply said, oh yeah, connect to the host name of simply Redis. Anytime that the API made a request out to a host name of Redis, it automatically got routed over to this other running service or this other running container. When you start deploying containers over to Amazon Elastic Beanstalk, however, or as we've said behind the scenes, technically ECS, we have to do a little bit more explicit mapping or kind of more explicitly form up links or connections between these different containers. So in the world of Docker Compose, everything was easy as pie. We just said, oh yeah, try to access this other running service over here, or try to access this other running service over here. And Docker Compose kind of took care of everything for us, or all that networking for us. So in the world of ECS, you and I have to form a little bit more distinct links between each of these running containers. So in our case, we know that Nginx needs to eventually send some traffic or redirect a request from the Nginx server to either the client or the API. So in our case, we want to make sure that Nginx knows that these other 2 containers exist, and we're going to do so by forming up a link between them. Now notice that links are kind of unidirectional. In other words, Nginx right here only has to kind of point over to client, but we don't have to form a opposite direction connection like so. It's just unidirectional. We just say, oh yeah, form a connection from Nginx over to the client. And so in our case right here, we're saying, yep, form a link from Nginx over to the client container and the server container. And one thing I want to mention here is that the name to links that we're providing maps up to the name property of the other container definition. So for example, this gets really important with the server definition right here because we used a name of server, but we used a host name of API. So for hostname, we did not, or excuse me, for the link definition, we did not say API right here. Instead, we just provided the name to that other container. That's how we form out the link. All right, so that's pretty much it for our container definition file. Now, the last thing that I kind of recommend you do, just because this is a JSON file and it's really easy to make typos in here without realizing it, one thing that you might do is open up a new tab and do a search for like JSON validator or something like that, and then find any random service in here, and then take all the JSON that we just put together, copy it, and throw it into the validator. And then somewhere on here, oh, there we go, validate JSON. And that's going to say, okay, you have valid JSON. So if you made any typo, this will very quickly tell you and give you a little bit of feedback before you try deploying the application, because Elastic Beanstalk is going to be a little bit brutal when it comes to validating the JSON here. It's going to be a lot more challenging to figure out exactly where the typo was. So again, I do recommend that you do just a quick validation to make sure that you don't have any missed commas or missed curly braces or didn't use single quotes instead of double quotes or whatever it might be. All right, so that's pretty much it for our Docker run aws.json file. So let's take a quick pause right here. We're going to come back to the next section and start setting up our environment on Elastic Beanstalk in the next section. In the last section, we finished up our Docker run file. Now, the last thing that we really have to do here, well, almost the last thing, is create a new environment over on Elastic Beanstalk. And that's going to serve as the target that we deploy our application to, eventually from the travis.yaml file. So to get started, I'm going to open up my browser and I'll navigate to aws.amazon.com. And then I'm going to, again, log into my account. And then just as before, I can either find the services dropdown up here or just type it into the services listing right here, or chances are you might see it listed as a recently listed service. Let me zoom in so you can see this a little bit better as well. So we'll search for Beanstalk, and we are looking for Elastic Beanstalk. Now, you'll notice that when I come here, I see the default dashboard again. That's because I deleted the other project that we had previously created. So as a quick reminder, remember anything that you create in this course, you can potentially be billed for if you are no longer on AWS's free plan. If you only created your AWS account in the last year or so, then you're still on the free plan. But if you made your account more than 1 year ago, then you're off the free plan and you're going to be paying for these resources. So you will definitely want to make sure that you delete any different instances or anything like that that we create through this course. So just like we did previously, on the top right-hand side, I'm going to find the Create New Application button. And for this application, I'll give it a name of multi-docker. And then I'll create the project. Just as before, we have to create an environment that matches up to the application that we just created. So I'll click on Create One Now. We're again going to make a web server environment. We then get prompted with a little bit of a form right here. We don't really care about anything in the first section, so I'll scroll on down to the base configuration. And for pre-configured platform, we're going to choose multi-container Docker right there. And then we can leave it selected as sample application. And then finally, on the bottom right-hand side, we'll say create environment. And that's going to start going through a whole bunch of scrolling information right here. That's definitely going to take a little bit of time. All right, now before we move on, there's one thing that you might have noticed that we've kind of totally missed in all of our discussion about deployment over to Elastic Beanstalk. We missed this in putting together the travis.yaml file. It's something that we have not discussed one bit. If you open up your Docker Compose file, the two very top services that we created inside of here was the Postgres database and the Redis in-memory data store as well. But we have not done a single darn thing with the travis.yaml file or the docker run aws.json file to say that we need an instance of Postgres or a container running Postgres or Redis at any point in time. So it kind of seems like we completely dropped the ball on that, like we just totally missed it. Well, this actually kind of leads into a larger discussion that I want to have about running databases inside of containers. So let's take a quick pause right here while our environment is being created. We'll come back to the next section and we'll talk about how you and I are going to approach creating a container with Postgres and Redis for use inside of our application. So quick break and I'll see you in just a minute. In the last section, we created a new Elastic Beanstalk environment for our multi-container Docker application. It looks like my application has successfully been created. But before we start working with this thing at all, I want to have a quick discussion on something that it seems like we kind of left out in all of our Docker run file stuff and all of our Travis stuff so far as well. So inside of our Docker run file, like I said at the end of the last section, we appear to have no references to any containers that are running Postgres or Redis, as we had previously set up inside of the Docker compose file. So let's talk about why that is. All right, so I'm going to show you a couple diagrams. I want to first remind you about the overall architecture of our development environment. We had said, yeah, we got the Nginx, the Express, Worker, all that stuff. And then most notably, we had the Redis container and the Postgres container as well. So in the development environment, we were running these two data services inside of containers. But as we move over to a production environment, we're going to change up this architecture in a pretty significant way. Now, we're going to make this architecture change for a very good reason. So let me show you first a diagram that's going to tell you a little bit about the architecture, and then I'll tell you many reasons about why we're going to take this alternate approach in production. Okay, so first off, the diagram. Here's what our architecture is going to be in the production environment. So we're still going to have the Nginx routing server, the Nginx file server, the Express API, and the worker, and those are all going to be running inside of our Elastic Beanstalk instance. We've already wired up the definition for all four of these containers inside of that Docker run aws.json file. The instance of Redis and the instance of Postgres that are going to be serving data for our application, however, will not be inside of the Elastic Beanstalk instance. Instead, we are going to rely upon two external services to fulfill all of our data needs for our application. The two services that we're going to use are called AWS Relational Database Service, very frequently abbreviated as simply RDS, and Amazon Elastic Cache. These are two services that are kind of general in nature. And when I say general in nature, I mean that they're not customized specifically for using with Elastic Beanstalk. They're not customized to be specifically used with containers. They can be used with just about any type of application out there you can think of, whether or not it uses Elastic Beanstalk or whether or not it uses containers. So they are general data services that can be used with just about any application. All right, so let's talk about why we're going to be using these services to host our copy of Redis and our copy of Postgres. So there's a couple of very good reasons that we might choose to use these outside services rather than creating our own containers manually and using our own containers for housing Redis or our Postgres instances. So in the case of Elastic Cache, got a couple of very good reasons to use this service as opposed to making our own copy of Redis and hosting it inside of that instance. So first off, Elastic Cache is going to automatically create an instance of Redis for you. This is an absolute professional grade Redis. So it's got all the settings, all the configuration that you would ever expect to have in a production deployment of Redis. And the common theme here is going to be that there are many settings set up by default for you that are probably going to be very beneficial for your application that you might not even know exist. In other words, you and I might not be Redis experts. We might not really know how to use Redis properly in a production environment. But Amazon has a lot of engineers, like entire teams of engineers who are absolute doctorates. They have their PhD essentially on Redis, and they know exactly how to set this thing up for a production deployment or a production environment. And that's kind of the running theme around why we would choose to use these external services for managing all of our data. These teams at AWS, they know how to set this stuff up and they know how to manage it extremely well. Now above that, with Elastic Cache, it's extremely easy to scale. So as you might imagine, if our application one day got really, really popular and we saw that for whatever reason our Redis instance was crashing all the time because our container or the hardware allocated to our container was insufficient, well, that might be a little bit of a pain for you and I to scale. We would have to figure out some way to allocate more resources to the container. We would have to figure out some way to restart the container without losing any data. Definitely a little bit of a headache there. But with Elastic Cache, we can essentially just say, hey, I think we need some more hardware here. I think that we need to upgrade the amount of memory or the processor or whatever it might be. And Elastic Cache is going to automatically manage that upgrade path for you. And you don't have to worry about doing a bunch of manual configuration or stuff like that. We get built-in logging, built-in maintenance. If there are security patches around Redis, AWS is going to automatically apply them for you. You're going to get automatic logs generated. You don't have to worry about getting logs out of your container and somehow reporting them to some outside service. In addition, very closely related to the first item up here that we spoke about, we're definitely concerned about security inside of our application, and we've done a couple of things to upgrade the security of our containers. However, with Elastic Cache, chances are they probably have a better idea around security than we do. And so I kind of feel a little bit more comfortable kind of delegating all these responsibilities off to AWS rather than trying to manage security on my own for this particular service. Now, this last one right here, this is one of the real big ticket items. This is one of the big reasons that you might choose to use one of these outside data services. We have a application architecture set up right now that is completely reliant upon Elastic Beanstalk and totally reliant upon making use of containers. I don't know what our application lifecycle is going to be. In other words, I don't know how long my application might need to be deployed and maintained. It's entirely feasible that at some point in time in the future, we might decide to migrate off Elastic Beanstalk and go off to some other service. And when we do that migration, it's going to be a lot easier to migrate away if we are making use of Elastic Cache, because it's completely decoupled from Elastic Beanstalk. Elastic Cache doesn't care where you're making a connection to it from. It could be from Elastic Beanstalk, it could be from some Kubernetes cluster, it could be from some random EC2 instance. All Elastic Cache cares about is that you are making a connection to it. And so it'll be much easier to make changes to our application in the future or entirely change the architecture if we're making use of this outside service. Now, essentially all the same points apply to the relational database service as well. Everything totally related as well. Yeah, they got these teams who know really well how to set up Postgres for production deployments. They make it really easy to scale, log, security. Now, the real big ticket item here, however, is this point right here. So something that does not get very frequently covered in a lot of courses, even courses that I make, is making backups of your database. In other words, making a backup of all the records in your database in case anything goes wrong at some point in the future. Setting up automated backups is not the easiest thing in the world, and in many cases, if you want to get some easy service to do it for you, you actually have to pay a little bit extra for that. And I'm talking about if you're using like a third-party add-on that's going to attach to your container and make automated backups or whatever might need to happen. AWS RDS, or Relational Database Services, has automated systems for taking backups for you. And if you ever decide, oh no, we've got some data corruption or we did something really wrong inside of our application in the production environment, it's like 1 or 2 button clicks to roll back your database to one of those backups. And so with AWS RDS, it makes life just incredibly easy when you start thinking about maintenance of data and data security. So that's kind of my spiel. It might sound like I'm a huge fanboy of AWS or something like that. In reality, no, I'm not a huge fan of AWS one bit, to be totally honest with you. I think that many aspects of it are rather challenging to work with. I'm not the biggest fan. However, I still do recommend making use of these outside services anytime that you're working with, say, Postgres or Redis or Memcache or any type of outside data service. I do recommend that you try making use of these services wherever possible because they're going to do a lot of stuff for you that is by default kind of challenging to do on your own. Now, one last thing I want to say here, yes, these services do cost a little bit of extra money, but to be honest, if you're making a serious application, we're talking about like dollars per month for running a Postgres instance and dollars per month of running a Redis instance. As a software engineer, your time is worth money, and it might take you an entire day or entire week to set up and maintain Postgres and Redis in a very appropriate fashion inside of Elastic Beanstalk. And so that one day or that 1 week, well, that time that you're spending, that is money. Your time is worth money. And so at the end of the day, it kind of is worth justifying to say, yeah, we're going to spend like $10 or $20 per month on a Postgres instance hosted through RDS rather than trying to maintain it on our own. All right, now very last thing I want to say here. So having said all that, yeah, I'm kind of advocating making use of these automated services. But having said all that, this is a course about getting a application running using containers. So our next project is going to set up Redis and Postgres in a production environment from scratch. We're not going to make use of any external service. So although I do recommend that you use the external services, I still want you to understand how we can set up an application that doesn't use them at all if you want to essentially strike it out on your own. Or if you're ever hosting on an environment that doesn't provide these kind of managed solutions. For example, let's say DigitalOcean. DigitalOcean doesn't have automatically managed copies of Redis or Postgres available, and you would have to manage those instances yourself. So we are going to go through an example of how you would set all this stuff up on your own in a production environment as well. But at the same time, in this example, I want to show you, I just want to show you both too. Okay, so enough of me rambling on about this. Let's take a quick pause right here. When we come back to the next section, we're going to start setting up a instance of Elastic Cache, instance with relational database services, and then learn how to wire them up over to Elastic Beanstalk. So quick break, and I'll see you in just a minute. In the last section, we spoke about reasons that you might decide to use an outside Elastic Cache or RDS instance for data needs in your application. In this section, we're going to talk about how we set up these outside services and connect them to Elastic Beanstalk. So unfortunately, you have to do a little bit of behind the scenes work here. Fortunately, the amount of work we have to do is very, very small. Like it's just going to be a handful of clicks, but the very few clicks or the very few actions that we're going to take require some kind of specialized knowledge. And so before we go and create the RDS instance or the EC instance, I want to very quickly give you an overview of exactly what we're going to do. All right, so you and I are going to have an Elastic Beanstalk instance, and inside of it are going to be our 4 different containers. And we're going to eventually want to connect those containers, or at least some number of them, to RDS, the Postgres instance we create, and Elastic Cache, or the Redis instance that we create. Now, unfortunately, in the world of AWS, by default, these services do not get to talk to each other. In other words, once we create these other services, we cannot just automatically say, oh, hey, containers, go out and find this RDS instance for me and connect to it and make use of Postgres or whatever you might want to do. Instead, we have to form up a very distinct link between the two. And that's the kind of series of clicks that we have to go through. Now, when I use the word link, I am not talking about the same kind of link that we put together inside of the Docker run file just a little bit ago. So the kind of connection between Elastic Beanstalk and RDS and EC that we're going to form up here has absolutely nothing to do with Docker. Docker is not involved one bit whatsoever. This is a completely unrelated aspect of wiring up these different services together, completely unconnected from Docker. All right, so here's the background. Here's what you need to know. Right now, when we created our Elastic Beanstalk instance over here called multi-Docker, it was created in a very specific region of the world. So Amazon has a variety of different regions, or essentially data centers, where you can create these different services. Right now, I'm using the Northern California region. You can find what region you're using on the top right-hand side. And you can actually also just take a quick glance at the URL to get the actual kind of like region code of where you are. So for me, I'm at US-West-1. That's the kind of technical designation of US West or Northern California. Now, in each of these different regions, by default, you get something created that is called a virtual private cloud, or VPC for short. A VPC essentially is kind of its own private little network so that any instance or any different service that you create is isolated to just your account, and it doesn't get automatically shared with like someone else's AWS account. In other words, when you create an Elastic Beanstalk instance, only your account is going to have access to that instance, and not like Bill, Joe, or Ted down the street. They're not going to magically see this Elastic Beanstalk instance appear in their account. Now, this VPC right here is also used to implement a lot of different security rules and a lot of different ways of connecting together these different instances or these different services that you create on AWS. Now, before we move on, just one thing to make really clear here. In each of the different regions or data centers around the world, you automatically get one default VPC created. And so when we created our Elastic Beanstalk instance, it was automatically assigned to that default VPC, unless you are a total total AWS whiz, and you already decided to assign it to some other VPC for whatever reason. You get one of these default VPCs for every region around the world. Let's very quickly flip over to the AWS console, and we'll take a look at the virtual VPC that was created for us. All right, so on services, I'll do a search for VPC, and that will bring up the VPC dashboard. And then once over here, you can click on your VPCs on the left-hand side, and it will show the default VPC. If you see multiple VPCs right here, it's probably because at some other point in time, you went through the process of creating another VPC. I only have one right here, and this is my default VPC. I can tell by scrolling over to the right-hand side, and you'll see this default VPC column says yes for me. Now, if I look at my ID right here, you'll notice it's like 0330 whatever. If I now flip over to some other region around the world, like let's say Paris, for example, I can flip over here. And after a very long load time, because this is on the other side of the world from me, so here are all the VPCs that I have in the Paris region. You'll notice that the ID of this VPC is distinctly different. So I copied the ID of the other one. In Northern California, I had 0330. Over here, I have 043F. So in other words, in every region, you get a different default VPC. All right. So with that knowledge in mind, we now are going to kind of take that idea of a VPC and figure out how we can get our different services to connect to each other. So to get these different services to connect to each other, we have to create something called a security group. A security group is a really fancy term for firewall rule. It's a rule describing what different services or what different sources of internet traffic can connect to different services running inside of your VPC. When you created the Elastic Beanstalk instance just a couple of seconds ago, or a couple sections ago, excuse me, a security group was automatically created that allows any incoming traffic from anywhere in the world to connect to port 80 on your Elastic Beanstalk instance. Each of the different security groups that you create are going to apply to some set number of different services that exist inside of your VPC. So the security group that was created for Elastic Beanstalk is already kind of attached or kind of scoped to your Elastic Beanstalk instance. And that's what allows someone else in the world to come into your virtual private cloud and connect specifically to your Elastic Beanstalk instance. Now, to look up this security group, we'll go back over to the VPC dashboard. Make sure that you're in the same region as where you just created the Elastic Beanstalk instance at. And then on the left-hand column, you can scroll down to security groups right here, and you'll see that there is a security group with the name of multidocker-env. So again, this was a security group that was created for our Elastic Beanstalk environment. If you click on this thing, you can then see a little summary down at the bottom. And most interestingly, you can click on inbound rules. So these are the kind of security rules or firewall rules that are going to be applied to your Elastic Beanstalk instance. And so this inbound rule says that we're going to allow all HTTP traffic to come in on port 80, and that traffic can come from absolutely any source in the world. Security groups can also optionally have outbound rules as well. The current default outbound rule essentially says, yeah, we're just going to allow all traffic whatsoever, any traffic you can possibly imagine from that Elastic Beanstalk instance to reach any possible destination across the globe. All right. Now on this diagram right here, I also reflected like an additional security group. This was just a random one. I just mean to say you can create your own security groups that customize the way in which your different instances are allowed to receive or respond to traffic. So now that we understand what a VPC is, and now that we understand what a security group is, how are we going to form a connection between Elastic Beanstalk and RDS and EC? Well, here's what we're going to do. We're going to create a new security group, and the security group is going to say, essentially as a rule, let any traffic access this instance if it belongs to this security group. So we're going to create the security group, and then we're going to attach it to all three of these different services. So they're all going to belong to this one common security group. And the security group essentially says, if another AWS instance belongs to this thing right here, then let the traffic flow through and let these different services talk to each other. So that's how we're going to get Elastic Beanstalk to talk to RDS and to EC as well. Again, the big takeaway here is that by default, when you create these services, they don't get to talk to each other. So we have to create the security group that specifically says, yeah, these different things can communicate with each other. All right, so that's pretty much it. I just wanted to give you a quick overview on the entire process before we go off and create the RDS and EC instances, because once you create them, it then gets a little bit confusing about, hey, what are we doing here? Why are we clicking around all over the place? So let's take a quick pause right here. When we come back to the next section, we're going to start to create the RDS instance and the EC instance, and then create a new security group and apply that security group to all three of these different services inside of our VPC. So quick break, and I'll see you in just a minute. In the last section, we had a very long discussion about the existence of VPCs and how security groups are used with them. So we're now going to start to create our RDS service that's going to be essentially a managed version of Postgres. And then if we have enough time, we'll do our Redis instance inside of Elastic Cache as well. So to get started, I'll flip back over to my AWS dashboard. I'm going to make sure that I'm still inside the same region as my Elastic Beanstalk instance that I already created. And then on the services drop down at the top, I'll do a search for RDS. Again, that stands for Relational Database Service. All right, so once over here, you'll see like a ton of different pop-ups, a whole bunch of different stuff going on. If you see this kind of notification or anything like that, you can just close it at the top. And then we'll scroll down a little bit and find a section marked as Create Database, which is of course what we definitely want to do. So I'm going to click on Create Database. We then have to select the type of database that we want to create. So we can make a MySQL, Oracle, Microsoft SQL Server. You could do Amazon Aura, which is a fork, I believe, of MySQL, specifically customized for AWS. But of course, for you and me, we want to make a Postgres instance. So I'll select Postgres over here. And then you get your little marketing spiel down here. I do recommend that you check this box down here to enable only options for free tier usage. Now, again, if your AWS account is over 1 year old, you do not qualify for free usage tier. You will see this option right here, even if you do not qualify for free usage. So my AWS account is many, many, many years old. I do not qualify for the free usage tier, but I still see the checkbox right here. I'll click next on the bottom right, and then we get asked to enter in a couple of details. So if you wanted to change the default version used, you could do it right here, but the default version is totally appropriate for us. You can then go a little bit lower and find DB instance class. Because we checked the only enable options eligible for free usage tier, the only class that we get is this T2 micro, which is essentially a very, very, very tiny virtual machine. Not a lot of power behind it. Maybe not the best instance to use if you expect a lot of traffic to come today to your database. We'll then scroll down a little bit more. You can see allocated storage right here. We definitely do not need 20 gigabytes for our application, but it is the minimum, so we'll leave it as that. We can then specify a couple of different settings in here, so stuff like DB instance identifier, blah, 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 all this other stuff. The only thing that we really care about is the master username and the master password. The username and the password right here maps up against, you might recall, inside of our Docker Compose file, at our API right here, you'll recall we had the Postgres username, the database, and password. So those entries that we're going to enter in over there map up to these environment variables that we're going to eventually have to get into the API container at some point in time. So these are very meaningful pieces of information over here. Let's fill in the instance identifier first. I'll call this about just multi-Docker RDS, or how about multi-Docker Postgres. We'll do a username here. You can do any username and any password you want. Just keep in mind you have to remember these because we need to pass them off to the API service when it gets created on Elastic Beanstalk and at some point in the future. So I'm going to use a username of Postgres, and I'm going to use a master password of Postgres password. Postgres password. And then I'm going to flip on over and just create a new temporary document over here just to remind myself about those values. So my username is Postgres, and my password is Postgres password. Again, you're going to need these pieces of information in just a little bit. So then we'll click on Next. Now you might get some other options on here. We want to put this new database inside of our default VPC because we want it to talk to every other service out there. Ideally, we would assign a subnet group, but that's just a little bit outside of the scope of what we're doing in this course, so we'll leave it on default. And for public accessibility, we're going to be very, very 100% sure that no is selected, because we do not want this thing to be publicly accessible by any other service beyond the ones that we assign to our security group, which we discussed just a little bit ago. And then finally down here, you'll see VPC security groups. Now, we are going to eventually make our own custom VPC security group and allocate everything to it, but you can just select create new VPC security group for now. But we're going to essentially overwrite that thing, or at least change its rules. Now, just a little bit more settings on here. We have to specify a database name. This is the same database name that we had to specify over inside of our Docker Compose file that I was just talking about a moment ago. So this is the PG database right here. So for my database name, I'll do something like, I don't know, fib values. I think that's reasonable. And I'm going to make sure that I record that is fib values, because again, we're going to need all this information in just a little bit. I'm going to make sure that I leave the default port on here, no reason to change it. And then we don't have to do anything with encryption. If you want to set up backups, this is where you would do it. Remember, I had said that with these managed solutions, they will automatically make backups for you so that you can easily roll back information if anything really goes wrong in your application. The default is 7 days. You can go all the way down to like, oh, not 0 days, 1 day, I suppose. You can actually do even more fine-grained details than that, I believe, if you are willing to pay some money. We'll leave it as the default of 7 days. And that's pretty much all we have to do here. So I'll click on Create Database at the very bottom. And then it's going to say, hey, it's going to take a couple of minutes to do this, which is totally fine. I can then click on All Database Instances, and we'll see the new database we just created right here, and it has a status of creating. Okay, so that's it for RDS. We're going to let this thing do its bit. Let's take a quick pause right here. We'll come back to the next section and do our Elastic Cache setup for Redis as well. So I'll see you in just a minute. In the last section, we put together our RDS instance, and we're just going to let it do its thing as it creates that database. While that's working, we're going to flip on over to another dashboard and create our Elastic Cache instance as well. So I'll click on Services up at the top, and I'll search for Elastic Cache. And okay, I've been saying Elastic Cache. I guess it's really Elastic Cache, whatever, all the same. Okay, so once over here, we're going to scroll down a little bit. And we really want to launch a cluster, but it's showing me this kind of annoying dashboard right here. Let's try clicking on Redis on the left-hand side, and then we'll find the Create button up here. So then this is going to walk us through the process of creating a cluster. Now, the interesting thing here is that we are specifically making a cluster. So technically, when you make an Elastic Cache instance, we are getting a copy of Redis, but there's some kind of separate nodes that just relay information from the primary Redis node. Way more detail than we really need to go in. Just so you know, essentially we're getting a very high-powered copy of Redis that would do really, really well if we had a lot of traffic. Now, by default, we don't really get the cluster created unless you select that little option right there. We do not need a cluster, so we're just going to leave it set as Redis without that checkbox checked. So then we'll throw a couple of options in here. For the name, I will enter in multi-docker Redis. We don't need a description. We can leave just about everything else on here at the default, except for the node type. So the default node type is a very expensive little instance. You would pay a lot of money for this thing, so we want to 120% make sure that you do not use the default selection here. So we'll click on little dropdown, and then we're going to go to T2, and we want to do cache T2 micro, which is the cheapest copy around. It's also the lowest performance, but of course our application doesn't really have very high performance demands. And we'll click on save. Now I want you to really verify right here that we do in fact have the cheapest option selected, which should be a cache T2 micro. If you have anything else selected, you will pay some dollars for it. We then get asked for the number of replicas. In this case, replicas would be kind of those separate nodes that kind of supercharge your copy of Redis, again, kind of outside the scope. We don't need any replicas because we definitely do not have high performance demands for our application. So I'm going to change replicas to none. All right. So now we get asked a couple of other settings over here. Some of these are just a little bit nasty. We get asked to create a subnet For this, we'll create a new subnet. This has to do a little bit with security. We don't really need to focus on the details of this thing too much. All we need to do is put in some name right here. I'll say Redis group. The one thing we do care about is marking the VPC ID as the default VPC. And so if you have a fresh AWS account, or if you've never created any other VPCs, the only option right here will be the default VPC that is created for your region. And so you will want to select that default VPC so that it's in the same kind of networking group as the RDS instance we put together already and the Elastic Beanstalk instance that we put together as well. And then for the subnets, we can just check both these right here. And it's just going to give us access to those different subnets. All right, and that's pretty much it. You'll notice that we also have the option to select a security group right here, but we're going to take care of the security group in just a little bit as a little follow-up to all this stuff. So I'll scroll on down to the bottom, and I'll click on Create. And that's pretty much it. It's now creating our instance of a Redis group of, I don't know, cache instances, whatever you want to call it. All right, so we got to wait for this thing to be created as well. So we'll take a quick pause, and when we come back to the next section, we're going to do the last step, which is to wire all this stuff up with a common security group and apply that security group to the Elastic Beanstalk, RDS, and EC instances. So quick pause, and I'll see you in just a minute. In the last section, we set up our Elasticache Redis instance. You should eventually see this thing flip over with a status of green available. If you don't see it ever flip over, you can click the refresh button on the top right hand side. It should take some handful of minutes, somewhere up to, I don't know, 4 or 5 minutes or so. Now, just in case you skipped through the last section, one thing I want you to triple check right now, make sure that you have a node type of something like cache T2 micro. If you see something like M2 medium or M2 large or M4 or something like that, you might end up paying a decent amount of money for this Redis instance. So please make sure that you did correctly update the node type, and you can see the value of it right there. So now that we've created both our Redis instance and our Postgres instance, we're going to now create a security group that is going to allow all three of these different services to talk to each other. So to create the security group, we're going to go back over to the VPC dashboard. To get there, I'll go to Services on the top left-hand side. I'll search for VPC and click on the VPC option. Then on the left-hand side, we're going to scroll down just a little bit, find the Security section, and go to Security Groups. Now in this list, you're going to see that we now have a new security group listed that we did not have before. It is the RDS Launch Wizard. This is a security group that was automatically created when we were making the Postgres instance. We don't have to do anything with this. We're going to actually create a new security group to allow communication between our three services. So to create a new security group, I'll click on Create Security Group at the top. And then we get prompted for a little bit of information. For the name, we'll do multi-docker. And for the description, I'll say something like traffic for services in multi-docker app. And then I'll make sure that I have my default VPC selected on this dropdown. If you only have the default VPC created in your account, like I do, you're going to see only the one option right here. If you have created other VPCs for any reason, you'll want to make sure that you select the default VPC, unless you know what you're doing and you're trying to create all this stuff in a separate VPC. So then finally, I'll click on Yes, Create. Now we're going to wait just a minute or two for this thing to be created, and then we'll see it up here on the list right here. And so it's the one with the name tag of multi-docker. So we just created the security group. Now we need to create a rule inside of it that's going to specifically allow traffic between any service that is assigned to that security group. So to create that rule, I'm going to select on the security group, and then I'll go to the Inbound Rules tab, and I'll go to Edit to add a new inbound rule. Now we're going to leave the type as custom TCP. We'll leave the protocol as TCP. We'll leave the port range as 0 to just open up all ports. Actually, you know what? Let's restrict this just a little bit. There's no reason to open up everything. We'll allow just the ports between the default Redis port and the default Postgres port. So it's going to be everything from 5432 to 6379. So I'll do 5432 to 6379. And notice how I'm separating the two with a little dash. Then for the source, this is the important part, we're going to allow traffic from any other instance that is in the same security group. So I'll click on source right here, and then I will select the SG multi-docker. That is the security group that we just created. That's the one that we are editing right now. So I'll select that, and that's going to allow traffic between all the different services that are assigned to this thing. All right, so that's pretty much it. I'll click on save right here. Save is successful, and now that's pretty much it for the security rule. Now, all we've done at this point was create the security group. We now have to go back through our 3 different services and assign the security group to each one. So we have to go look up Elastic Beanstalk instance. We have to apply the security group. We have to do the same thing for RDS and EC as well. So let's take a quick pause right here and continue in the next section. In the last section, we created our new multi-Docker security group that's going to allow traffic from any other instance that has the same security group applied to it. Now that's not the end of the story. We still have to go back over to each of these instances or each of these services and apply the security group to them so that they actually belong to the security group. So we'll start off first with Elastic Cache, and then RDS, and then update Elastic Beanstalk as well. So first, let's open up the Services tab up here. And on the left-hand History tab, you should see Elastic Cache. If you don't see it there for any reason, you can always do a search for cache and find Elastic Cache up here. Once over here on the dashboard, we'll select Redis on the left-hand side. I'll then select this little checkbox right here and then click on Modify at the top. This will open up a little window that's going to allow us to make changes to this cluster. We're going to change the VPC security groups. So we'll click on the little pencil, and then we'll put a checkbox next to the multi-Docker security group. And then finally, save. Now, normally when we make a change to a Elastic Cache cluster, it's going to try to schedule that maintenance for some very specific time, usually some overnight period where hopefully not a lot of people are using our service. But making changes to a security group doesn't actually require a maintenance window, even though this thing is going to tell you that it does. So we can just click on Modify, and it will immediately start to change the security groups on there. That's pretty much it. So we'll now move on to our next service, RDS. So I'll again go up to the Services tab. I'll do a search for RDS and find Manage RDS. We can find the Instances section on the left-hand panel, and then select the one database instance that we have, the multi-Docker Postgres. Now, finding the security groups on here, it's a little bit more buried, so we're going to scroll on down past all the different charts that we have on here. So scroll, scroll, scroll. Here's the Details section. Under Details, you'll see all the different security groups that are currently being applied to this instance. We can't change it from right here. We have to go back up to this Details heading, and then look all the way over to the right-hand side, and you'll see the Modify button. So we'll click on Modify, and then we go back into this kind of wizard screen. We'll scroll on down to Network and Security, and you'll see the Security Groups section inside of here. You can select this drop-down and then find multi-Docker right here. So there's multi-Docker being applied as a security group. And then we'll scroll on down to the very bottom. And at the very bottom, you'll see the button that says Continue. So click that. Now, again, it's going to tell you that it wants to schedule maintenance and it wants to make this change at some point in the future. That is not true of a security group change. You don't have to schedule any maintenance, but if you feel like it, you can just hit apply immediately. Again, it's not going to actually restart the database or anything like that. So either one, just go ahead and click Modify DB Instance. And then if you click on Instances, again, back on the left-hand side, you may or may not see this thing flip over to something that says like Updating. If I refresh here, okay, sometimes it does, sometimes it doesn't. But if you click on the database again, and then scroll back down to that Details section, you will see Security Groups adding the multi-Docker security group right there. All right, so that's it for RDS. So the last one we have to take care of is Elastic Beanstalk. So I'm going to again go up to Services. I'll find Elastic Beanstalk on History. Now, as you can see, my environment is a little broken right now, which is totally fine. I made a little change to it. It's not actually broken. It just thinks that it's very temporarily broken. So just ignore the fact that I have a severe environment for right now. No issue there. On the left-hand side, we'll find the section that says Configuration. And then in the very middle here, I'll see the card that says Instances. We'll click on Modify on the bottom. And then we'll scroll on down to the very bottom here, and we'll see EC2 security groups. So as you might guess, we're going to add a checkbox next to multi-Docker, and then I'll click on apply. We're going to get a quick warning right here. This is just saying that it's going to create all of our, or restart our EC2 instances, which is no issue whatsoever because we're not doing anything with our Elastic Beanstalk instance just yet. So on the bottom right-hand side, I'll click on confirm. Okay, so that's going to update our environment, which will take just a couple minutes. So let's take a quick pause right here. We'll come back to the next section and start working on a little last piece of setup of our environment on Elastic Beanstalk. So quick break and I'll see you in just a moment. In the last section, we wired up a security group to all three of our different important resources, the Elastic Beanstalk instance, RDS, and EC. Now, the very last piece of configuration we have to do now is make sure that our different containers inside of the Elastic Beanstalk instance know how to reach out to RDS and EC. And so to do so, we have to set a couple of environment variables, just as we did previously inside of our Docker Compose file. So remember, inside of Docker Compose, on our API, or the Express server, we set up this list of different environment variables. And we did the same thing for our worker process as well. Here it is right here. We set up the Redis host and the Redis port. So in order for both our Express API and the Redis server, or excuse me, the worker, to work correctly, we have to provide these different environment variables. So that's what we're going to do by using the console over on Elastic Beanstalk. So I'm going to make sure that I'm still looking at my Elastic Beanstalk instance. I'm going to find configuration on the left-hand side, and then I'll select modify on the software card. I went there really quickly, sorry about that. On the software card, I'll select modify. And then down at the very bottom, I'll see the different environment properties that I can set up. Now, I'll be honest with you, these environment properties do not get their values hidden over here. And so once you enter these properties in, potentially other people could come to this page and see your database password. I've looked at the Elastic Beanstalk documentation, and supposedly this is nonetheless where we're supposed to put these passwords. I don't know if there's a better place out there. If there is, I encourage you to add a note on this lecture and say, hey, here would be a better way of doing this. This is one of my kind of weak points in this regard. So let's get to it. We're going to add on a collection of different environment variables here. We're going to go just straight down this list with all the different variables. So the first one we'll add in is the Redis host. So the name will be Redis host, and then the value is not going to be simply just like, Redis or anything like that. It's going to be the actual endpoint or URL of our running Elastic Cache instance. So to get that, we need to actually flip on over to the Elastic Cache dashboard one more time. So I'm going to scroll up, I'll go to services, and then I'm going to open up Elastic Cache in a new tab. And then I'll close the services dropdown and go back down to environment properties. Now in the second tab that I just opened up, I can look at Redis. I can click on the little arrow right here to expand it, and you're going to see primary endpoint listed right here. So we're going to copy that primary endpoint. Now note, on the primary endpoint, there's the :6379 to designate the port. We don't want to copy that, so I'm going to make sure that I copy everything to the left of that colon. So I'm going to copy that. I'll go back over to my environment properties, and for Redis host, I'm going to paste in a value of that endpoint. Now, take note, on the very right-hand side over here, I do not have a colon. I do not have the 6379. So please make sure that you trim that off as well. So next up, we'll do our Redis port. So I'll again copy the name of the variable over. And as you might guess, we're using the default port of 6379. So I'll set a value of 6379 like so. All right, that's it for Redis. So now we're going to move on to PG user, all the other Postgres variables as well. So for PG user, I'll copy that over. And this is where I hope you still have that document where we saved some of the different user names and whatnot. So this is the different variables that we entered when we created our RDS instance, or the Postgres instance. So my username that I used was simply Postgres. So I will copy Postgres over for the PG user entry. Next up, we need our PG. Let's skip on down to the password because those should really be right in a row. So my PG password was Postgres password. And that's what I wrote down in my document over here. Next up, we need our PG host. So I'll put in PG host. We again need to open up the RDS dashboard, just like we did with Elasticache, and get the endpoint for our Postgres instance. So I'll flip back over to that second tab. I'll again go up to services. I'll go back to the RDS dashboard. I'll click on the instances section. I'll open up the database instance. And then finally down towards the bottom in that details section, oh, not details, but connect right here, I'll find the endpoint listed. So I'm going to copy that entire endpoint, and then I'll paste it back over on my environment properties for the PG host, like so. Okay, so we've got PG user, password, and host. I think we just got a couple more here. See, we got PG database. So that's our next key, PG database. For that, my database name was fib values. That's why I called my database. And then finally, we got our PG port. That's the very last one, PG port. And as you can see over on the dashboard, we did not change the default port of 5432. Okay. Now, quick pause right here. I gotta tell you, in all the courses I've ever done, the most common error that I ever see in my life, this is repeated over and over and over again, the most common error by far is people entering in these environment properties with incorrect spellings for the names or incorrect values. So at this point, I gotta ask you, please, I beg you, triple check the names of all the environment properties listed over here. And I'm going to tell you right now, if your application worked successfully in our development environment when we were using Docker Compose, but does not work properly when you push it up to Elastic Beanstalk or you push it up to production, one of the first things that I will tell you to troubleshoot is to come look at these variable names and all the different values and triple check to make sure that they are correct. So I ask you again, please triple check the names, triple check your values, make sure you've got the correct things in here. Now, once you've got everything entered in successfully, we'll hit the apply button on the bottom right-hand side. Okay, so that's going to make a couple changes and apply them to our environment. Okay, so that's pretty much it. That's all we got to do for setup. Now, one little piece of trivia here, something you might be curious about. Back when we put together the Docker Compose file, we had to manually specify all these environment variables and specifically pass them into this specific service. And we did the same thing for Redis on the worker down here as well. Now on Elastic Beanstalk, when you set up those environment variables, they automatically get added to all of the different containers that you listed inside of that Docker run aws.json file. So every single one of these containers has automatic access to that set of environment variables. So we do not have to do any additional environment variable mapping. So that makes life a little bit easier. Okay, so that's pretty much it. That's all we had to do for the AWS setup. So now the very last thing we have to do is a couple more changes to the travis.yaml file to make sure that after we successfully build all these images and push them off to Docker Hub, we are going to do that little tap on the shoulder of Elastic Beanstalk and tell it to repull all the images and attempt to deploy them. So let's do another quick break, come back to the next section, and start to wrap up the travis.yaml file. In the last section, we finished up just about everything on the AWS dashboard. There's one last little thing we have to do, and it's tied to the deployment that we're going to set up inside of our travis.yaml file. So remember, at this point inside of the travis.yaml file, we're currently building the production version of all of our images, and then we push them off to Docker Hub. Now, I have said several times that after we do all that stuff, we're going to then kind of tap on the shoulder. Here we go. We're going to kind of tap on the shoulder of Elastic Beanstalk and say, hey, it's time for you to go and pull these new images and deploy them. And so I'm going to be honest with you, when I said kind of tap on the shoulder, I made it sound like it was a different deployment process than what we had done on the previous application. In reality, it's going to be no different. We're going to still deploy the entire application over to Elastic Beanstalk. The only difference this time around is that the only file that we really have to deploy is or send over to Elastic Beanstalk is the docker run.aws.json file. We're going to send the entire project over to Elastic Beanstalk, but in reality, this is the only file that we really have to send. Once Elastic Beanstalk gets this file, it's going to pull these images from Docker Hub and take it away from there. But again, I've been saying like, oh yeah, we're going to send a little notification. there's not really a notification. We're just going to dump the entire project over the same way we did previously. Now, I've got the Travis file from our previous project. Remember, this is the single container application that we just put together. And here's what we did for the deploy section. So we had to set up the provider as Elastic Beanstalk, specify the region, app, environment, blah, 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 all this different stuff. And one of the real keys in here was providing the access key ID and the secret access key as well. And these were both set as environment variables on our Travis CI dashboard. So in this section, we're going to generate a new AWS access key and secret key on the IAM dashboard on AWS, and then we will assign those as environment variables to our Travis build. So let's get to it. So to get started, I'm going to open my AWS dashboard back up. I'll go to Services, and we will again go to IAM. And then on the left-hand side, I'll find the user section because we're going to create a new user with deploy access to Elastic Beanstalk. So I can click on that Add User button, and then I will use a username of something like multi-docker. How about multi-docker deployer? That makes sense. And then we'll give it an access type of programmatic access. And then permissions. Again, we're going to attach existing policies directly. I'll do a search for Elastic. Actually, we'll do just Beanstalk is probably the easier one to search for. And then we're just going to add everything straight down here. Just toss it all on. We could definitely go a little bit more fine-grained, but for right now, I just want something that's going to work as it stands. I'll then do Next Review. And then we'll do a Create User. And now this is going to show us the user, the access key ID, and the secret access key. Remember, this secret access key right here is something that you do not want to share with the outside world whatsoever. And of course, you can try to use my secret access key, but by the time you watch this video, I will have deleted it because we've got to be responsible with those secret access keys. So now that we've got the keys right here, we'll open up Travis CI again and set these up as encrypted variables on the dashboard. So I've still got my Travis dashboard open. As a quick reminder, you can get here by going to travis-ci.org. Once over here, you're going to make sure that you open up the multi-Docker project. So make sure that you are not looking at Docker React. This is bad. We're going to look at multi-Docker. We'll then go over to Options, Settings, and then we're going to add in some new environment variables. And of course, we can still see the Docker ID and password that we had previously set up. So the first variable we will set up is the AWS access key. And then I'll copy over the access key and paste it in as the value. Now, like I just said a moment ago, please triple check the spelling on the key right here. So AWS access key, make sure it's got the 2 C's and 2 S's in it. And then I'll add that thing. And then we'll do the same thing for AWS secret key. And I'll copy the secret key over here and paste it in as the value. And again, please triple check, make sure you spelled secret correctly, especially the word secret. This is a very easy word, believe it or not, to misspell. We'll click on Add, and that's pretty much it. Okay, so we've set up our environment variables over here. So now the last thing we need to do is add on our little deploy script at the very bottom of the travis.yaml file. So let's take care of that in the next section. So quick break, and I'll see you in just a moment. All right, we just about got everything set up. The very last thing we have to do is add on the deploy section to our travis.yaml file. So let's get to it. Now, the deploy section that we're going to add on here is going to be just about identical to the one that we did on our previous project, the single container deployment. So a lot of these options are going to be very similar, and so we're going to go through them rather quickly. So at the bottom of travis.yaml, I'll add on the deploy section. I'll add a provider of Elastic Beanstalk. Quick reminder here, we do not put any dashes in here because these are not array entries. It's all one single configuration object. Next up, we'll add on the region. For the region, I'm going to flip back over to my dashboard for Elastic Beanstalk, which I still have open. And remember, you can get your region very easily by looking at the subdomain on your URL. So that subdomain right there, that's the region that we're talking about. So I'm going to copy that and put it over as my region entry. For my app entry, My app name is multi-docker. That's the first part of the kind of header up here. The env is going to be, or environment will be the multi-docker-env right here. So I'll put that in as the environment. Next up, we have to do our bucket name and the bucket path. And this is going to be where Travis zips up our entire project and where it stashes it inside of some S3 bucket. So remember, we are probably going to want to go over to S3 really quickly and make sure that there's some bucket over there that we can use. So I'm going to flip back over to my dashboard. I'll go to Services, and then S3. And then on here, I'm going to find my bucket for the region that I'm currently in. So for me, it's Elastic Beanstalk US West 1 right here. I'll click on that, and then I'm going to get the bucket name, if I can copy it. I don't think I can copy it up at the top. I feel like I copied it. Yeah, there we go. That's better. So I'm going to copy the bucket name, and I'll put it in here as the bucket name. And then we have to do a bucket path as well. And for this one, I'll again just call it Docker multi. Now previously we had said only try to deploy this thing on branch master. We're going to do the same thing this time around. So only try to run this deployment when the branch that we are pushing or building up on Travis is the master branch. In other words, if we push up some like feature branch, don't try to build and deploy this thing. And then finally, we're going to do our access key ID as AWS access key. Again, remember there are 2 C's in the word access. And we'll do secret access key. And we'll say this is going to be a secret, or excuse me, not secret, but secure AWS secret key, like so. All right, so that's pretty much it. That's all we have to do for our travis.yaml file. So now the last thing we have to do is actually deploy this thing and test it out. So I'm going to make sure I save this file. We'll take a quick break right here, and we'll continue in the next section. In the last section, we pushed up all of our code to GitHub. Travis pulled it down and started to build a project. Now I've got my build right here, and it looks like it was successfully built and deployed off to Elastic Beanstalk. So if you have any error at the Travis CI step, it very likely means that you might have made a typo somewhere along the way. As a reminder, you can always check out the GitHub repository of all of my code, which is linked in one of the very first sections in this entire course. And so that's a great place to get started if you want to do a little bit of troubleshooting. Now, assuming that the deploy for you went successfully, so all the way down here I can see deploying application, no problems with that, we can then flip over to our Elastic Beanstalk dashboard over on AWS. So once you go over here, you might see an error or a warning, which again is totally fine. We very much expected this to happen. I just wanted you to see an example error with a deployment like this. So if I scroll down a little bit, I can see recent events, and underneath recent events, you might notice an error message right here. And it says invalid setting for container client. So that is an invalid setting that was detected inside of our dockerrun.aws.json file right here. In particular, it's complaining to say that we did not specify an option called memory, and we must specify this option if we're going to use the Docker run file. So what's going on here? Well, essentially, we correctly put together our Docker run file, but we missed one required option for every one of our container definitions, and that is a memory option. Essentially, when Elastic Beanstalk decides to create each of these containers, it's going to allocate some amount of RAM to each of them. And so it wants us to tell it exactly how much RAM or how much memory should be allocated to each container. And we do so by adding in a memory option to each of these different objects inside of here. So underneath the essential flag on client, I'm going to put a comma, and I'll specify memory. And then we're going to specify the amount of memory in megabytes. Now for this step, unfortunately, it's kind of challenging for me to give you very strong guidance on exactly how much memory should be allocated to each of these services, or more precisely, how much memory you should use as a rule of thumb. The best guidance I can possibly give you is to do a little bit of research to look up these services that you're trying to host, and there tends to be many Stack Overflow posts that give a little bit of guidance on the appropriate amount of memory to allocate. So for our application, we're just going to do a straight across the board 128 megabytes for every one of our services. Again, I'm not going to necessarily say this is good practice or bad practice, or maybe we're putting too much memory into one service or too little into another. I really recommend that when you start working on your own projects, you do a little bit of research on this front. So I'm going to take this memory 128, I'm going to copy it, and then I'll go down to the server. At the end of essential, I'll put a comma, and I'll paste in memory 128. I'll go to worker, I'll find essential false, I'll put a comma in and do memory 128. And then finally, I'll do the same thing down on Nginx. Here's links, I'll put a comma at the very end, and I'll do memory 128 again. Okay, so that's it. I'm going to save this file, and then we will again flip back over to our terminal. We'll do a git status. So we made a change, and we now want to deploy this change. So we'll do a git add, a commit. I'll say something like added memory allocation, and I'll do a git push origin master again. And now, just like before, this is going to send all of our code to GitHub. Travis CI is going to pull it down, build our images, push them off to Docker Hub, and then attempt to send that Docker run JSON file back over to Elastic Beanstalk. So another quick break, and I'll see you in just a minute. Once again, if anything goes wrong, totally fine. This is all a part of the debugging process. So if anything goes wrong, continue in the next section, and we'll take a look at any possible error message. So quick break, and I'll see you in just a minute. In the last section, we made a little change to our Docker run file and redeployed the application. I've now sat through the redeployment, and it looks like everything went through successfully, and the application should now be working. Now, if you do not see health of OK right here, or if you see any other errors appearing in the log down there, one quick tip that I'll give you for debugging here, and this is where I recommend you first go to figure out exactly what went wrong, you can click over on the Logs tab on the left-hand side. And then on the far right-hand side, click on Request Logs, and then Last 100 Lines. This will give you the last 100 lines of output from each of your containers, along with a couple other services that are used to host your application. So you can then look at the log file by clicking on that download link, and you'll get a very large, rather consolidated log file. So this has logs from a bunch of different services, and they're all placed in these different sections. So this is one section of logs, and it contains all the logs from a ecs-init log file. Remember that when we use Elastic Beanstalk with a multi-container setup, behind the scenes it's actually using that ECS or Elastic Container Service application that we had mentioned a little bit ago. You'll also see some PHP app logs inside of here. Those are logs that are generated by the default Elastic Beanstalk application that was created when we first made our environment. And then if you go through here, you'll eventually start to see some logs from, say, here we go. So our container logs from the client container. Here's from the Nginx container. Here's from a Nginx proxy, which is being used to route information around our application. And here's the server logs right here as well. So again, if you have an error being displayed on the dashboard back on Elastic Beanstalk, I encourage you to take a glance at these logs, read through them somewhat deeply. Somewhere inside of here will be a message telling you exactly what went wrong. All right, so with that in mind, if the deployment went successfully, you can go back over to Elastic Beanstalk and find the URL to the application up here at the very top. So you can click on that link and it will open up our application. And so my app is hosted at multi-docker-env, and then some string, blah, 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 elasticbeanstalk.com. I can now enter in some index of a value to calculate and then click on submit. And if I refresh the page, I'll see that index appear. Cool, so that's pretty much it. We can refresh as much as we want. We can add in some value and it'll just calculate the Fibonacci value for any given number. So that's pretty much it. I hope you've enjoyed this application, at least the deployment part. The last thing I want to show you is in the next section, I just want to go through the process of redeploying the app and making sure that we can get some updates to appear on the screen. So one last section, and I'll see you in just a minute. The last thing that I want to do with our application is a very quick change to some of the source code inside of it. I then want to redeploy the application and just make sure that we can get changes to appear on the screen. So inside my client directory, I'll find the source folder and then the app.js file. Inside of here, we've got the H1 title of Welcome to React. Let's just change that text in there to something like fib calculator. I'll then save the file. We'll then flip back over to our terminal. I'll do a git status and verify that the change is there. Yep, it is. We'll do an add, a commit, and then of course a push origin master. And that'll push those changes up to GitHub. Now, the entire flow of making changes on a branch and then merging a pull request and then only deploying those changes can absolutely still be used with this multi-container deployment. In other words, that entire kind of development workflow that we went through with that single container deployment, totally applicable here as well. But I think that we've seen enough examples of that. So we're just kind of short-circuiting the process more or less and doing a deployment directly to master, where it will then be built and deployed off to Elastic Beanstalk. So let's take another quick pause. I'll let the deployment go through, and then we'll catch up in the next section and just make sure that all those changes, or I guess that one change that we made, shows up on the title of our application. So quick pause, and I'll see you in just a second. In the last section, we made a very small change to our application and then redeployed it again. As usual, went up to Travis CI, that built our images, pushed them over to Docker Hub, and then pushed our entire project over to Elastic Beanstalk. Elastic Beanstalk then saw the updated docker run.aws.json file, pulled down the new images, and launched them as new containers for our application. So now if we revisit our link, we'll see Fib Calculator appear as the title at the very top. Cool, so that's pretty much it. Well, we've looked through at everything we need to know about single container deployments and multi-container deployments on Elastic Beanstalk. Now, before we move on, one quick reminder here, it's extremely important for you to close down all the resources that we used during this section, unless you very specifically want to keep them around. So one last quick break. In the next section, we're going to walk through the process together of shutting down all the resources that we just created. In this section, we're going to walk through the process of shutting down the 3 different resources that we created while we deployed our multi-Docker application. So as a quick reminder, we got a couple things to shut down here. Let's see, here we go. Good enough diagram right here. So we need to shut down the Elastic Beanstalk environment, the RDS instance, and the EC instance as well. We do not strictly have to shut down or close off the security group that we had created. There's no billing associated with creating a security group, but we'll walk through the process of deleting it anyways, just in case you don't want to have any stray security groups running around your application. So let's get to it. First thing we're going to clean up is our Elastic Beanstalk instance. So on Services tab, I'll go back to Elastic Beanstalk. I'll then find the multi-Docker environment, or excuse me, application. And on the right-hand side, I'll click on Actions and then Delete Application, and then click on the Delete button. So that's going to start the process of deleting the application. It's going to appear that nothing is happening for a minute or two, but you can refresh the page a couple of times, and eventually you're going to see that it says, okay, we're closing things down. And in fact, if you click into the application itself, you'll probably even see the events right here that say, okay, it's terminating the environment. All right, next up is RDS, so our Postgres database. I'll again go to Services and then search for RDS. We can then go to DB Instances, either right here in the middle or the Instances button on the left-hand side. We can then click on, don't want to click on that. We'll click on the little check mark right there, and then we can go to Instance Actions and Delete. So we'll delete this. We do not want to create a final snapshot because there's no data for us to really save here. So I'll click on No. We'll hit I acknowledge that we're not making any backups of this thing, and then I'll enter in delete me. And then finally I'll click on delete at the bottom right. And then we see that is deleting. And at the very last one, we'll look up Elasticache right here. I'll go to the Redis tab on the left-hand side. And then again, I'll click on the little, checkbox right there. All these UIs look, it's very subtly different. It's always kind of funny. Anyways, click on the checkbox and then hit the delete button at the top. And yes, we want to delete this cluster. Okay, that's good. And then finally, we're going to clean up the security group that we had created on the VPC. So I'll look at VPC. And then on the left-hand side, we'll scroll on down to Security Groups. I'll select Multi-Docker, Multi-Docker Env, and the RDS launch wizard right here as well. Now, with these security groups, this is the only location where you can very easily mess up other services that might be running on your account. So please triple check and make sure you're deleting multi-Docker, and the RDS launch wizard. So I'm going to make sure I select all three of those, and then I'll do security group actions at the top, and I'll delete those security groups. And again, please triple check to make sure you've got the correct ones selected here. And I'll click on Yes, Delete. Now, just in case you see this right here, you might see one or two on here that say, hey, we can't actually do that. So if you see that around, the first one, multi-Docker env right there, or multi-Docker, the bottom one right here, that's totally okay. It means that these are tied to existing Elastic Beanstalk or other existing services that you already have. So you might have to wait a couple minutes and then come back to this page and try deleting them again, because we are in the process of deleting some other resources that are still using these groups. So for me, I'm just going to hit OK, and I'll come back to this later on and attempt to delete these later. Now, as a quick reminder, if you don't delete these, it's totally fine. You don't get billed for this at all, no billing whatsoever. They can sit in your account for all time and nothing bad is going to happen. Now, the very last thing that you might want to clean up is on the IAM dashboard. We can clean up our deploy keys that we had generated. So on IAM, I'll find my users tab on the left-hand side, and then I'll delete the user that I'd created. So here's multi-Docker deployer right here. And I'll go ahead and delete that user. So eventually this thing's gonna, there we go, finally. So you'll notice that it says that these things, or deleting this might affect running systems. That's totally okay for us. We definitely want to delete this thing. So I'll check the box over there and then click on Yes, Delete. Okay, so that's pretty much it. That is the cleanup. So I hope that you enjoyed putting together this multi-container application, but there's still a lot for us to do and a lot to learn. So let's take a quick pause right here and continue and keep going in the next section. All right, my friends, we've got a whole bunch of experience with Docker under our belts. So now it's time to move on to the world of Kubernetes. In this section, we're going to start doing a little introduction to the world of Kubernetes, first beginning by answering two very important questions. First off, what is Kubernetes? Secondly, why would we ever want to use it? Now we're going to try to answer both these questions at the same time inside this section, so let's get to it. All right, so to begin, I want you to think back to the Elastic Beanstalk application that we just put together. Inside that application, we had 4 different containers running at the same exact time. We had Nginx, which was forwarding traffic to our server and our client, and then behind the scenes, we kind of had that worker process running as well. And of course, we had a copy of Redis and Postgres running as well, but those weren't really containers that were running with the rest of all of our other containers as well. They were outside services. Now, I want to think about this application, and I want to ask you a very simple question. How would we scale up this application? In other words, if we started getting a lot of traffic and we started having a lot of different users starting to enter in different numbers to calculate the Fibonacci sequence for, how would we kind of respond to that? Well, if I had to take a guess, I would say that it would probably be this worker container over here that was doing the absolute brunt of all the work inside of our application. In other words, this worker process was using an algorithm for calculating that Fibonacci value that was very inefficient. And we very purposefully left it kind of inefficient just to see what would happen if it took a long time for that particular container to get some work done. And so if we started having a lot of users making use of our application, the most critical part to make sure that this thing was working correctly, or the entire application was working correctly, would have been this worker container over here. Now, ideally, what would have been really nice is if we had some way to easily spin up multiple processes or multiple containers of that worker image. And so if we had like 3 users come into our application at the exact same time, it would have been great if we had 3 different workers, one of each could have been used to create or to calculate a different Fibonacci value. However, this would have been rather challenging to do in the world of Elastic Beanstalk. You see, in order to scale an application by default with Elastic Beanstalk, here's what actually happens behind the scenes. So this is the typical scaling strategy for Elastic Beanstalk. Rather than creating more copies of a single container, Elastic Beanstalk looks at that docker run.aws.json file, and it spins up additional copies of the entire set of containers. In other words, we can kind of imagine that to scale up our application, Elastic Beanstalk would have created maybe 2, 3, 4, 5 different sets of all of our containers. Now, unfortunately, we don't really have a lot of control over what each of these different groups of containers are doing. In other words, on each of these different groups of containers, we got an additional copy of Nginx, an additional copy of the server, and an additional copy of the client. But at the end of the day, chances are that the Nginx or the client or the server images or containers that we were running were not going to be really the limiting factor of performance inside of our application. Like we just discussed, it was the worker container that was the limiting factor. And so it would have been way more ideal to scale our application if we had the opportunity to do something a little bit more like this. Let me show you. It would have been just great if we had the ability to spin up these additional machines and just create a ton of additional copies of that worker container on each one. Chances are we didn't really need multiple copies of Nginx or the server API or the client. They were all relatively simple, and for the most part, we're just kind of serving up flat files or responding to very simple API requests. It was only the worker container that was doing some major computational work inside of our application. And so it probably would have been ideal if we could have done something like this instead. So, as you might imagine, this is the type of approach that Kubernetes would allow us to have. If we were making use of Kubernetes, we could have had additional machines running each of our containers, and we could have had a lot of control over what these additional machines were doing or what containers they were running. So let's take a look at a quick diagram of how Kubernetes could have been used to solve this entire scaling issue. So what you see on the screen right here is a diagram of a very simple Kubernetes cluster. A cluster in the world of Kubernetes is the assembly of something called a master and one or more nodes. A node, which is each of these blue boxes right here, are a virtual machine or a physical computer that is going to be used to run some number of different containers. So each of these different virtual machines or physical computers that you see right here can be used to run different sets of containers. I want to be really clear that each of them can run different containers, like different images, or even different numbers. So for example, the node on the far right-hand side over here is running 3 separate containers, and the one in the middle is running just one container. These can be completely different containers. They don't have to be identical. And so in the world of Kubernetes, you can imagine that we could have very easily gotten closer to a kind of scaling flow like this right here. Or maybe we had just one node or one virtual machine that was running Nginx, our server and our client, and then maybe we had a bunch of additional nodes or virtual machines that were running copies of our worker image. Now in the world of Kubernetes, all these different nodes that get created are managed by something called a master. This master down here has a set of different programs running on it that control what each of these different nodes is running at any given time. You and I, as developers, interact with a Kubernetes cluster by reaching out to this master right here. You and I give some set of directions to the master. For example, we might say, hey, please run 5 containers using the client worker image. The master receives that command and then ultimately relays that command to all of these different nodes. Now, outside of our cluster, which is represented by this gray block box right here, we have a load balancer, which will take some amount of outside traffic in the form of network requests and relay all those requests into each of our different nodes. Now, one thing that's going to be a big point of discussion for us is exactly how this node balancer works. And so that's going to be something that we talk about inside of the next many videos on Kubernetes that we're going to go through as well. Okay, so in this section, just a very high-level discussion on Kubernetes and what it is and what it does for us. So at this point, I think we've kind of established that Kubernetes is a system for running many different containers, so different types of containers, different numbers of containers over several different computers or virtual machines. And we would choose to use Kubernetes if we had the need to scale up our application and run multiple different types of containers in different quantities. If we only wanted to have a system where we essentially ran, let's go back way over here. If we ran the same set of containers over and over again, like you see right here, not a lot of good reason to use Kubernetes. Again, we want to use it anytime we expect to have an application that consists of many different types of containers running in different quantities on multiple different computers. All right, so with all that in mind, let's take a quick pause right here and continue in the next section. In the last section, we said that Kubernetes is a system for running many different types of containers over multiple machines, and we choose to use it if we have an application that specifically requires us to run multiple different types of containers. If you are planning on creating an application that would largely just have one type of container inside of it, Kubernetes might not be the best solution for you. Now, in this section, we're going to continue a little bit more by talking about how we use Kubernetes in a development or production environment, and then we're going to start setting up Kubernetes on our local machine. All right. So when we work with Kubernetes, there is a very large distinction between using it in a development environment, as in on your local computer, and in a production environment, where you would expect some outside traffic or users to visit your application. In a development environment, we make use of Kubernetes by using a program called Minikube. Minikube is a command line tool whose sole purpose is going to be to set up a tiny little Kubernetes cluster, like the one you see right here, on your local computer. We'll talk about what Minikube does in just a little bit, but for right now, just understand that it's a program that is used to set up Kubernetes on your local machine. When we start using Kubernetes in a production capacity, we very frequently make use of what are called managed solutions. Managed solutions are references to outside cloud providers such as Google Cloud or Amazon AWS that will set up an entire Kubernetes cluster for you and take care of a lot of very low-level tasks that are required to get everything working the way you expect in a secure fashion. And so if you're making use of Kubernetes on AWS, you would be making use of something called Amazon's Elastic Container Service with Kubernetes, which is abbreviated as EKS. And if you make use of it on Google Cloud, you would be making use of something called Kubernetes Engine, or GKE for short. You always also have the option to set up a Kubernetes cluster on your own as a sort of do-it-yourself option. And so you do not have to use these managed solutions that set up everything for you. But when you're first getting started with Kubernetes, it's without a doubt far easier to go with one of these managed solutions until you actually really have a deep understanding of Kubernetes and how it all works together. All right, so the big takeaway in this section is that in a development environment, you and I are going to be making use of something called Minikube. In a production environment, we very frequently make use of these managed solutions. Now we're going to start installing Kubernetes on our local machine in the next section, but before we do, I want to tell you just a little bit more about the setup process. So again, when you're developing locally, you're going to be making use of a program called Minikube. Minikube is going to create a Kubernetes cluster on your local machine. And so behind the scenes, it's essentially going to create a virtual machine whose sole purpose is going to be to run some number of containers. Minikube is a program that is used to create this virtual machine or this single node on your computer. In order to interact with this thing, you and I are going to be using a program called kubectl. kubectl is the program that is used to interact with a Kubernetes cluster in general and manage what all the different nodes are doing and what different containers they are running. So the reason I'm showing you this diagram right here is that we're going to start using a lot of different programs to work with Kubernetes, and it's going to very quickly become a little bit confusing as to what program is doing what. And so as everything moves forward from this point on, I want you to remember that we use kubectl anytime that we want to tell a virtual machine or a node what set of containers it's supposed to be running, or essentially manage what the node is doing. And we use the program Minikube just to create and run a Kubernetes cluster on your local machine. When you start moving to a production environment, this Minikube thing down here falls away. So we only make use of Minikube in a local environment. However, kubectl is going to be a program that you use both locally and production. So even when you start to deploy your application on a Kubernetes cluster off to, say, Google Cloud, we will continue to use kubectl. All right. So here's what we're going to do to set up Kubernetes on our local machine. We're going to first install that kubectl program. We then have to install a virtual machine driver that's going to allow us to create that virtual machine that we mentioned just a second ago on your local computer. Now, I want you to remember back to our entire discussion about Docker a long time ago. You'll recall that we had said that when we installed Docker for Mac or Docker for Windows, it was technically creating a virtual machine at the same time. So that's essentially the same thing that's happening in the world of Kubernetes. The only difference is that Docker for Mac or Docker for Windows install that virtual machine for you and all the associated software with it. In the world of Kubernetes, not quite so automatic. You and I have to install a little bit of software that's going to allow Kubernetes to create, or Minikube in this case, to create a virtual machine for you. Now, to install this virtual machine, we're going to be installing a program in particular called VirtualBox. So after we install kubectl and VirtualBox, we're then going to install Minikube. Again, this is the piece of software that it allows you to create a Kubernetes installation on your local computer. All right, so that's it. Let's take a quick pause right here. When we come back to the next section, we're going to start going through this setup process on Mac OS and Windows. So quick break, and I'll see you in just a minute. In this section, we're going to walk through the setup of Kubernetes on your local machine for the Mac OS operating system. So if you are running Windows, pause the video right now and continue to the next section. All right, so for Mac, here are the series of steps that we're going to go through. And I added one or two inside of here beyond what we saw just a moment ago. Don't worry, it's not a lot of extra work. So to install the majority of all this stuff, we're going to be using a package manager called Homebrew. Chances are that you might already have Homebrew installed, but we're going to first just double check to make sure that you do have it installed. And if you don't, we'll very quickly add it to your machine. So to make sure that Homebrew is installed on your local machine, we'll open up our terminal, and then we'll run which brew. Now, if you see something like this right here, if you see a path to Homebrew, you're good, and you do not need to do the extra step. If you see a message that says like brew command unrecognized or command not found, then you do have to go through this extra download brew step right here. Okay, so if you saw an error message, we're going to go to brew.sh in a new browser tab and download and install Homebrew. It's very quick. So inside of a new browser tab, I'll navigate to brew.sh. I'll find the script right here on the very center. I'll copy the entire thing. I'll flip back over to my terminal and I'll run it. Now, I already have Homebrew installed, so I'm not going to run this command. But after a very quick little setup process, you should see something that says Homebrew is installed. And after that, you should then successfully be able to run which brew and see something like this appear. All right, so now that we've got Homebrew installed, we can move on down to the next step, which is to install the kubectl command line tool. Remember, this is the tool that we're going to use to interact with the Kubernetes master. So to install this, which is a command line tool, all we have to do is run brew install kubectl. Yep, that's it, just that easy. So at my terminal, I'll run brew install kubectl. Now for me, I'm getting a little warning right here because I already have it installed, but for you, you'll very quickly see a bunch of text scroll over the screen, and then something at the bottom should more or less say kubectl has been added. And to verify that it was, we can run which kubectl, and we should see a path like this appear on the screen. So hey, not that bad, right? Okay, for the next step, we're going to install a virtual machine driver called VirtualBox. This is a executable that we're going to download at virtualbox.org. So inside of a new browser tab, I'll navigate to virtualbox.org. On the left-hand side, I'll find the download section. And then I'll find OSX hosts right here. When you click on that link, it's going to automatically start downloading the installer. So go ahead and click on it. It's about 90 megabytes or large or so you'll download it rather quickly. And then once you've downloaded it, pull that thing open inside of a folder explorer, and you should see the virtualbox.dmg file. So we can double click on this thing. That'll pop open a window like this. We're going to find the installer up here on the top left-hand side. Double click it, and it's going to start up a installation wizard. And so as usual, go ahead and hit continue, 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 and you're pretty much going to be good to go. Now, I've already installed VirtualBox, so I'm going to close out of this thing myself. Once you have finished the installation of VirtualBox, which should take just a couple of seconds or so, we'll move on to the last item, or second to last item, which is to install Minikube. And remember, Minikube's job is to make sure that we can use that virtual machine to boot up a single node and configure it to run Kubernetes. So to install Minikube, back at our terminal, we'll run brew cask install Minikube. So back at my terminal, brew cask install Minikube. Now, once again, I already have this program installed, so I'm probably going to see a warning or error message here rather quickly, but you will install this thing, and then you should eventually see something that says, okay, good to go with Minikube. And of course, you can run the command which Minikube and see a path like this appear once you have successfully installed it. All right, so now the very last thing that we're going to do is run a command with Minikube. We're going to execute Minikube start. And when you run this command, it's going to automatically access the copy of VirtualBox that you just downloaded and installed. It's going to use that to set up a virtual machine, and then it will configure that virtual machine to behave as a Kubernetes node. So to start up Minikube, I'll flip back over to my command line, and I'll run Minikube start. Okay, we should see something that says starting VM appear on the screen. Now, this is going to take several minutes, so we're going to pause the video right here, and we'll continue in the next section. By the way, if it appears that this thing is not progressing, if it feels like it's just completely stuck, you can exit out of the start process with a Control-C, and then start it back up again with another Minikube start. So I'll leave it right here, I'll let this command finish up, and then I'll see you in the next section. In the last couple of sections, we went through the setup process on Kubernetes on Mac OS and Windows. To make sure that everything is working as we expect now, I'm going to open up my terminal and run Minikube status. When I do so, I should see Minikube running, cluster running, and kubectl correctly configured. I'm also going to run the command kubectl cluster-info, like so. And I should see a message like this right here appear. If you see any warning or any error message, it means that something went wrong during the setup process. And you will want to flip over to the QA section on this video and go through a little bit of troubleshooting steps to get everything fixed up. Okay, so now that everything is up and running, we're going to set ourselves a little short-term goal. So we're going to say that as a short-term goal, we want to take the multi-client image that we had put together over the last couple of sections and get it up and running on our Kubernetes cluster that is now locally created on your machine by Minikube, running as a container. So that's the goal. Now, to just say this as a goal without giving any kind of directions or path to get to it is kind of hard. So I'm going to show you a sequence of diagrams that are going to give you a good idea of how to transfer some of your existing knowledge in the area of Docker Compose over to all this Kubernetes stuff. All right, so here we go. We've put together several Docker Compose files throughout this course. And when we were working on the multi-container project, we ended up with a Docker file that had a couple of different services inside of it. And there's a couple of observations I want to make about the Docker Compose files that we've created throughout this course. The first observation I want to make is that in these Docker Compose files, every entry, or in other words, each of these different services that we created, can optionally use Docker Compose to build the image. And we did that with Nginx, with Worker, and the client. Remember, we specified the build section that provided the path to a context and a Docker file as well. The next observation I have is that each of the entries inside of here represents specifically a container we wanted to create. We were only creating containers through Docker Compose. We did not create any other type of software or program or anything like that. It was specifically containers that were being created inside of our Docker Compose file. Now that might sound like a weird thing to observe, but let's just hold on for that for right now. Now, the last observation I have is that every entry inside the Docker Compose file also optionally defined some networking requirements. In other words, it set up all that port mapping, right? It set up a outside port on our local machine to a port inside one of our containers, as was the case for, say, the Nginx image. Okay, so we got these three observations right here. Now I want to take these observations and kind of map their equivalents into the Kubernetes world. And so this is going to allow you to translate some of your existing Docker Compose knowledge into the Kubernetes world. Okay, here we go. So first off, each entry that we put inside of that Docker Compose file optionally allowed us to build an image. So in the Kubernetes world, we don't get any benefit like that. With Kubernetes, we are expected to come with all of our images already built. So Kubernetes has no build pipeline. There is no build process. If you're going to make use of Kubernetes, the expectation is that during some outside step, you're going to build all of your different images and have them ready to go, ready for deployment onto your Kubernetes cluster. Now, the next big observation was that each entry inside of our Docker Compose file represented a container that we wanted to create. With Kubernetes, things are just a little bit different. With Kubernetes, we do not have a single config file. Instead, we're going to end up with multiple configuration files. Each of these different configuration files that we're going to put together are going to attempt to create a different object. An object is not necessarily going to be a container. Now, you might be wondering, well, what would we ever create when we're talking about these container things than a container? Well, we'll take a look at what it means to create an object in just a second. But for right now, just understand that we use multiple configuration files to create different objects that are going to be in use inside of our Kubernetes application. And the final thing I want to mention, so we had said that each entry inside of the Docker Compose file defined the different networking requirements. So in the Kubernetes world, we have to manually set up a vast majority of all of our networking. So remember, in Docker Compose, if we created all of these different containers inside of a single Docker Compose file, we could very easily connect to other containers. In addition, if we wanted to do any port mapping, it was as easy as adding in a little entry to the Docker Compose file. So in the Kubernetes world, the process of kind of joining together two containers with networking or exposing a port on a container to the outside world is a far more involved process. And a vast majority of the work that we do throughout the rest of this course is going to be all focused 100% on some of these networking topics. That's going to be one of the biggest things that we discuss. Okay, so with all these kind of mappings over in mind, I now want to think about how we're going to essentially treat each of these items as we think about our current goal of getting the multi-client image working on Kubernetes. All right, so I put a final column into this diagram, and these are going to be the steps that you and I are going to go through to make sure that we are able to get our simple container up and running. So when we think about Kubernetes expecting all images to already be built, that means that you and I are going to have to make sure that our image, specifically the multi-client image, is already built and pushed up to Docker Hub. So we're just going to confirm that that is the case. And you'll recall that through the last application that we worked on, we spent a tremendous amount of time making sure that our images were being pushed up to Docker Hub. So our images should already be there. We're just going to make sure that that is the case. Next up, with Kubernetes, we make one config file per object we want to create. So that means that we're definitely going to make one config file to create our container. Now we're going to go into great detail on this right here because technically we're not going to be making our container per se. We're going to be making something else slightly different. But again, we'll go into that in great detail. Now finally, with Kubernetes, we have to set up all that networking manually. So you and I are going to make an additional configuration file to set up some networking between our container and essentially the outside world. Or in other words, remember, with our multi-client image, we were starting up an Nginx server and serving up some production React files. And so if we want to be able to access that container from within our web browser, we're going to have to do a little bit of networking setup with Kubernetes. So in total, we need to make sure our image is on Docker Hub. We need to make one config file to create our container, or something that's going to essentially represent or contain the container. Again, we'll talk about that in great detail. And then we'll make a second config file to set up some networking and make sure that our container created during this step is accessible from our web browser. So quick pause. We're going to come back to the next section and we'll get started on step number 1. So I'll see you in just a minute. In the last section, we spoke about the series of steps that we're going to go through to get our first container up and running on Kubernetes. So the first thing we're going to do is double check Docker Hub and just make sure that our image is up there for the multi-client image. All right, so to get started, I'm going to open up a new browser tab and I'll navigate to hub.docker.com. And once over here, I'll look at my list of repositories and just verify, yep, my image is up here, Stephen Grider /multi-client. This is the repository that contains the image that we want to create a new container out of on our local Kubernetes cluster. Okay, that was easy enough. So I'm going to close that tab. And we're now going to move on to our second task, which is to make one config file to create our container. Now, to make this config file, we're going to create a new project directory. We're going to open up our code editor inside that project directory, and then we're going to start writing a little bit of configuration into it. All right, so I'm going to flip on over to my terminal. You'll notice that I'm back inside of a workspace directory of sorts, so I'm no longer inside of that complex folder that we had been working in previously. Out here, I'm going to make a new folder called Simple K8s. The term K8s is a little abbreviation for the word Kubernetes, and you'll very frequently see the word K8s in place of Kubernetes in a lot of documentation. The 8 in there is meant to represent the 8 letters between K and S in the word Kubernetes. Okay, so I'm going to make that directory. I'll then change into it eventually. There we go. And then I'm going to start up my code editor inside that directory. All right, there we go. So now inside of here, we're going to make a configuration file. And remember, the ultimate goal of this file is to create our container inside of our local Kubernetes cluster. So inside my code editor, I'm going to make a new file called client-pod.yaml. And then inside of here, we're going to list out a little bit of configuration to create our container. Now, I'll be completely honest with you. I want to be like as transparent as I possibly can. These first dozen or half dozen videos on the topic of Kubernetes, this is the 5th time that I've gone through and recorded all this stuff. So I've recorded 4 times already and deleted everything because I just wasn't happy with it. So in this try, or this run through of recording this stuff, we're going to do things just a little bit differently. We're going to write out all the configuration inside this file, and we're going to write out all the configuration inside that second configuration file as well. And then once you see all this configuration in front of you, we're then going to do a real big discussion and talk about exactly what every line of this configuration means. Now, like I said, recorded this stuff like 4 times, and I'm convinced that writing stuff out is probably the best way to expose you to this. So the good news is we're going to learn exactly what's going on inside these 2 configuration files. The bad news is that you and I are going to do a pretty good amount of typing right now. So as usual, I got to ask you, please triple check your spacing, triple check your spelling, make sure you got everything dead accurate the same as I. Otherwise, you're going to run into a little bit of issues down the road. Okay, so let's get to it. Inside of here, I'm going to first type out API version :v1. I'll do kind pod. I'll do metadata. And then I'll do an indent and say name is client-pod. I'll say labels. And then I'll indent another line and do component : web. Then I'm going to go all the way back out. So no more indentation. I'll say spec containers, and then I'll do a dash to indicate an entry inside of an array. I'll say name client, image of your Docker ID, so Stephen Grider for me, / multi-client like so. Now remember, when we put in this image name right here, that is assuming that our image is up on Docker Hub. If your image, for whatever reason, for multi-client is not on Docker Hub, you can always make use of my image name, which is, or excuse me, my Docker ID, which is Stephen Grider. I'll then list off my ports that I want to open up for connecting to from the outside world, just as we did before over inside of our Docker Compose file. I'm going to have a single entry here, and I'll say container port is 3000, like so. Okay, so that's our first configuration file. Now, again, I gotta ask you, please, I'm begging you, triple check your indentation, triple check your spelling on what you have. And once you're happy, we're going to create one other configuration file that's gonna do a little bit of networking setup for us and make sure that the container that we're creating with the first configuration file will be exposed or available to the outside world. So inside my code editor, I'm gonna make another file. I'm going to call this one client-node-port.yaml. Okay, and then inside of here, we're just going to do a little bit more typing, and then we'll talk about what all this stuff is doing in more detail than you could ever possibly imagine. It will be great. Okay, so inside the new file, we'll say API version is v1. I'll say kind is service. We'll do metadata. I'll give a name of client-node-port. Then I'm going to unindent, so I'm all the way back out to the left-hand side, and I'll say spec with a type of node port. We'll do a ports array, so I'll do an entry in the array indicated by this little dash right here, and I'll say port is 3050. I'll do a target port of 3000, and I'll say node port of 31515, like so. And then finally, I'm going to unindent, so I'm back online with type and ports, and then I'll say selector is component:web, and I'll save the file. Now again, I gotta ask you, please, 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 triple check your spelling inside of here, triple check the indentation. Remember, inside of a YAML file, if your indentation is not perfect, the file will be misinterpreted and nothing is gonna work the way you expect. Okay, so that's all the typing we gotta do. Now we're gonna take a quick pause right here. We're gonna come back to the next section and we're gonna go over both these files in just tremendous detail. So quick pause and I'll see you in just a minute. In the last section, we put together a ton of configuration inside of 2 different files. In this section, we're going to start to pull these 2 files apart line by line. We're going to first focus on the first 2 lines in each file, so specifically API version v1 and kind pod. You'll notice that the other file has the very similar same 2 lines at the top, but in the second file, we have kind of service. So again, we're going to focus on these 2 lines to get started. And just so you know, we're going to first, between the 2 of them, we're going to first focus on exactly what kind is referring to. All right. So just as we discussed a couple moments ago, we had said that with Docker Compose, we had created a configuration file to describe the different containers that we want to create. And we had done something very similarly over with Elastic Beanstalk as well. Now with Kubernetes, we do make these config files to make containers, but we had kind of honed in on that definition with this diagram over here and said that when we make a config file with Kubernetes, we're not quite making a container, we're kind of making something else slightly different. We're making something called an object. And so I first want to focus on exactly what an object is and help you get an understanding of what an object is. All right, so back over here. Okay. So we've written 2 configuration files. We're going to eventually take these 2 configuration files we put together and feed them into the kubectl command line tool that we installed a couple of videos ago. Remember, that is the kubectl command that we had ran at our terminal just a moment ago. Just a second ago, we ran cluster info, like so. So eventually, we're going to take these 2 configuration files and pass them into this command line tool. When we pass them in, kubectl is going to interpret both those files and create 2 objects out of each file. So the config files that we write are going to be used to create objects in general. The term object is a reference to a thing that exists inside of our Kubernetes cluster. And so we don't specifically say that we are making objects quite so much. In reality, we are making specific types of objects. And in this diagram right here, I'm showing you a couple of sample object types. So an example of an object would be a stateful set. Another example of an object would be a replica controller. These are all things that we can create inside of our Kubernetes cluster that have very specific purposes to make our application work the way we expect. 2 other examples of object types that we're going to very frequently be using is a pod and a service. And you might have noticed that inside of our 2 configuration files, we have the word pod next to kind, and we have the word service next to kind as well. So the first thing to understand here is that the kind entry inside of all the configuration files that you and I are going to write is meant to represent or indicate the type of object that we want to make. So in our client-pod.yaml file, we are making an object of type pod because that's what we entered in for the kind property. In the client node port file, we are making an object of type service because that's what we represented for the kind property over here as well. Now you might be curious, what exactly is an object? What are they used for? Well, like I just said, they're essentially things that are going to be created inside of our Kubernetes cluster to get our application to work the way we might expect. And so, for example, every object that we're going to create, or every type of object, has a slightly different purpose. Some objects are used to run a container, as is the case with a pod. A pod is used to run a container. Other types of objects might monitor a container. Other types of objects, such as a service, are going to set up some kind of networking. And so we made an object of type service to set up some networking inside of our Kubernetes cluster. Okay, so that's kind of a brief overview on exactly what what kind service and kind pod mean. Now I want to tell you a little bit more about API version v1 on both these files. All right, let's see, over here we go. So when we specify the API version at the very top of the file, that essentially scopes or limits the types of objects that we can specify that we want to create with any given configuration file. So inside of both of our configuration files, we specified an API version of v1. That essentially opens up access to us to a predefined set of different object types. And so we have access, or our configuration file in both cases, because we are designating API version v1, we can create an object of type component status, or config map, or endpoints, or event, or namespace, or pod, or any of another of other object types that I'm not reflecting inside this diagram. If we had used a different API version, such as API version :app/v1, we get access to a different set of object types. And so if we had put in app/v1, we could have created an object of type controller revision, or an object of type stateful set. Now in practice, the API version flag is just a little bit annoying, I'll be honest with you. What you're usually going to do with any configuration file you put together is you're first going to decide on what kind of object or what type of object you want to create. You'll then figure out what API group that object type belongs to, and then you're just going to go look up that API version and stick it into your configuration file. So in other words, I knew that we had wanted to create something to create a container inside of our Kubernetes application, and so based on my knowledge, I knew that we needed to create a pod. So what I did was I looked up a document that said, hey, if you want to make a pod, you have to be using the pool of object types designated in API version v1. And so that's why I put down API version v1 inside my config file. It's because ahead of time, I knew that I had wanted to make a pod. So the reason that I say that this API version is a little bit annoying is that it's mostly a reactionary feature, and you just got to go do a little bit of reference to figure out what you should be specifying. Now, throughout this course, I'm going to be telling you in great detail about exactly what API version we're going to be specifying for every config file we put together. So you don't really need to worry about memorizing these things that much throughout this course. Okay, so at this point, we've discussed what API version means. We've also discussed what kind means, although we haven't really discussed what a pod is or really discussed what a service is. So let's take a quick pause right here. We're going to come back to the next section and expand on exactly what a pod is. So I'll see you in just a minute. In the last section, we expanded upon the API version and kind properties inside of both our config files. We're now going to start to talk about what a pod is, and then we'll very quickly talk about what a service is as well. Okay, so a pod. All right, quick diagram. Let's find it here. Here we go. All right, so just a moment ago when we went through that setup process to install Minikube and kubectl on your local machine, remember we installed Minikube and then we ran that command minikube start. When we ran that command, it created a new virtual machine on your computer. We refer to that virtual machine that is now running on your computer as a node. That node is going to be used by Kubernetes to run some number of different objects. Now, one of the most basic objects that you and I are going to create throughout this course is something that we refer to as a pod. And so when we start to load up this configuration file right here into kubectl, we're going to push into kubectl, and it's going to create a pod inside of that virtual machine that is running on your computer. And remember, we refer to that thing as a node. Now, the pod itself is essentially a grouping of containers with a very common purpose. Now, you might be wondering why we're making a pod that has a grouping of containers, when just a moment ago I had told you, oh yeah, we want to get something running as a container. Well, in the Kubernetes world, there is no such thing as just creating a container on a cluster. Back with Elastic Beanstalk, back with Docker Compose, we were creating containers willy-nilly all day, no issue whatsoever. But in the world of Kubernetes, we do not have the ability to just run one naked single container by itself with no associated overhead. The smallest thing that you and I can deploy is a pod. So we're always going to be deploying containers within a pod. That's the smallest thing that we can deploy to run a single container. Now you might be wondering, why is that? Why would we make a pod at all? Well, let's talk about why we would make a pod. So the requirement of a pod is that we must run one or more containers inside of it. Now, when I say one or more containers, you might very quickly think back to the multi-container application that we put together. Let's pull up a quick diagram of that thing. I've got one around here somewhere. Here we go. So back on the multi-container application we put together, we had our Elastic Beanstalk, and it was running multiple different containers all in this single little grouping. And so when I tell you that inside of a pod, we will run one or more containers, you might be thinking, oh, okay, that's it, like game over. We're going to take our 4 containers or 4 images right here and create 4 of these containers inside of this one single pod. Well, that would definitely be an option, but it's not what a pod is meant to do. The purpose of a pod is meant to the purpose of a pod is to allow the grouping of containers with a very similar purpose, or containers that absolutely positively must be deployed together and must be running together in order for our application to work correctly. Now, even when I say that, you might be thinking, well, Stephen, back here on this application, we had to have the Express server deployed with Nginx up here to serve the React application or respond to API calls. So you might be thinking, yeah, this thing had to have all these different containers put together to work correctly. Well, actually, that's not 100% accurate. You see, back on this application, if our worker container over here crashed for any reason, the rest of the application would still function a-okay. If the Nginx React server right here failed, well, everything would still pretty much work correctly. If the Express API closed down, well, everything else would at least kind of still function. In other words, if we take away the vast majority of these containers, the rest of the containers inside the group are still going to generally function the way we expect. It's definitely not ideal, but they would definitely continue to work. Now, in the world of a pod, when we start to group together containers, we are grouping together containers that have a very discrete, very tightly coupled relationship. In other words, these are containers that absolutely have a tight integration and must be executed with each other. So as an example, let's imagine a pod that is running 3 containers that you see right here. This would be a good example of when we would use a pod with multiple containers. So in this example, I've got a Postgres container. So that's running the Postgres database. And then in addition to that, we've got 2 other containers. Now, these are imaginary images that I've listed here. So there is no image called logger that I know of. There probably is, but yeah, I'm just making this thing up. And I don't really know of any image called backup manager. So again, these are 2 imaginary containers that we're just kind of pretending exist. You could pretend that the logger container might need to connect over to Postgres and store some database logs. And maybe this backup manager needs to connect to the Postgres container and do a SQL dump or something like that and make a backup of all the data inside that database. And so again, this would be a very good example of why we would want to use a pod with multiple containers. A logger like this right here is 100% intended to connect to this Postgres container and pull some information out of it. If the Postgres container goes away, the logger 100% worthless. No 2 ways about it, the logger is completely useless at that point in time. And it's the same thing with the backup manager as well. The backup manager might need to reach into this Postgres container and pull out some information to make a database backup. And so the backup manager 100% has a very tight integration, very close relationship with the Postgres container. And again, if that container goes away, the backup manager, no 2 ways about it, 100% worthless. So again, in the world of Kubernetes, we make use of pods as the smallest thing that we can deploy. We cannot deploy individual containers by themselves as we could with Docker Compose or Elastic Beanstalk. Anytime we want to deploy a container in the world of Kubernetes, we have to make use of a pod. A pod can run one or more containers inside of it. Inside this course, you and I are only going to be running one container inside of any given pod, but reasons that you might want to add in more containers is if you have some other containers that have a very, very tight integration with other containers that exist inside the pod. So with all that in mind, if we flip back over to our client pod.yaml file, again, we're specifying a object type of pod inside of here, and hopefully now some of the other configurations inside of here might make a little bit more sense. We are creating a pod that's going to run one container inside of it. We're going to give that container an arbitrary name of client. The name of client right here is, for our purposes, largely going to be related to logging and giving us the ability to reference this running container. But if we were running other containers inside of here as well, we could also use this name property to get some networking or connections between these different containers that are running inside the single pod. The image property, well, I bet you can guess what that is. That's the name of the image or the repository off on Docker Hub that this container is going to be made out of. And then finally, the ports entry on here is, it's kind of like that port mapping stuff that we were doing before. The ports of container port right here is essentially saying that on this container that we're going to create, we want to expose port 3000 to the outside world. Now you might be curious, why are we exposing port 3000 in particular to the outside world? Well, if you recall, back to our multi-client project, here's the source code for multi-client right here. There's the client directory. We had created a Nginx server that runs inside of that container, and it listens on port 3000. So we set up that container port 3000 right here because we're going to eventually want to expose port 3000 to the outside world. So this line, at least right here, is very similar to some of the stuff that we did back inside of our dockerrun.aws.json file with Elastic Beanstalk, and it's also similar to some of the stuff that we did inside of our Docker Compose file as well. This is setting up our port mapping. Now, one thing I want to be really, really clear about is that this is not the full story of port mapping inside the world of Kubernetes. This line of code right here alone is not going to give us access to port 3000 inside of our running container. In order to get that networking set up, that was the entire job of the second configuration file we put together. And so that's going to serve as a nice segue. Let's take a quick break right here. When we come back, we're going to start talking about the purpose of this service object that we put together inside the second file as well. So quick pause and I'll see you in just a minute. In the last section, we went over the majority of our client pod.yaml file. We spoke about what a pod is and what its purpose is. We also spoke about the spec section down here a little bit, but we have not yet spoken very much about this metadata section. Now, very quickly on metadata, the name is pretty much what you would expect. It's going to name the pod that gets created, and this is mostly used for a lot of logging purposes. We're going to see the name of client pod used when we start using kubectl to print out information about our running cluster at the terminal. Now, the other piece of information inside of metadata is labels right here with component web, and that's very tightly coupled to the other config file that we're going to start to discuss right now. So in this section, we're going to focus on the second config file we put together, the one with a kind of service. So let's talk about what's going on inside here. All right, so at this point, we've spoken about the object with type pod. A pod is used anytime we want to run one or more very closely related containers. So we're now going to start talking about a second kind of very commonly used object. The second object type that we're going to discuss, and again, this is a type that we're going to be discussing just so much throughout this course because all this networking stuff is so important to understand. Anyways, second object type, services. We use this object type anytime we want to set up some amount of networking inside of a Kubernetes cluster. So let's take a look at a couple diagrams that are going to give you a better idea of exactly what a service is and how it behaves. Now, the first thing I want you to understand is that in the world of pods, we have basically just pods. That's it. Like, that is the object type. But in the world of services, there are 4 very commonly used subtypes. In fact, there's only 4 subtypes. And so I've listed all the subtypes of the service object type right here. So as a service, we can create a service of type cluster IP, node port, load balancer, and ingress. Inside of our particular file, we specified a object type or a primary object type of service with the kind property up here. And then inside of the spec section, we specified a subtype or a type of service known as a node port. So we are making a node port service. The purpose of a node port service is to expose a container to the outside world, or in other words, to be able to allow you, like you as a developer on your computer, to open up your web browser and access that running container. A node port service is only good for development purposes, and we do not use node port as a service type inside of production environments outside of one or two very specific exceptions. And actually, one of those exceptions is something we're going to cover later on inside this course. Now, you'll notice that on the other service types on here, I'm not putting any notes or anything on here. We are going to talk about the other service types in tremendous detail throughout this course. Again, services and networking is a very important topic to understand. But if I added in those other descriptions right now, it would just be a little bit confusing. So I'm going to leave the other descriptions off. And for right now, we're just going to focus on the node port service type. Okay, so again, node port is something that we use to expose a container to the outside world and essentially allow you and I to access that container inside of our browser. Now, I want to show you a series of diagrams to give you a better idea of what this service is doing for us. So inside this diagram, the overall blue box is our computer. And so at some point in time, you and I are going to want to open up our browser and connect to that multi-client container that is running inside of our pod. That pod and the container inside of it are running on the local Kubernetes node. Remember, this is the VM created by Minikube that is running on your local machine. Now, when we create that service of type node port, it's going to set up a communication layer between the outside world and the container running inside of that pod. You'll notice that there's another box on here called the kube proxy. Every single node or every single member of a Kubernetes cluster that we create has a program on it called the kube proxy. The kube proxy is essentially the one single window to the outside world. So anytime that a request comes into a node, it's going to flow through this thing called the kube proxy. This proxy is going to inspect the request and decide how to route it to different services or different pods that we may have created inside of this node. So right now, I'm only reflecting one service right here, but over time, we might end up with multiple different services. Something like that right there, as messy as that may be. And so when we end up with multiple services inside of a single node, it would be up to kube proxy to make sure that incoming requests are sent off to the appropriate service. Now, when a request comes into the node port service that you and I are going to create, it's going to attempt to take that request and forward it onto port 3000 on our multi-client container that we defined to run inside of our pod. Now, that gives you an idea of the placement of the service here, but that doesn't really kind of describe everything else that's going on inside of here. So what's going on with the three different ports? And what's going on with the selector down here? Let's take a look at another diagram that's going to be slightly more detailed than this one right here, that's going to give you a better idea of those different pieces of configuration and their purpose. Okay, so very similar diagram, just with more detail added in. I just got to fix that thing or I'm going to go crazy. Okay, so on the service, you'll notice I added in kind of a long statement right here. If you look at the client configuration file, you'll notice that at the very bottom is a selector that says component:web. You'll also notice that there's nothing else inside this file that seems to indicate that it should be that this service should be handling network traffic for our pod with a name of client pod. Here's the pod file. It's got a name of client pod. Here's the service file. Nowhere in here do we say client pod. So in other words, there's nothing inside of here that says, I need to send traffic to client pod. There's no declaration like that inside of here. Instead, rather than referring to the service, or excuse me, the pod that we want to have this service direct traffic to, rather than using any naming system, we instead use a system in Kubernetes called the label selector system. So inside of this service file, you'll notice that down at the bottom, we have a selector of component:web. And then over here, back inside of the pod file, we have a metadata labels property of component:web. That's how these two different objects get linked together. When the service first boots up, it's going to say, okay, I need to do some port forwarding. I don't know who I'm supposed to forward this traffic to. it's then going to see its selector property down here, and it's going to say, oh, okay, I'm going to look for any other pod or any other object that is running that has a key value pair of component:web. And if I see any other object running inside this Kubernetes cluster with the label of component:web, I'm going to direct all traffic to these ports on that thing. So the service that we've created and the pod that we created are linked together by the label inside the client pod and the selector inside the service. Now, the one thing that I want to make sure is really clear is that the selector that we've used here of component:web is 100% arbitrary. So we could have just as easily called this thing like tier front end. If we had made that change, we would just need to make sure that the client pod has the same label as well. And so back inside the client pod, we would need to have tier front end as well to make sure that the two are 100% identical and match up perfectly. Now, I am going to undo those changes, and I'm going to go back over to component:web on both configuration files. Okay, so again, when the service boots up, it says I'm going to look at my selector property, and it's going to see that it has a key value pair of component:web. It's then going to reach out in the Kubernetes cluster, and it's going to find every other object that has a label of component:web. And it's going to attempt to expose port 3000 to the outside world, more or less. And so, of course, our pod needs to have the appropriate label of component:web. Okay, so that brings us up to speed on the selector inside the client node port file and the label in the client pod file. Now, the last thing I want to tell you about is the collection of ports right here. We have ports, target port, node port, all these different things. Now, one quick thing I just realized, I put ports right here. That is a little typo. It should be port singular, like so, my mistake. I'll mention that again at the end of this video just to make sure that if you're speeding through this section, you don't miss out on that little fact. Okay, so in the service, we have a port section. This is describing all the different collections of ports that need to be opened up or mapped on the target object. One thing I want to point out here is that the service ports property is an array, and so we could very easily have additional ports that we're trying to be mapped on here as well. So we could do like, I don't know, 9,000 or whatever it might be. Now, something that might seem a little bit weird is the fact that we have 3 different ports inside of here. First thing I want you to notice is that the target port of 3000 is identical to the container port over inside of the pod definition. Now, that's not really a lot of help. Let's just look at a diagram. It's going to explain these different things. All right, I'm wasting time. Here we go. Okay, so inside the node port service, we're exposing those 3 different properties, or we have defined those 3 different properties. Now, the first thing that we're defining inside there is port. Port for you and me is more or less 100% worthless for the application that we are putting together right now. The port property is going to be the port that another pod or another container inside of our application could access in order to get access to the multi-client pod. So this multi-client pod right here, that represents the actual pod that the service is trying to map traffic over to. So we can imagine if there is some other pod inside of our application, like let's say other pod right here, if there's some other pod that needs access to multi-client, it could connect to it through this port designation right here. And so again, for you and I, for the application we're doing right now, this port property is not useful because we do not have any other objects or anything else inside of our Kubernetes cluster that's going to attempt to reach into that multi-client pod. Now, the next property inside there is the target port. So as you might imagine, the target port is the port inside of that pod that we want to open up traffic to. We used a target port of 3000 right here, which indicates that we want to send any incoming traffic into port 3000 inside of this pod. And port 3000 has been mapped up to the multi-client container. Now, the last thing on here is the node port. You'll notice that for the node port, we used a rather large port number. I used 31515. Now, the node port is the one that you and I probably care about the most whenever we make use of a node port type. The node port is the port that you and I inside of our browser are going to access whenever you and I want to actually test out the container running inside that pod. So the node port right here is going to be essentially what you and I type into our browser. So as the URL, we'll do whatever the IP address is, :3, what was it? 31515. So we're going to type in that port into our browser in order to access the multi-client pod. So again, we can kind of ignore the port property for this application we're doing right now. The node port is what gets exposed to the outside world, and the target port is what gets opened up inside of the targeted pod. Now, the last thing I want to mention is that the node port is going to always be a number between 30,000 and 32,767. If you do not specify the node port, so we are not required to specify it, we could actually delete it if we wanted to. If we do not specify that port, one will be randomly assigned to us, and it will be between 30,000 and 32,767 as well. Now the reason, or I should say one of the reasons that you and I do not make use of the node port service in a production environment is because of these funky port mappings. Obviously, when a user goes to something like google.com, they want to go to google.com. They don't want to go to google.com:351515 or whatever, right? Now, again, that's just one reason of many that we do not use a node port in a production environment outside of some very specific exceptions. Okay, so I think that explains just about everything inside of our client pod file and the client node port file as well. So now the last thing we have to do is take these two configuration files and we're going to load them into our Kubernetes cluster through the kubectl command line tool. So quick pause and we'll come back in the next section. In the last section, we finished going through both of our configuration files and we're now ready to load these into our Kubernetes cluster and try to access our running container. So in order to do so, we're going to feed both these configuration files into our cluster through the kubectl command line tool. The command in particular that we're going to run is the apply command. So at the command line, we're going to run kubectl apply -f and then the name of a configuration file, or I should say the path to the configuration file. Now kubectl, again, that's a command line tool that we use to mess around with everything going on inside of our Kubernetes cluster. The apply keyword means that we want to change the configuration of our cluster, and that's actually kind of a very loaded term. Like these words right here, change the current configuration. That's a real loaded term right there, and it's something that we're going to expand upon at great length in just a little bit. We then specify that we want to load in a file that contains all this configuration that we care about. So we're going to add on the -f flag, and then the path to the file is the path to the file. That's pretty much it. So let's try flipping over to our command line, and we're going to run this command 2 times, one time for the client-pod.yaml file, and one time for the client-nodeport.yaml file. So back in my terminal, I'm going to first make sure that I'm inside of my simple k8s directory, which is where I have those two configuration files. I'll then run kubectl apply -f, and let's first load up the client pod. So I'll say client-pod.yaml. I'll hit enter, and then we'll very quickly see that the pod has been configured. Now, what does configured mean? Who knows? That seems a little bit mysterious. So it doesn't really seem to say that the pod was or the container was successfully created. And in fact, this message printed up a little bit too quickly for me to really feel like the container was successfully created. So we might need to do a little bit of a status check here in just a second to make sure that the pod was in fact started up successfully. But before we do, let's apply our other configuration file. So I'll do kubectl apply -f, and then the other file was called client node port. So client-node-port.yaml. And again, I see configured message right here. Now again, in both cases, it seems like these messages appeared pretty quickly, so I don't really know if everything worked the way we would expect. So let's try figuring out how we can print out the status of both these different objects that we just created, and just make sure that they were in fact successfully created. So in order to get the status of any different object that you and I create through a configuration file or any other means, we're going to be making use of the kubectl get command. The get command is going to print out the status of an entire group of object types. So for example, we would say kubectl get pods. In this case, pods is the type of object that we want to get information about. kubectl will look at our Kubernetes cluster, it'll find all the different pods that have been created, and it'll print out the status of every single one. So it's a very easy way to get a kind of high-level look at everything that's going on inside of your cluster. So I'll do kubectl get pods at my terminal, and I'll see that I have one pod created. It has a name of client pod. 1 of 1 right here means that there is one copy of it running, and we need to have one copy running. So the first number right here is the number of pods that are running, and the second number is the number of copies that we want to have. As we start to scale our application, we might want to have multiple copies of the exact same pod running. And so when that happens, you would expect to see one right here change to 2, 3, 4, 5, whatever it might be. We then see that the status is running, so it definitely looks like everything started up a-okay. There have not been any restarts, so if your pod right here crashes for any given reason, it will be automatically restarted, and you would see restarts right there increment by 1. And then age of 1 hour means it's been running for 1 hour. Now, in my case, the thing has not actually been running for 1 hour. I just started up this pod a while ago, and I forgot to close it before running the apply command, but not a big deal. You're going to see a age of like, 1 minute or something like that. Okay, so now we're going to get the status of all the different services that we have created as well. So to get a printout of all of our different services, we're just going to slightly change the kubectl get command. We're going to say that we want to get a printout of all the objects with type service that we have created. So I'll say kubectl get services. And that's going to print out 2 different services. Now, chances are you have 2 services running as well. One might be Kubernetes with a type of cluster IP. If you see that, that's one of the inner workings of Kubernetes, and you can completely ignore that thing. Now, hopefully, you're going to see a second service printed out in here with the name of client node port. Its type will be, of course, node port. It'll have a cluster IP, an external IP, and then a listing of ports and age over here as well. Now, I want you to look very closely at port over here. You'll notice that there's both the port property and the node port property as well. And so as a quick reminder, the first number on there, where's our diagram? Here we go. So the first number on there is the port. That is the port that other pods or other objects would use to access the service that this thing the pod that this service points to. The second number is the node port. And so that is the port that you and I would use to access that service inside of our browser. You will notice that the one port that is not reflected inside of here is the target port. So the service does not report the port that is trying to open up inside the target pod. That's not done for any security issues. It's just done because, like, who cares? Who cares, right? For that print up, you probably don't care about the target port. You probably only care about the port property and the node port. All right, so that's pretty much it. We have now deployed both of these objects, and they are now running on our local cluster. So now the very last thing we have to do is attempt to access our running multi-client project inside of our browser. Now, you might expect, and based on my wording right now, as you might guess, this is not the way we do it. You might expect that we would go to localhost : and then whatever we put in as the node port over here, 31515. Remember, this is the port that we use to access or test out our container inside the browser. So you might think that we go to localhost : 35151 or whatever. I keep mistyping that thing. I'm just gonna do a copy paste. There we go. So of course, when you go there, yeah, nothing works. So what's going on? Well, remember what is going on behind the scenes on your computer right now. Let's pull up a good diagram for this. This one right here, this will do. Let's do this one. Okay, so when we are inside of our browser, when we want to access some container that is running on that Kubernetes node VM created by Minikube, this is not addressed by localhost. In other words, all the ports that exist inside this node VM right here are not available on localhost. In order to access this VM, we need to actually ask Minikube for the IP address that was assigned to this virtual machine when it was created on your computer. So this virtual machine right here that was created on your machine has its own IP address, and you need to visit that IP address in order to access any of the different services, any different pods that are running inside of here. So to access that IP address, we'll flip back over to our command line, and we're going to run minikube IP, and that's going to print out the IP address of that virtual machine. So at any point in time, forever, inside this course and your own applications, anytime that you want to access some application that is running inside of Minikube or inside of that virtual machine, you are not going to use localhost. Just forget it. There is no localhost, period. No localhost. Anytime that you want to access a service or a container or a pod or whatever it might be that is running on your virtual machine or inside of your Kubernetes cluster, when you're running in development mode, you're going to run minikube IP, and you're going to use this IP address right here. So hopefully I made that memorable enough. You're not going to use localhost. That's pretty much it. So we're going to copy this right here. I'm going to go back over to my browser. I'm going to put in that IP, and then we're going to specifically access the port, the node port that we set up on that thing. So I'll say :31515, and I'm going to put that over inside my command line just to make sure it's really clear. Yeah, there's a colon on there. Now remember, your IP address might be very different than mine, so do not go to my IP address. Go to whatever IP you see printed out at your terminal. All right, so we're going to go there, and lo and behold, we see our application appear on the page. Now, of course, if you open up your terminal, you're going to see a couple error messages because this thing is not able to access the Express API. Well, that's totally fine. It's just because we have not actually set up that API inside of our Kubernetes cluster yet. Okay, so that's pretty much it. We have gone through the entire process of creating two different objects, both a pod and a service. We understand the differences between the two, and we understand that we have to create a service if we want to access anything inside of our running pod. Remember, by default, Kubernetes is far more restricted with all of its networking stuff than anything we ever did with Docker Compose or with Elastic Beanstalk. With Kubernetes, we have to be very, very explicit about all the networking that we want to set up. And we do all the networking setup by the creation of these different service things. So that's pretty much it. That's the basics of Kubernetes. So let's take a quick pause right here, and we're going to start looking at some more complex stuff in the next section. In the last section, we went through a very long-winded demonstration of exactly what was happening inside of our local node. Now, at this point in time, our understanding of the Kubernetes architecture is kind of limited to this diagram right here and a couple of discussions about, some networking stuff and nodes and blah, blah, blah. Very simple, straightforward stuff. So in this section, I want to change that in a big way. We're going to walk through the process of exactly what happened when we fed that configuration file into kubectl and get a better understanding of what is kind of happening behind the scenes. Now, before I do, I want to give you a very quick demonstration at my command line, and I want to show you something rather interesting, okay? So I'm going to flip over to my command line. Now, some of these commands you are not going to be able to issue successfully. If you run the commands I'm about to run, you will see an error message. So please don't try to run these, just follow along visually for a second. I will show you how you can run these commands in just a moment as well. But for right now, just watch. Okay, so I'm going to first start off by doing a kubectl get pods. That's going to list out the current status of our running pod right here. And as you can see, it currently has restarts of 0 and an age of 1 hour. Now I want to do something very interesting. I'm going to execute a command. You're going to see a Docker PS right here, and you're going to see that I'm running a tremendous number of containers right now. One of the containers I am running is the multi-client image. So this is the container that is running inside that pod right now. Now I'm going to take that container ID. Again, this is a container that's running inside that pod. I'm going to take the ID, and I'll do a Docker kill with that ID. So this is going to completely kill that running container inside of that pod. So that's it. It is done. It's gone. Now I'm going to do a Docker PS again. If I scroll all the way back up, you're going to very quickly see that it looks like, hey, wait a minute, it's still there. There's Stephen Grider multi-client. That is the container running inside that pod. But you'll notice that the thing was only created 2 seconds ago. If I also run the command kubectl get pods, you'll notice that there is now 1 restart reflected inside of here as well. And so the thing that I wanted to demo to you here very quickly, that's going to kind of play into the diagram that we're going to look at in just a second, is that it appears that if we manually delete, or if one of those containers inside that pod crashes, it appears that it automatically gets restarted for us, for free. So with that in mind, we're now going to look at a rather complex diagram. We're going to walk through the process of what happened when we deployed, or applied, I should say, these 2 configuration files. Now, just a quick disclaimer, this is going to be a rather long video as we go through this discussion, so I don't know, pause it at some point and take a break if you feel like it. I don't know. Okay, so this diagram, super boring, not enough detail. I want to look at this right here. All right, so this is a little bit more realistic diagram. We're going to walk through this thing step by step and see what happens when we deploy one of those files. Now, on the right-hand side, you'll notice that I'm reflecting 3 separate nodes. Remember, a node in the world of Kubernetes is a computer, or essentially a physical computer or a virtual machine that is going to run some number of objects that we create inside of our cluster. You'll notice down here at the bottom center, I have something labeled called the master. On the left-hand side over here, we've got a deployment file. So the deployment file is essentially identical to the 2 files that we just put together that create a pod or a service. And then finally, up here on the top left-hand side, I have the Docker Hub that lists a couple of the different images that we have created throughout this course. So let's walk through a series of actions now. We're going to start off with our deployment file down here. Now we're going to imagine that rather than creating a single instance of the multi-client image or multi-client container, maybe we have a deployment file that instead says that it wants to create 4 copies using the multi-worker image. So we're just going to imagine, for the sake of discussion, that we slightly changed our deployment file. We're then going to imagine that we take this file and we feed it into the kubectl apply command. Remember, that is the command that we use to load up the 2 files that we had previously put together, the client pod and client node port. So when we run this command right here, the file is taken and it is passed off to something called the master. Now on the master, there is a variety of different programs, 3 or 4 in total, that control your entire Kubernetes cluster. So there are 4 programs in total, but you and I are just going to kind of imagine for right now that there's just one program called the kube API server. Again, 4 programs, we're just going to kind of consolidate it all down to 1. The kube API server program is 100% responsible for monitoring the current status of all the different nodes inside of your cluster and making sure that they are essentially doing the correct thing. So we're going to imagine we take this deployment file and pass it into the master. Kube API server is going to see this new file. It's going to read the configuration file and it's going to interpret it in some fashion. The master then has a little kind of notepad of sorts that records all of its responsibilities, or essentially all the things that you and I have told it to do in the form of these deployment files. So when we feed in the deployment file, Kube API server is going to look at that file and it's going to see, oh, all right, the developer wants us to run 4 copies of multi-worker. And so Kube API server is going to update its little list of responsibilities and say, okay, I need to be running an image called multi-worker. I need to be running 4 copies of it, and right now I am running 0 copies. So Kube API server is going to update its little list of responsibilities right here, and it's going to say, oh boy, I need to be running 4 copies, and I'm currently running 0. Well, that's definitely bad news. So what's going to happen? Kube API server is then going to reach out to the 3 different nodes that are running. And it's going to say to each of these, hey, people, look, we got a big problem. We need to be running 4 copies of multi-worker, but right now we are running 0. So you 3 nodes, I want you to start up some number of copies of multi-worker. It's going to say to the first node down here, I want you to start up 2 copies of multi-worker. I want you to start up 1 copy. And I want you to start up 1 copy as well. Now, inside of each of these nodes, there is a copy of Docker running. That's right, a copy of Docker running inside of each of these virtual machines. That is true of the virtual machine that is running on your computer right now with Minikube as well. So technically, on your computer, you now have 2 copies of Docker running. Both the copy created by Docker for Windows or Docker for Mac, and the copy that is running inside of that single node that has been created by Minikube. Now, when the master down here says you need to create 2 copies of multi-worker, 1 copy, the copy of Docker inside of each of these different nodes is going to spring to action. It's going to reach out to Docker Hub, and it's going to find the multi-worker image right here. It's going to copy or download that image and store it on some local image cache inside each of these nodes. Now, the thing to remember here is that each of these copies of Docker are 100% kind of autonomous, not connected. So they're all going to reach out and grab that, oops, not multi-client, but multi-worker image. And so you can kind of imagine that we get the multi-worker image inside of each of these nodes like so. then each node is going to use that image to create a new container out of it. So we're going to create one copy of multi-worker as a container. We're going to make another copy down here. And then we had said that this last node would make 2 copies of the container like so. Now remember, technically each of these containers are being ran inside of that pod interface, or that pod object thing. But for the sake of this diagram, we're just going to say, yeah, the containers basically exist, but they are inside of pods nonetheless. So now that each of these have started up a copy of multi-worker, the master is going to reach back out to each one of these nodes, and it's going to say, okay, need a status update. How are things going? It's going to look at the first node. It's going to see, okay, 1 copy. It's going to look at the second node. Okay, 1 copy. It's going to look at the third node. Great, 2 copies. So in total, it now has 4 copies of multi-worker running. And so it goes back to its little list of responsibilities of sorts over here, and it's going to say, I now have 4 copies of multi-worker running. And at that point, the master says, all right, that's pretty much it. I'm going to sit back and relax because I've done my job. So that's pretty much the entire flow. Now, the last thing I want to mention is what happened when I did that Docker PS command over here. And then you'll recall I killed that running container with Docker kill on this ID right here. So what exactly happened there? Well, just a second ago when I said, oh yeah, the master sits back and relax, well, that's not what really happens. You see, the master is always continuously polling each of these different nodes. It's watching every single one, and anytime that something happens inside one of these nodes, the master gets a little notification. So we can kind of imagine that when I ran Docker kill and then I killed that container, we can imagine that one of these containers essentially fell away, like so. So the master then got a little notification that said, hey, little issue here, one of our containers just up and died, completely gone. And so the master very temporarily updated its little list of responsibilities to say, okay, I need 4 copies of multi-worker, but I now have 3 copies running. Whoa, that's a big problem. So the master then looks back out at its collection of nodes, and it says, maybe it picks this node right here and says, hey, you need to have an additional copy of multi-worker running. And so this node right here will use that image that it's already downloaded, and it'll create a new container out of it. So multi-worker container. And then it reports back to the master and says, hey, we're good. I just started up another copy. And so the master says, great, I now have 4 copies running again, and I am plenty happy. All right, so that is the full flow. That is what is happening behind the scenes. Now, some of the big takeaways that I want you to understand here from all this stuff. First off, when you and I loaded up that deployment file, we did not pass that deployment file directly off to one of these worker nodes. Instead, the deployment file went to the master. So the big lesson here is that you and I, as developers, work with this master. You and I do not work directly with the nodes over here. In other words, you and I are never going to reach into a node with some series of commands and attempt to manually start up a container inside of one of them. Instead, we're always going to use the kubectl command line tool, which is going to send all of our commands off to the master. It's then up to the master and the different programs that are running inside this thing to reach out to some appropriate node and create the appropriate container, or essentially update the state of, update the appropriate container, update the appropriate node. It's up to the master to reach out to some node and tell it to do some amount of work to fulfill the master's little list of responsibilities. The next big thing to take notice of is that the master is always watching each of these different nodes. Anytime that some container, or some object for that matter, runs into some issue, the master is going to automatically attempt to recreate that object inside of some given node until its list of responsibilities is 100% balanced out. Now that kind of idea of us kind of saying, hey, master, here's your list of responsibilities, and then having the master constantly work to make sure that that list of responsibilities is fulfilled is one of the most important ideas in everything around Kubernetes. Yes, just as important as that other thing I said was really important, the networking stuff. Yeah, there's a lot of important stuff. You get the idea. But in reality, or all joking aside, the idea of the master constantly working to fulfill this list of responsibilities right here is very important. So we're going to take a quick pause right here, and we're going to have a real quick discussion. I'll make it as quick as I possibly can, I promise, about how we interact with Kubernetes in general, and how we approach this idea of having the master kind of have this list of responsibilities that it needs to fulfill. So quick pause right now. We'll come back to the next section, and we're going to expand on this idea around the master. In the last section, we had a very long discussion about what Kubernetes is doing behind the scenes to deploy our application with some given deployment file. And there's a couple of takeaways I want to highlight very quickly. So here's a couple of important notes that I just want to kind of double down on and make sure are really clear. So first off, Kubernetes overall is a system to deploy containerized apps. We've been talking about services and pods and objects and all this stuff, but at its core, it's all about deploying containerized applications. Some of these different objects that we're going to make use of have a goal of supporting these containerized applications, but at the end of the day, it's all about running containers. Next up, a node is an individual machine, like a physical computer or a virtual machine that is going to run some number of containers or objects. On your computer with Minikube, you are currently running exactly one VM that is behaving as the node. We also have a master. This is a machine or virtual machine that has that set of programs that are going to be managing everything that goes on inside the nodes associated with your Kubernetes cluster. Now, the next item on here is something we didn't quite cover. Remember Kubernetes, we did. We spoke about Docker Hub. So Kubernetes specifically did not build our image. It got the image that we wanted to deploy from Docker Hub. Next big thing is that the master decided where to run each container. You and I did not add in any input saying, hey, specifically, I want you to run this multi-worker container like over here or over here. Now, we absolutely can control where a container gets deployed. We can add in some configuration to our deployment files to say, oh yeah, I want this pod that gets created to be created on like this node or this node. We have the ability to do that, but by default, the master is going to decide where to deploy all of our different objects for us. Now, the last two items on here, and this is the real focus of what I want to cover inside this section, is the important stuff. So to deploy something, we updated the desired state of the master with a config file, right? We passed in this deployment file over here, and the master updated its little list of responsibilities to say, oh, okay, yeah, I understand. I'm supposed to be running 4 copies of the multi-worker image. So the way in which we interacted with our entire Kubernetes cluster was to update its desired state. We said, this is what we want you to be doing. We did not specifically say something like, hey, please create this copy of multi-worker, and this copy, and this copy, and this copy. Instead, we just very generically say things like, I want to run 4 copies. And then we hand that directive off to the master. And the master is in charge of making that happen. Now, the other big important thing here is to understand that the master is going to work constantly to meet your desired state. And that was the entire purpose of me killing one of those containers and showing you that Kubernetes automatically restarted it for us. So the master is going to just constantly churn away at its list of responsibilities and make sure that our desired state right here, like the fact that we need to have 4 copies, is always going to be met. Now, again, this entire topic, or this entire idea of having the master kind of work to meet our desired state, and the entire idea of us passing some desired state to the master in the form of a configuration file is really key to understanding Kubernetes and how you and I work with it as a developer. So we're going to look at a couple more diagrams that are going to expand upon this idea of us kind of telling Kubernetes what we want, as opposed to us very specifically saying like, hey, please create this pod or something like that. Now, this overall topic is kind of a discussion between 2 ways of approaching deployment. We could approach deployment with an imperative style or a declarative style. With an imperative style, you and I would issue a series of commands that say specifically like, create this container, and create this container, and then delete that one, and then upgrade that one, and restart that one, or whatever might need to happen. In the case of a declarative deployment, we say to our master something like, you know, it'd be great if you just made 4 containers happen and made 4 containers happen all the time. And you know what, master, you just go ahead, you figure out how to deal with that. So with the imperative, we give very discrete actions, or very discrete commands. With the declarative, we kind of set guidance or a directive. We say, just make this happen for me, would you please? Now, just kind of giving you a quick overview right there is not really enough, so I just want to show you a couple diagrams to really drill home the point or the differences between an imperative deployment and a declarative. Okay, so here's an example of a imperative deployment. I want you to imagine for a second that we did not have access to any of these configuration files or anything like that. And I want you to imagine that we just had access to some like imaginary Kubernetes command line. All right. So I want you to imagine that you and I have or need to have 3 containers. Like for whatever reason, we decide that our application has to have 3 containers right now. And let's imagine that we don't really have any Kubernetes commands or anything like that to get the current status of how many containers we are running. So what would you have to do to make sure that you have 3 containers? Well, chances are you would have to open up some dashboard on Google Cloud or AWS, and you would have to look at the overall state of your application. So maybe when you open up your dashboard, you see that you have 4 containers running. So what would you have to do to get 3 containers? You would have to very distinctly look at your current state and then figure out some way to migrate from your current state of 4 containers down to 1 container. And so you would have to just say, there we go, fix that up really quickly. You would have to issue some command to say, okay, I need to remove 1 container to get from having 4 down to 3. And so you might issue this imaginary command that says something like, Kubernetes remove 1 container. Now, the important thing that I want to really drill home here, this is the really important thing to understand, is that even though it kind of seems trivial to say, okay, I need 3 containers and I currently have 4, all I need to do is remove 1, that still required a lot of computation out of you. You had to understand your desired state. So your desired state was to have 3 containers. You had to do some research to determine your current state, like how many containers you currently have, and then you had to come up with some migration path, some series of actions that would take you from your from your current state to your desired state. And so you would have to come up with this migration plan that says, okay, I'm going to remove 1 container, and that will take me from my current state to my desired state of 3 containers. Now, I'm sure that sounds like a trivial example, like, Stephen, really? Figuring out to remove 1 container is hard? Well, let's look at a more complex example, all right? Slightly more complex. So in this example of an imperative deployment, let's imagine for a second that you have a ton of different containers running, and they're all running some very specific version of the multi-worker image, like maybe version 1. And so you come along and you decide, all right, I need to update every running container to use image version 1.23 instead. Now, in this case, things would be a lot more challenging. You would have to open up your dashboard. You would have to find all of the different containers that were running the multi-worker image. So for example, maybe like, this container and this container and this container right here, maybe these were running a completely different image. And you want to update this one, this one, this one, this one, and this one. So maybe you would want to update the versions used by the green one. So now, determining a migration strategy is a little bit more complicated. You have a desired state of running version 1.23 inside of every container. You have a current state where these container are running maybe version 1 or whatever it might be. And so you would have to figure out some way of isolating just these green containers and saying, okay, I want to pick out like container 1, 2, 3, 7, 20 right here, and I want to update just those. And so you would have to figure out some series of update actions to just update that very specific set of containers. And again, I'm going to argue that that might be really challenging for you to do. So how would we approach a problem like this with a declarative deployment rather than an imperative deployment? Another diagram. So this is how we would do things with a declarative deployment. You would say, okay, I need to update all of my containers running multi-worker to version 1.23. So here's what you would do with Kubernetes in an ideal world. You would open up your config file. So like this config file right here, the same one that we just put together a little bit ago. You would find the image designation right here. And you would update the tag on this thing to say, I specifically want to use version 1.23. You would then save that file, and then you would send that config file off to Kubernetes. Master would then inspect that file. It would update its own little list of responsibilities right here and say, oh, okay, I understand. I need to be running version 1.2, 1.2.3, or whatever it might be. And then the master is going to automatically find all the nodes that are not running version 1.23. It's going to take those all down. Excuse me, not nodes, but pods. It's going to take all the pods that are not running version 1.23 down, and it's going to create new pods that are running the correct version. And now my question to you is, which of these two deployment processes would you want to go through? Where's my diagram? Over here. I bet you would probably want to use this declarative process. I bet anything you would not want to be responsible for looking at the current state of your cluster, finding all the outdated containers, and writing a command to update each of them. Instead, it would be far easier to just update a single config file, send that config file to Kubernetes and say, here you go, take care of it. Like, I don't care. It's up to you. Figure it out. And Kubernetes, the master, is going to constantly work to make sure that its configuration is met and make sure that whatever the real state of the nodes are is what it needs to be. Okay, so this has been a pretty long discussion, and I think that you probably get the idea now of the differences between a imperative deployment and a declarative deployment. So why am I telling you all this, right? This has been like 10 minutes. I'm really drilling in here. This has been a very in-depth talk. So the reason I'm telling you all this is that when you start looking at Kubernetes documentation, blog posts, Stack Overflow posts, whatever else, you are going to see some resources out there recommend that you take a imperative approach. You're going to see some resources that say, oh yeah, write in a command into kubectl that specifically adds a pod, or specifically removes a pod, or specifically updates a pod, whatever it might be. But I'm going to tell you that Kubernetes has the ability to do things both ways. So Kubernetes has the set of commands through kubectl to take this imperative approach. That is the set of commands that some blog posts out there are going to advocate. And they're going to say, oh yeah, run something like pod, update, whatever it might be. But Kubernetes, or kubectl, also has a set of commands to do things through a declarative approach as well. Throughout this course, you and I are going to constantly strive to only use the set of commands that take a declarative approach to building out a Kubernetes cluster. That's the whole point. That's what I'm trying to convey here in this entire lecture. I want you to understand that when you start reading these blog posts, some of them are going to tell you to do things in an imperative way, but for any real production deployment, every engineer out there, everyone in the community is always going to advocate taking the declarative approach. That's the entire point of Kubernetes. And so it's going to be kind of up to you when you're reading a blog post to understand that, okay, maybe not all these blog posts are saying things that are 100% accurate. And hopefully, eventually you'll start to develop a sense of when a blog post says like, oh yeah, just go run this command to update this pod in place. That's probably something you don't want to do. In general, you and I are going to always try to do the same thing over and over and over again of updating a configuration file and then sending that config file off to Kubernetes master again and again and again. And so throughout this entire course, everything that you and I are going to do from here to the very end is going to be all about updating these configuration files with some new desired state, and then eventually sending that off to Kubernetes master. And we're just going to repeat that process over and over and over. And that's exactly how you are going to do things on your own application. And that's how you're going to do things, especially in a production environment as well. All right, so that's enough soapboxing for me for a while. So let's take a quick pause right now. Now that we've gotten all out of the way, we'll take a quick pause right now, and we're going to continue in the next section. So quick break, and I'll see you in just a minute. In the last section, we had a very long discussion about the differences between an imperative and a declarative deployment. In this section, we're going to put a little bit of practice into this and get a very practical example of how we might update an existing object using a declarative approach. So what are we going to update? Well, we're going to say that our new goal, the old goal was to just create a container inside of our Kubernetes cluster. We're going to say that our new goal is to update that existing pod that we created to use the multi-worker image as opposed to the current multi-client image that it is currently using. So essentially what we want to do is find that existing pod and update the image that it uses. Now let's take a quick thought on how we would do this with an imperative approach and a declarative approach. So if we took an imperative approach to this, we might do something like the series of steps you see on the left-hand side. We might run a command to list out all the different pods that we have inside of our cluster right now. And then maybe we would issue a follow-up command to like take an ID or something like that out of the current running pod and tell that thing very explicitly that it should now be running a new image. So in this imperative approach over here, we would have to essentially get the current state of our application by running a command to list out the current pods and find some ID of the current pod that is running the multi-client image. We would then have to figure out a migration strategy on our own to update from the current state to our desired state. Now, in this case, figuring out that migration strategy is pretty straightforward. We could probably look up some command API reference and figure out how we could tell a pod to update the image it uses. But again, that would take a little bit of work. So I'm going to suggest that we instead use a declarative approach. With a declarative approach, updating an existing object inside of our Kubernetes cluster is always going to be the exact same process every single time. So we're going to go and find the config file that originally created that pod, and we'll then make an update to it. The update is going to simply say, hey, I want to use a new image. So inside the config file that we used to create the pod, we're going to no longer say, I want to use an image of multi-client. Instead, I now want to use a new image of multi-worker. Once we make that change to the config file, we're going to just throw it into kubectl at the command line, and Kubernetes is going to work to update that existing pod to use the new image. Now, one thing that's kind of interesting about the process of the declarative approach over here is that we're essentially saying that we're going to take this config file, throw it into kubectl, which is, of course, going to forward it on to master, and somehow, magically, the master is going to realize that it needs to update this existing pod as opposed to creating a new one. And that's actually something that's kind of interesting. We're just going to update this config file, and you might notice that inside this config file, there's really no unique ID or anything like that. There's nothing that says, hey, go and find this existing pod, like a pod we already created and update it. And so it might be a little bit confusing to figure out when making a change to a configuration file will update an existing object, as opposed to just deciding to create a completely new one. So behind the scenes, here's what Kubernetes does anytime that you toss in a configuration file into kubectl and master. So inside of our config file, we're always going to have an object, or we're always going to be creating an object that has a name. So every single last object that you and I ever create with a config file is always going to have a name assigned to it. And in our case, we assigned a name of client-pod. In addition, every single config file we ever put together is going to have an object type assigned to it as well. And technically, it's not like labeled in there as the type, it's really labeled as the kind, recall? Remember, like right here on line 2, we say kind pod, not object type. But you get the idea. Every config file is going to list out the type of object that we want to create. So every single time that we take a configuration file and pass it into kubectl, the master is going to look at that configuration file and inspect its name and kind properties. It's then going to look at all the different running services inside the cluster, and it's going to say, okay, if I have any other object inside of here with a identical name, and in this case we do, and an identical type, then that must mean that rather than trying to create a new object, I'm going to try to take the updated configuration file and apply all these changes to the object that already exists inside the cluster. So in other words, the name and the kind are our unique identifying tokens for any object that we create. If you ever want to update an existing object, you're going to take your existing configuration file, you're going to always leave the name the same and the kind the same. And then you can change the rest of the configuration file and then feed it all into kubectl. And master is going to automatically find the existing object and make updates to it. Now, if we made a change to the name, so if we said client pod, I don't know, new or something like that. Well, it now has a new name, so master is going to say, okay, do I have an existing object that is a pod with the name of client pod new? And in this case, we do not. There's no existing object inside of our cluster with that same name and same object type. And so master would say, okay, well, this is a new name. I guess I need to create a brand new object with that name and that type. So in short, anytime that we want to make an update to an existing object, we just go and find the original configuration file. We'll leave the name and the kind the same, and then we can make any other change we want to inside that file. So with that in mind, let's take a quick pause right here. We're going to come back to the next section, we're going to make an update to our configuration file and then feed it into kubectl, and we're going to expect that it's going to update an existing pod as opposed to attempting to create a brand new one. So quick break, and I'll see you in just a minute. In the last section, we spoke about how we're going to update an existing object. We're going to take that existing config file, leave the name and the kind the same, and we can make any other change we want to the file, and throw that back into kubectl, and our expectation is that we're going to update an existing object as opposed to creating a new one. So let's flip on over to our config file. Remember, our goal right now is to update the existing pod to use the multi-worker image instead of the multi-client. Now, quick note here, remember that the multi-worker image really expects to have a copy of Redis available. And so it's entirely possible that when we do this update, something is going to crash, or I should say the container that gets created might crash because there is no copy of Redis available. Nonetheless, I just want to make sure that we have the ability to update the image that is being used, and I'm not really concerned about getting a pod successfully running. I just want to update the image right now, that's all. All right, so we're going to open up our code editor. We're going to find the client pod file. We're going to leave the kind the same and the name identical as well. The only thing we're going to update inside of here is the image that we are using. So instead of using multi-client, I'm going to use multi-worker instead. We'll leave everything else inside of here identical. I'm not going to change the port, even though multi-worker doesn't really expose anything on port 3000 or anything like that. Again, I just want to update the image and make sure that we are updating a pod in place and not creating a new separate pod. All right, so I made the change to multi-worker. I'm going to save the file. I'm going to flip back over to my terminal. I'm going to make sure I'm still inside my simple k8s directory, and then I'm going to feed this updated configuration file back into kubectl by using that apply command. Remember, apply is the magic command. It's how we make any changes to the configuration of our Kubernetes cluster. So I'll say kubectl apply-f client-pod.yaml. And now you'll notice that when we hit enter and we submit that command, we do not see something that says like, oh, I'm going to update, or I'm going to create a new pod or anything like that. Instead, it says very specifically, client pod has been configured. When you see the message configured, it means that we've updated the configuration that is applied to client-pod. So we should now be able to run that get pods command and verify that there's still one pod that exists inside of our entire cluster. So I'll do kubectl get pods, and you'll notice that we now have still just one pod. It has the name of client pod. There's one copy, it's running. There's 2 restarts currently because we just caused this thing to be restarted when we updated the image that it's running. Now, the only thing that's kind of awkward right now is that we can't really inspect this pod and verify that it is, in fact, running the updated image. So I want to figure out some way that we can actually look at this very specific pod right here and look at the different containers that are running inside there and verify that 100%, no two ways about it, yes, we are running the multi-worker image. So in order to inspect this very particular pod right here, we're going to learn a new command on kubectl. Here's the new command. Oh, not there, not there. Where'd it go? Here we go. So to get detailed information about an object inside of our cluster, we're going to use the kubectl describe command. Describe is used to print out a ton of information about a very particular object. So we'll say kubectl describe. We'll then pass in an object type and then the name of the particular object that we want to investigate. Now, just as a quick curiosity here, or something that's kind of interesting, you can actually omit the object name if you want to. If you do that, you'll get detailed information about every different object type of the specified, or excuse me, every different object with the specified object type. But it's a ton of information, so in general, we usually use the full command, which is kubectl describe, the type, and the name, to just get information about that one particular object. So let's try that out right now. Again, we're going to run this command to verify that the client pod is, in fact, running that updated image. So I'll do kubectl describe. Our object type is pods, or we could simply say pod. Either one is fine, pods or pod. And then we'll put in the name of that very particular object, which is client-pod. So that's going to print out a ton of very detailed information about that very particular pod. Down at the very bottom, you're going to see a series of events right here. Very frequently, this is going to be some of the most interesting information. This is going to be events that are not logs coming out of the containers, but events that have occurred over the life cycle of the pod. So you'll see messages about things that have crashed, or pulling new images, or changing images, or stuff like that. Now, if we scroll up a little bit higher, there is a ton of information in here that's kind of outside the scope of what we want to talk about right now. But if you scroll up, scroll up, scroll up, you will see containers. We have a container with a name of client. Recall that client name right there was provided inside of our configuration file. So there's name client right there. And then we're told that the client container, remember that's the name of the container. This is kind of misleading because we have these kind of conflicting names all over the place. But essentially the image is the multi-worker image. That's exactly what we just updated our configuration file to use. So without a doubt, updating that configuration file and leaving the name and the kind identical found an existing object that was already running inside of our cluster, and it updated it in place as opposed to trying to create a completely separate pod. All right, so that's it. That's a quick example of this entire idea of declarative versus imperative deployments. So we like to use declarative as much as possible, and the formula for doing a declarative update is always going to be the same thing over and over. We're going to go find our original config file. We're going to make a change to it, leaving the type or kind and the name the same. We'll update some configuration inside the file, and then we're going to throw it back into kubectl. And our master is just going to kind of make the change for us. And we don't have to worry about manually printing out a list of running pods and issuing a command to update a very specific pod or anything like that. We're going to see this declarative approach throughout this entire course, just nonstop. It's going to be all we are doing throughout the entire course. Update the config file, throw it in kubectl, verify that in fact everything worked correctly. Okay, so that's a good example. Let's take a quick pause right here, and we'll continue in the next section. In the last section, we made a change to our pod configuration file. The very particular property that we updated was the image right here. We then fed that back into kubectl, and we saw the updated pod using the describe command. In this section, I want to make another change to this configuration file. Now, this next change we're going to make is going to appear to be a very small change, like similar in nature to changing the image, but when we try to feed the configuration file or the updated configuration file into kubectl, we're going to very quickly see an error message. So let's go through this process. We're going to see the error message, and then we'll talk about why we are seeing the error message that we're going to see. All right, so inside my client pod file, I'm going to find the container port listed down here. Now remember, multi-worker doesn't do anything with container port 3000. No usage whatsoever. Multi-worker has no ability to receive or make outgoing requests or anything like that. So we'll just make an arbitrary change here. I'm going to change the container port from 3000 to about 9999, like so. Okay, so totally arbitrary change, no rhyme or reason behind it. I'm going to save this file now, and then we're going to try to update our pod in place by using the kubectl apply command again. And again, when we run this command, you're going to see an error message, and we're going to talk about why we are seeing the error message. All right, so I'm going to save the file. I'll then flip back over to my terminal, and I'll do kubectl apply client pod.yaml again. Now when I run this command, we're going to see this tremendous amount of output right here. I want you to scroll up to the very top of this message. And up here, you're going to see the reason for the error. Essentially, it says that we are not allowed to update any pod configuration piece other than the image used, some other image property, some active deadline something, or tolerations property. So this error message right here is essentially saying that when we update a pod, we are only allowed to update these 4 different configuration properties. And so this definitely kind of goes very much in the face of what I just told you about how we make updates. I had just told you 2 seconds ago that, yeah, we make updates to existing objects by updating the configuration file and then feeding that into kubectl. But in this case, we just made a very simple change to our configuration file, and we very quickly saw an error message. So how do we use this kind of configuration file-based process of updating something if kubectl won't allow us to change something as basic as a container port? Well, of course, there is a workaround to this. So let's take a quick pause right here, and we're going to come back to the next section, and we're going to start to investigate how we can use a different type of object besides a pod to be allowed to change any piece of configuration tied to a pod that we want to. So quick break, and I'll see you in just a minute. In the last section, we made a very small change to our pod configuration file, updating its container port. But when we did so, we very quickly saw an error message that said that we were not allowed to update certain fields that are tied to a pod. So essentially that message is telling us that there are some fields that we are allowed to update, such as the image that a pod uses, but there are other fields that we are not allowed to touch at all once the pod has been created. And so this kind of flies in the face of everything I just told you about making changes to a configuration file. In other words, how are we going to change a configuration file to change an object inside of our cluster if there are fields that we are not at all allowed to update or touch? Well, to solve this issue, we're going to start making use of a new type of object that is going to replace our usage of pod inside of our very simple application as it stands right now. So the new type of object that we're going to make use of, in addition to pods and services, is something called a deployment. A deployment is a Kubernetes object that is meant to maintain a set of identical pods. So that can be 1 pod, 2 pod, 3 pod, whatever number. And the deployment is going to constantly work to make sure that every single pod in its set that it's supposed to manage is always running the correct configuration and is always in a runnable state. In other words, it is not crashing or it's not dead or anything like that. Now, a deployment is very similar in nature to a pod. Yes, I just said a deployment contains a set or maintains a set of pods, but at the end of the day, we can use either deployments or pods with Kubernetes to run containers for our application. So let's compare and contrast some of the differences between pods and deployments. So with the pod, we're running a single set of very closely related containers. Remember, in a pod, we're only going to stick in multiple containers if they have very tight integration with each other. In reality, pods are only used in a development environment, and usually only if you have like a very one-off single container or a very small group of containers that you want to run. We do not actually make use of pods directly in a production environment because of all these limitations around being able to update its configuration and stuff like that. Now, a deployment, on the other hand, again, is meant to run and manage a set of identical pods. So that is one or more. That can be 1 pod, 2 pod, 3 pod, however many you want. In that set of pods, every pod is going to be running the exact same set of containers with identical configuration. Now, the deployment itself is going to monitor the state of each pod. It's going to watch the configuration of each one. It's going to make sure that every pod is running the container successfully inside of it. If any pod happens to crash for any reason, the deployment is going to automatically attempt to restart that pod or completely recreate it in a fresh new state. We make use of deployments in a development environment, and we use them as the primary means of running containers in a production environment as well. So in this course, I first started off showing you pods just so you understand here is a very basic way of creating a container with Kubernetes. But in reality, when we start making use of Kubernetes for any serious purpose, we make use of deployments as opposed to individual pods. So from here on forward, we're going to kind of tend to forget that pods exist, and we're going to instead make use of deployments for running all of our different containers. Again, behind the scenes, a deployment is just making use of pods, so it's still very important to understand what a pod is and how you work with one. But again, we're going to make use of deployments in our development and production environments. Now, last thing I want to show you is just a very quick diagram here of what's kind of going on behind the scenes. So when we create a deployment object, it's going to have attached to it something called a pod template. A pod template is essentially a little block of configuration a little block of configuration that says, hey, here's what any pod that is created by this deployment is supposed to look like. So the pod template might say, okay, every pod that this deployment manages is supposed to have one container that has a name of client that exposes port 3000 and uses the image multi-worker. And so that deployment would use this template to create a pod that looks like this. A pod that has a name of, not client pod, just simply client. It's running the multi-worker image, and it exposes port 3000 to the outside world. If we made a change to the pod template over here, like let's say we're instead supposed to expose port 3000, We change that to 999 like so, then the deployment would attempt to either change the existing pod that it's managing, or alternatively, it would attempt to kill this pod entirely and replace it with a brand new pod that has the correct port assigned to it, like so. So again, this deployment object over here is going to be constantly watching all of the different pods that it maintains. It's going to be watching their state and making sure that they have the correct state. So at the end of the day, to solve this issue that we're having right now with updating the configuration for our pod, rather than trying to make use of a pod and update the container port, we're going to instead refactor this thing to instead be a deployment that creates a pod running the multi-worker image and with a very specific container port. Once we make use of the deployment, all those restrictions around updating certain variables, like say the container port right here or the name of the container, will be lifted. With the deployment, we can change any piece of configuration tied to a pod that we want to. We don't have to worry about seeing that error message like we did previously. Okay, so let's take a quick pause right here. We're going to come back in the next section. We're going to start to refactor our client pod file, or just completely recreate it for that matter, and we're going to turn it into a deployment object type instead. So I'll see you in just a minute. In the last section, we started talking about deployment objects. Remember, a deployment is going to run and manage a set of identical pods. From this point forward, throughout this course, we are no longer going to create pods ourselves manually. Instead, we're going to create deployments that will create pods for us. So deployments are appropriate for use in both a development and production environment. We're going to make a deployment that has a pod template that's going to try to create a container using the image multi-client, and we're going to make sure that port 3000 is exposed. Now, the reason we're going to make a deployment with multi-client and port 3000 open is so that we can test this out in the browser once the deployment creates our actual pod. So to make a deployment, we're going to use the same process that we use for every other object that we're ever going to create with Kubernetes. We're going to make a configuration file and then feed that configuration file into kubectl. So inside of my code editor, I'm going to create a new configuration file inside of my root project directory. And I'll give this file a name of client-deployment.yaml. And then inside this file, we're going to add all of our configuration to describe this new deployment that we're making. We're going to write out all the configuration together right now, and then we'll talk about the purpose of every line immediately after that. So I'll get started by writing out API version, and I'll say apps/v1. I'll specify kind of deployment. So these two lines right here, I bet you can guess what's going on. We are saying that we want to use an object that is defined inside the API version of apps/v1. And the specific type of object that we want to create is a deployment. Next up, we'll put down our metadata section. And we'll give this thing a name of client-deployment. Then we'll do our spec after that. For the spec, we'll say replicas is 1. I'll add on a selector with match labels and a component web property like so. I'll then unindent, so I now only have one indent right here. I'll say template. I'll put in metadata, labels, component web. I'm going to unindent again so that I'm on the same indentation layer as metadata. I'll say spec, containers, and we'll define the list of containers that we want created with every pod that is controlled by this deployment. So this is an array entry, so I'll put in my little dash like so, and I'll say that I want a pod that has a name, or should be a container in this pod with a name of client. I want it to run the image of my Docker ID / multi-client, and then finally we'll set up that port mapping. So I'll say ports with a container port of 3000, like so. Okay, so some things inside this file might look a little bit familiar. Let's take a quick pause. We're going to come back to the next section and start breaking this thing down line by line. So I'll see you in just a minute. In the last section, we put together our first configuration file to create a deployment. In this section, we're going to walk through the configuration file and talk about a couple of interesting things that's inside of here. Now again, the first two lines that you see specify the API version and the object type that we want to create. So in this case, we're making an object of type deployment. After that, we see a very familiar metadata section that names the object that's going to be created by this configuration file. So in our case, our deployment will have a name of client-deployment. Now down in the specs section, I want to skip on down to the template property right here. So inside the template, we're listing out the configuration that is going to be used for every single pod that is created by this deployment. The entire template section right here probably looks a little bit familiar to some of the configuration that we put together inside of our client pod.yaml file. So back inside of client pod, we had a label, we had a list of containers assigned as well. And so you can essentially imagine that this template section right here is defining the exact configuration that should be used for every pod that is created and maintained by this deployment. Every pod that gets created by this deployment will have a label of component web, and it will have a container with the name of client and using the image multi-client with a port 3000 mapped up to that container. Now, besides the template right here, the other properties that are kind of interesting is replicas and selector. So first off, replicas. As you might guess, this is specifying the number of different pods that this deployment is supposed to make. And remember, every one of those pods that it creates are going to be absolutely identical in nature. So at this point, we are saying, hey, deployment, create exactly one pod using this template down here. If we wanted to, we could very easily change this up to something like 5. That means that we would want to create 5 separate pods, each of which run this exactly identical template. We're going to leave replicas as 1 for right now, however. Now, the other thing that's kind of interesting inside of here is the selector. The selector looks very similar to a selector property that we previously put into our node port file. So back over here, we had a selector property as well. Let's talk about what the selector is. Essentially, it's doing something very similar to what the selector inside of the service configuration file was doing. You see, when a deployment creates a pod, it doesn't directly create the pod itself and maintain it. Instead, the deployment reaches out to the Kubernetes API on the master and it says, hey, master, I need you to create a pod for me, and here's the configuration for it. The master then goes ahead and creates the pod. Now, it's the master or some program inside the master that is creating the pod for us. And so the deployment, after the pod is created, needs to somehow get a handle on the pod that is created. And that's the purpose of that selector field. The deployment says, okay, I'm going to ask master or some program in master to create this pod for me. After it gets created, I need to somehow get a handle on it. And so to get a handle on that newly created pod, I'm going to look for objects with a label of component web. And so, of course, every pod that we are creating using this deployment is going to have a label of component web, because that's what we specified inside of our template. And so match labels and selector right here, this section right here is essentially giving us a handle on this label down here. I know it seems a little bit repetitive to have to kind of like designate this stuff twice inside the same file, but it's entirely possible that we might have multiple labels assigned to our deployment, or excuse me, multiple labels assigned to the pod that is created by our deployment, and maybe we only want our deployment to look for 1 or 2 very specific labels out of those. So that's why you're seeing it kind of replicated here twice. Okay, so that's pretty much it for our deployment configuration file. So let's take a quick pause right here. We'll come back to the next section, and we're going to apply this deployment file to our Kubernetes cluster by using kubectl, and then we'll very quickly be able to look at a couple of interesting things around the deployment and the pod that is created with it. So quick break, and I'll see you in just a minute. In the last section, we finished up our client deployment configuration file, and we're now ready to toss this thing off to kubectl and see it running on our local cluster. Now, before we do, I want to give you a very quick reminder. If you flip over to your terminal and do a kubectl get pods, you'll recall that we still have the original pod that we had created with our client pod.yaml configuration file. I think that would be really nice if we got rid of this pod or somehow deleted it before we sent out our deployment. That way that when we get our pods in the future, we will only see the one pod that was created by the deployment, as opposed to the one pod from the deployment and this one pod from the original client pod configuration file we had created. So I want to figure out how we can delete this existing pod. Now, to remove an existing object, we're going to be making use of the configuration file that was used to create it. So in order to remove an existing object, we're going to run kubectl delete -f, and then we'll pass in the config file that was used to create that object. When we pass in that configuration file, kubectl is going to look at the file. So here's the client pod file. It's going to look at this file. It's going to look at the kind property right here and the name specified as well. kubectl is then going to try to find an object with the same type that has the same name. And when it finds it, it's going to delete it. Now, one thing I want to mention very quickly here is that this delete command seems an awful lot like an imperative update to our cluster. And in fact, it really is. This is an imperative update. We are issuing a very direct command that says, hey, Kubernetes, I want you to make this very discrete change to the state of our cluster. Now, unfortunately, this is something that we really just can't quite get over. When we want to create a resource or change an existing resource, we pass in an updated configuration file. And so we're kind of leaving it up to Kubernetes to make the appropriate changes. But when we want to delete a resource, unfortunately, if we wanted to delete some object inside of our cluster, we would have to kind of take the entire state of our entire cluster and then subtract out that one object. In other words, it's just kind of hard to picture a way to make a declarative update that will delete an existing object. And so this is going to be the one kind of location where we kind of fall back to the idea of an imperative update to the state of our cluster. Okay, let's give this a shot. So back at my command line, I'll do kubectl delete -f, and then I'll specify the client-pod.yaml file. And then we'll see that the pod with the name of client pod was deleted. Now, if it appears that this command just seems to hang, it will eventually resolve after about 10 seconds or so. When the pod gets deleted, it's going through the same process in the background that usually gets applied to deleting a container with the Docker CLI. Remember, when you delete a container, or stop a container, I should say, the container is given 10 seconds to resolve, and then eventually it just gets killed. That's what happens in the Docker world. And the same thing is what happens when we delete a running pod. It gets 10 seconds to resolve and eventually turn itself off, and then after those 10 seconds, the thing automatically just gets axed entirely. If we now do a kubectl get pods, we'll see that we no longer have any running pods. Okay, so now that we've cleaned things up a little bit, let's try applying our configuration file of client-deployment.yaml to our cluster. After we apply this thing, we should see a new single running pod using the multi-client image. So I'm going to flip over to my terminal, and I'll do a kubectl apply -f client-deployment.yaml. And then we very quickly see that the deployment was created. So we can now print out the status of all of our pods with kubectl get pods, and we'll see that there is exactly one pod running right now. And it has a randomly generated name, very clearly tied to the client deployment that we just created. We can also print out the status of that deployment itself using the command kubectl get deployments. So we're still using the get command, the same one we were using before, but we're changing the type of object that we are looking for. So now, as opposed to looking for pods, we're looking for deployments. So I'll run that, and we'll see that we have one deployment called client deployment. You'll also notice a couple of interesting columns on here. We have ones across the board for desired, current, up-to-date, and available. Desired is a reference to the number of replicas or the number of pods that this deployment wants to eventually have. So at present, inside of our configuration file, we said that we want exactly one replica running, and so we have desired of 1. We then see current, so that's the number of pods that are up and running. We have up to date, which is also 1. So at any point in time that you make a configuration change to your deployment, specifically a configuration change to the template down here, the deployment would automatically mark all the existing pods as being out of date. And so we might see up to date go down to 0. And then as the existing pods get updated or recreated with that new configuration state, they'll eventually restore this up to date field. And then finally, available right here is the number of pods controlled by this deployment that are ready and available to accept incoming client traffic, or essentially just successfully running their containers with the appropriate configuration for each one. Okay, so that's it. So we've now seen how we can use a deployment to create a set of pods, or in this case, just one single pod. Now, the last thing I want to do is still make sure that we are able to visit our running application inside of the browser. So we want to make sure that this pod right here is in fact successfully running the multi-client image. And I want to make sure that we can still access our React project files. So let's take a quick pause right here. We'll come back to the next section and we'll make sure that we can still access this pod or this container in our browser in the next section. In the last section, we finally applied our first deployment to our local cluster. Now, just to make sure that everything is working the way we expect, I want to try to connect to the container inside of that pod running the multi-client image. And when we connect to it, we should see that little React application appear on the screen. So I want you very quickly to remember how we connect to our local cluster. We do not use localhost. We have to run that minikube IP command. Remember that minikube virtual machine that is our local node has its own IP, completely different from localhost. So we need to first run minikube IP. Once we get the IP address, we'll then make sure that we connect to the port that is associated with that service that we created, which was hard-coded to be 31515. So back at my terminal, I'll do minikube IP. There's the IP of my virtual machine. I'll copy it. I'll make a new tab inside my browser, and then I'll put on :31515, because again, that is the hard-coded port of our service. And when I do so, I do in fact successfully see my application appear on the screen. Awesome. Now, this is actually going to be a really good time to start to understand why we use these service things. Like, why do we have to create that service object? Why were we not able before to just directly connect to one of our pods that was running the container that we care about? Well, now that we understand the idea behind deployments, understanding why we have to have these service things is going to make a lot more sense. So one thing I want to show you very quickly. Back over at your terminal, try running the command kubectl get pods, and then we're going to add on an argument here of -o wide, like so. That's going to still get our list of pods, but it's going to append on a little bit of additional information. Now I'm going to zoom out here really quickly just so I can see this thing on a single line. There we go. Now I want you to notice how we now have these IP and node columns over on the right-hand side. Now the really important column to take notice of here is the IP column. Every single pod that we create gets its own IP address assigned to it. So when we just deployed our deployment just 2 seconds ago, and that created a pod, it was randomly assigned an IP address of 172.170.6. This is an IP address that is internal to our virtual machine. So you and I cannot visit that IP, or at least we cannot visit it very easily. It is an IP address that has been assigned to the pod inside of our node right here. Now, the interesting thing about that is that if this pod ever gets deleted, or if an additional one is created, or if for any reason the pod gets updated or changed in any way, shape, or form whatsoever, it's entirely possible that the pod might suddenly get a brand new IP address. So let's imagine that this pod right here has that IP address of something like, I don't know, the 172.001. We'll just kind of make up an IP address like so. So I want you to imagine if we figured out some way to connect our browser to a pod running directly inside of our node. Then inside of our browser, we would type in something like 172.001. And then we would probably want to connect to port 3000. So we'd probably put on :3000 or something like that. Now the problem starts to arise if we start to recreate this pod right here, because maybe we have to remake it because our configuration has changed on the deployment, or maybe the original pod crashed, or whatever reason it might be. And so we can imagine that maybe we have to create a second pod. And this one would get a randomly generated IP of something like 002. And then maybe this original pod gets deleted. Well, now we originally had that IP address of 172.001. That IP address is not going to work anymore because the object or the pod associated with it just plain no longer exists. And so in order to access this pod right here, we would, in theory, now have to manually type in that 002, like so. Now, as you might guess, having to update the IP address all the time inside your browser in a development environment would definitely be a big pain. And that's why we make use of these service objects. this service is going to watch for every pod that matches its selector, because remember, that service has a selector. If we look at client nodeport.yaml, it has the selector of component web. So the service is going to look for every pod with that selector and then automatically route traffic directly over to it. So that's why we make use of the service. These pods are coming and going all the time. They're getting deleted, they're getting recreated, and every time they potentially might get assigned a brand new IP address. The service is going to kind of abstract out that difficulty, and that's why we make use of these services anytime that we want to connect to one of our different pods. Okay, so hopefully that gives you a better idea of why we care about these service things. So let's take a quick pause right here, and we'll continue in the next section. In this section, we're going to start making some changes to our deployment configuration file and just verify that all the pods that are associated with this deployment successfully get updated. So in particular, I really want to try updating the container port value down here from 3000 to some other value, because you will recall that when we tried changing that container port inside of our client-pod.yaml file, we very quickly got an error message saying, hey, you can't update that value. Okay, so back inside of the client deployment, so we're in the deployment file right now, I'm going to find the container port, and I'll update the port to 99999 like so. Now, just so you know, when we change this port assignment, you will no longer be able to visit our application inside of the browser. So in case you apply this update and then try to test it out inside the browser, it's not going to work because the container doesn't care about port 999. It wants to expose traffic on port 3000. Okay, so now that we changed our configuration file, I'm going to make sure that I save the file, and then I'm going to go back over to my terminal, and we're going to do the same thing we always do anytime we want to update an object. We'll do a kubectl apply-f client deployment.yaml. So I'll run that, and then it tells us very directly that an existing object type with this name was configured. It says configured as opposed to something being created. So we definitely just made a change to an existing deployment as opposed to creating a new one entirely. We can now do a kubectl get deployments to print out all of our deployments. Yep, it's still there. I can do a kubectl get pods, and now with this, you're going to see something a little bit more interesting. Notice how the age of this pod right here is 26 seconds. So clearly, when we apply this configuration file right here, Kubernetes noticed that we made a change to the template for the pods that are being controlled by this deployment. It saw that we changed the container port. And so rather than trying to update the existing pod that already existed, it deleted that pod and completely recreated it with the new container port value right here. Okay. Now, one thing that would be really nice to do is make sure that this new pod right here is in fact running with that new port. So I'll do a kubectl describe pods. We'll get the long form description about this pod right here, and we'll probably be able to verify that port 999 is assigned to it. Now remember, when you do describe pods, the name of whatever you want to look up is completely optional. In this case, we only have one pod, so I'll just print out the information about all pods because, hey, there's only one. Okay, so when I run that, I'll scroll up a little bit, and then I should be able to see our list of containers. Here's the client container, and it has port 999 mapped on it. So without a doubt, this pod is running with the most up-to-date configuration. Okay, so that's pretty cool. Now, I want to do one other change, or one or two other changes here. Let's first try scaling up our replicas setting right here. So when we scale up from 1 to something like, say, 5, we're now going to have our deployment attempt to create 5 different pods, all with this identical template right here. So I'm going to make sure I update replicas to 5. I'll save the file, and then as usual, we'll do a kubectl apply client deployment.yaml. And now, if you type in very quickly kubectl get deployments, we might, okay, a little bit too slow in that case. You'll notice that everything says 5 right here. If we were a little bit faster, we might be able to see that there are less than 5 of these different pods available. We'll make another change in a second that will hopefully be able to, if we type in this get deployments fast enough, we might be able to see the update in action. And we'll see something like, hey, only 5 or maybe 1 or even 0 pods are currently available. So if we now do a kubectl get pods, you'll notice we have 5 separate pods, each of which are running a unique copy of that very specific client. Let's see, multi-client, that's the idea, or that's the name of it, multi-client image. So we now have 5 containers running, each in their own very separate little pod. Let's try making one more configuration change. So how about instead of running the image multi-client, let's try running the image multi-worker instead. So I'm going to change the name of the image that we're running inside this pod. I'm going to make sure I save the file. And now this time, after we do the kubectl apply-f client deployment, I'm going to very quickly, right after I run this command, I'm going to very quickly do a kubectl git deployments. And hopefully we'll be able to see some different numbers of containers, or excuse me, different numbers of pods inside there as the deployment is creating and destroying some of the pods inside of our cluster. Okay, so I'm going to hit enter here, and then very quickly I'll do a kubectl git deployments. Now that's interesting. So notice I typed in fast enough that I was able to see some different numbers in action here. So the client deployment wants to have 5 different pods with the very specific configuration listed right here. But at present, there are 7 pods. That means that maybe 5 of the old version exist, or actually, you know, we can use these other numbers here to figure it out. So there are 7 pods total, and 4 of them are up to date and available. That means that we have 4 up-to-date and available pods running the newest configuration that says that we should be running the multi-worker image. That means that there are 3 other pods, because 7 minus 4 is 3. It means that there are 3 pods still sitting around using the old configuration, and those need to be deleted and cleaned up. If we now do kubectl git deployments again, we're probably going to see 5 across the board, because now all the old versions of those pods have been deleted and replaced with the latest up-to-date version of the pod spec, which says that we need to have the multi-worker image running inside there. Okay, so it's pretty interesting to see these deployments in action. So let's take another quick pause. We're going to come back to the next section, and I want to point out 1 or 2 kind of interesting things about this entire deployment system that might trip you up when you start making use of it in a production environment. So quick pause, and I'll see you in just a minute. In the last couple of sections, we've looked at a couple of different ways of updating a deployment. So we understand that we can change the number of replicas, and we can change, say, the container port, or even the image that is used by this deployment whenever it is creating a pod. But one thing that we haven't quite looked at is how we can update a deployment when a new version of an image becomes available. So I want you to imagine for a second that maybe you and I go off to our multi-worker project, and maybe we make an update to that image, and then we push the image up to Docker Hub. How would we somehow get our deployment to pull down that latest version and recreate all of our pods using that latest version? I want to look into that a little bit inside this section. Now, let's take a look at a diagram that's going to explain the series of changes we're going to make to our project to kind of simulate updating an image and kind of simulate how we would update a deployment to accommodate for that updated image. Okay, so first off, we're going to update our deployment, and we're going to change it to use the multi-client image again. The only reason that we're going to change it to use multi-client is that it gives us something to look at inside the browser. And so it makes it really easy to verify that our pods are running the correct version of an image. After that, we're then going to go back over to the source code for our multi-client project. We're going to make a change to that project. We're going to rebuild the image and then push the image up to Docker Hub. So that's going to simulate a very real deployment or a very real change to an application. All the time when you're using Kubernetes and all this container stuff, you're going to want to change an image, and you're going to want to make sure that the latest version of that image eventually gets deployed onto your Kubernetes cluster. After we push that changed image up to Docker Hub, we're then going to somehow get our deployment to recreate all of its pods with that latest version of multi-client that you and I create. So let's get to it. Step number 1 is going to be to change our deployment to use multi-client again. So inside of my code editor, I'm going to find the client deployment.yaml file. We're going to make a couple changes in here. The first thing I'm going to do is reduce the number of replicas down to 1. So we're just going to run 1 replica all by itself. That's just going to make it a little bit easier for testing purposes so that we can get a better idea of when that single pod is being updated or recreated or whatever it might be. Next up, we're going to change our image right here. So instead of multi-worker, we're going to get multi-client. And then one other thing that I want to do on the image right here, besides putting on multi-client, is I want to make sure that we also update the port that is exposed or forwarded on that image. So a container port, rather than 999, we're going to change that back to 3000 like so, because you remember that is the port that is exposed, or that Nginx inside the multi-client image is going to listen on. Okay, so that looks good. Let's now take these changes. I'm going to save this file, and then I'm going to apply this new configuration to our Kubernetes cluster. So back at my terminal, I'll do a kubectl apply client deployment.yaml. So I'm going to make that change, and then we will want to very quickly test this out inside the browser and make sure that we can access that newly created container that's inside of that new pod. So remember, anytime that we want to access our app inside the browser, we need to get our minikube IP with the minikube IP command. I'll copy the IP address, then we'll go back over to our browser. I'll paste in that IP, and remember, we set up that service to listen on port 31515. So I'll do :31515. And then I see our application appear. Okay, so that's easy enough. Let's take a pause right now. When we come back to the next section, we're going to make an update to the multi-client image, and then we're going to push it up to Docker Hub. So quick pause, and I'll see you in just a minute. In the last section, we started to investigate how we can get a deployment to make sure that all of our pods are using the latest version of an image that is available. So in the last section, we flipped our deployment to use the multi-client again. We're now going to go back to the complex project. That's the multi-container project that we worked on previously. And we're going to update the multi-client image. So inside of my terminal, I'm going to open up a second tab, and then I'll navigate over to the complex project that we had previously put together. Remember that inside of here, we have that client folder. That's where the multi-client project is coming from. So I'm going to change into that directory, and then I'm going to start up my code editor inside of that client folder. All right, so here we go. So I've got my client project right here. Inside of the client project is that src folder, and inside there are a couple of different React components. And so to update our multi-client image and get kind of a change this thing that we can very easily see inside of our browser when we run this application, I'm going to open up the app.js file. And inside of here, I'm going to find the render method. Inside there, we have an h1 right here. I think that a very easy to detect change that we can make would be to alter the title that appears on the page. So rather than simply saying fib calculator, I'm going to put on fib calculator version 2, like so. So that's just going to be a very simple change that will appear inside of our browser, and it'll make it very obvious when we are using a newer version of this particular image. All right, so I'm going to save this file, and then we're going to close that code editor, and we'll then rebuild our image and push it back up to Docker Hub. So back at my command line, I'm going to make sure that I'm still inside of that client directory. We'll do a Docker build, and we'll be sure to tag this thing with your Docker ID / multi-client, like so. And then I'll specify my build context with a dot at the very end. Don't forget the dot. Okay, so I'm going to run that. It's going to rebuild the entire image. Now, remember, we have to rerun the build portion of that script because we made a change to our source code. After all that, we finally get our new image created. So now the last thing we have to do is push this new image up to Docker Hub. So I'll do a docker push my Docker ID / multi-client, like so. Okay, so it's going to push that set of changes up. And there we go, that's pretty much it. So now Docker Hub has the latest version of our multi-client image. And now it's just up to us to figure out how we can somehow get our deployment to make use of that newer image for all the pods that it manages. So let's take a quick pause right here. We'll come back to the next section, and we're going to figure out how we can somehow get our deployment to update all of the pods that it manages. In the last section, we updated our multi-client image, and then we pushed the result off to Docker Hub. We're now going to move on to step 3, which is to somehow convince our deployment to recreate or otherwise update all of our pods with the latest version of that multi-client image. Now, unfortunately, step 3 right here is very challenging, and there's not a very good solution around it. Now, that might be very surprising, but I just want to be very clear with you. In the world of Kubernetes, convincing a deployment to recreate our pods with the latest version of an image is not the easiest thing in the world to do. So inside this section, we're going to take a look at why this is challenging, and then we're going to look at a couple of different ways to solve this problem. Now, before we start talking about why this is challenging or any of the solutions, I want to very quickly mention to you that on the GitHub page for the Kubernetes repo, you can go to the issues board and reference issue number 33664. To get to this issue in particular, you can just type that issue number directly into your address bar. This is an entire issue with a ton of different conversation going on here, talking about how challenging it is and suggesting different ways of convincing your deployment file to somehow update all the pods that it is managing. So I do recommend maybe taking a quick glance at this issue thread and getting a better idea of some of the root causes here and some of the different ways of solving the problem. All right, so let's take a look first at why this is so challenging to get a deployment to update the image that is being used by all the pods that it manages. I want to first remind you that in order to update any object inside of our Kubernetes cluster, we make a change to our deployment file, and then we send the deployment file off to the kubectl command line tool with something that looks like this right here, right? We do the kubectl apply. Now, the issue that we have right now is that inside of our deployment file, there's nothing inside of here that says, hey, I want to use some particular version of our multi-client image. So when we send an update to multi-client off to Docker Hub, when we make our updated version of that image and we send it off, there's nothing that we can kind of turn back around to this file with and say, hey, I want you to now use like the latest image. Now, the reason that's such a big deal is that if we try to take an unchanged configuration file and apply it with kubectl, if there's no changes in the configuration file, then kubectl apply is just going to flat out reject the file. Let's try that out right now. Remember, we've already applied this file and we've made no changes to it since we last authored it. Okay, or excuse me, since we last applied it. So back at my command line, I'll do a kubectl apply -f client deployment.yaml. And then when I run this command, it's going to tell us that the file is unchanged. And so the entire file, the entire apply command is just flat out rejected because the config that we're trying to upload is identical to the last config we put in place. Now, when you put this file up, it's unchanged. That means totally rejected. So there's nothing inside that process that says, oh, we should probably go and see if a new version of this image is available. That does not occur. At no point when you try to re-upload or reapply that config file, it does not try to see if a new version of this image is available. And so the entire apply command just flat out rejected. That's why this is such a big issue. Okay, so with all that in mind, we're now going to look at a diagram that's going to lay out 3 possible solutions that we could use to get around this issue. So none of these solutions are really that great, I'll be honest with you. None of them are really that good. They're kind of the best of a bad situation. Okay, so here's the first option we can use to get our deployment to update with the latest version of that image. We could manually delete all the pods that are managed by that deployment. Now, when we manually delete a pod that is managed by a deployment, the deployment is going to very quickly notice that the pod is missing, and it's going to attempt to recreate it automatically. So in other words, if we go over to our terminal right now and do a kubectl get pods, and then attempt to delete this pod right here, the deployment will very quickly notice that it has a missing pod, and the deployment will recreate this thing automatically. So our hope there would be that when the pod gets recreated, hopefully it would pull down the latest version of that image. And so we could use that as a means to recreate our pods with the latest image, or excuse me, latest version of some particular image. Now, why would we not do this? Well, as you might guess, deleting pods seems like a really, really silly situation or a really silly solution. There's so many things that could go wrong with this approach. In a production environment, we could very easily accidentally delete the wrong set of pods. Totally possible. So if we delete the wrong set of pods, who knows what type of bad situation we would be in. In addition, if we manually delete all of our pods related to one very particular aspect of our application, let's imagine that maybe this is the pod that serves up all of our web traffic. And so if we delete all those pods for a very brief period of time, any user trying to access our application would be trying to get at a pod or get at a container inside there that just doesn't exist. And for a very brief window, our users would essentially not be able to access our application entirely. And so everything about deleting these pods just kind of seems like a bad idea. Okay, so let's take a look at the second possible solution. All right, so I want to give you a quick reminder on tagging of Docker images. When we tag a image, we put down usually our Docker ID, a slash, and then the repository or project name. Now, one other thing that we can optionally put in here is a colon and then a version for this image. And so we could put in something like, v1, and then maybe the next time we build the image, we would increment it to v2 or v3 or v4 or v5 or whatever it is. So as a possible solution to this problem, we could decide to tag our images with real version numbers and then specify that version inside the config file. So in other words, when we build our image back over here inside of, run our Docker build command and tag the image, we could put on a version number like v1, v2, v3, or v4, whatever it might be. We then push that tag up to Docker Hub, and then inside of our config file, we could append on that v1, v2, v3, v4, or whatever it is. Now, when we change the config file with a version number like this is an actionable change to our config file. So if I put on here v4 and then save the file and then rerun that kubectl apply command, that is detected as a very real change to our config file. And so the config file would be accepted by kubectl apply because we are specifying a completely different image version. Our deployment would then use that new image version to recreate and update all of the pods that it manages. So this would be one possible solution. Now, the downside to this approach is that it really adds in an extra step to our deployment process, and it's definitely not a very friendly step. Because think about what we would have to do. We would essentially have to make sure that anytime that we build our images, we would have to append on some version number over here, like 1, 2, 3, 4, 5, whatever it is. And then we would have to go over to our configuration file and put the exact same version number inside of here as well. So we would have to remember the current version and somehow insert that number inside of here. And that's definitely a non-trivial step to add in here. Now, one quick workaround to that you might imagine if you're a little bit savvy, you might think, okay, well, if it's such a pain to get the version number in here, maybe we could get like an environment variable or something like that would carry the version of that image. So when we build the image, we could store the version number in an environment variable and then reference that environment variable inside of our file. So we could do something like, client version. Well, unfortunately, we are not allowed to use environment variables inside of these config files. So that solution kind of goes out the window as being an easy workaround. So specifying the version, it definitely would work, but it adds in that extra step of having to assign a version number when we build the image. And then we also have to make sure that we somehow inject that version number into the file. We literally would have to inject the version number through some type of templating process. So that definitely doesn't seem like it's a very good version or very good solution as well. All right, so now the last thing that we could do is we could use an imperative command to update the image version that the deployment should use. So this is somewhat similar to the last step. It's saying that when we build our image, we would still append on a version number. So like, v1, v2, v3, whatever it is. But then rather than updating our config file, we could immediately run a command after building our image that says to Kubernetes, essentially like, hey, Kubernetes, go find my client deployment and update the version number, I don't know, I'm just making up this command here, update version to v1 or something like that. Now, this is very similar to the previous step in that we are still going to tag our image with a version number, but the downside to this approach is that it's using an imperative command, and it's essentially completely skipping over our config file and keeping our config file up to date with the state of our cluster. So all three of these steps seem like, bad solutions. They don't really seem like they're the best things in the world to solve this problem. I think without a doubt, the first solution over here is definitely very, very bad. I think that this solution right here is definitely a pain in the rear because we are making a change to our config file. And anytime that we're changing our config file, we would probably want to do a git commit, right? We would probably want to commit that new version. Well, the downside to wanting to do that git commit is that, remember, we traditionally only build our versions or build our images with the Docker build command right here when we are in a CI environment, like off on Travis CI. And so we're only on Travis CI when we've already made a git commit. So we're kind of talking about like making a git commit to update the image and then pushing this off to Travis, getting the image built right here, and then simultaneously taking that version number and updating this file and then committing this file too at the same time while we're still on Travis. Now, if that doesn't make sense, that's totally fine. What I'm trying to say is that this step right here, it definitely sounds like it's a good solution, but in practice, it ends up being a tremendous pain in the rear. So that kind of leaves us with solution 3 over here. We're going to use an imperative command. So after we rebuild an image, we are going to tag it with a version number. And then we're going to very specifically reach out to kubectl and tell it to update our deployment with the latest version of the image that we just pushed up to Docker Hub. Now, I know this uses an imperative command, and I just told you how we like to avoid these as much as possible. But again, this is kind of like the best of a bad situation. And I think that you'll see when we eventually deploy our application to a production environment, this ends up being like a pretty reasonable solution. It's not the best solution, but it's pretty reasonable when it really comes down to it. Whew, okay, so this has been a very long section. I apologize for the length, but again, I wanted to make sure it's really clear that this is just a continuous not nice issue to have to deal with, and I wanted to go over some of these possible solutions because these 3 in particular get outlined in this issue thread over here if you decide to read this thing. All right, so with all that in mind, let's take a quick pause right here. We're going to come back to the next section. We're going to learn how we can somehow tag our image with a unique version number when we build it, and then make sure that we can run a command that's going to tell our deployment to update itself with the latest version number available. So quick pause, and we'll come back in the next section. In this section, we're going to walk through the update process that we described at the end of the last section. So here's what we need to do. We're going to first tag our image with a distinct version number, and then we're going to push that new version up to Docker Hub. After that, we're going to run a rather long kubectl command that's going to forcibly update our deployment and tell it to use this new version of the image that we have pushed off to Docker Hub. So let's get to it. Step number 1 is going to be to tag our image. So to get started, I'm going to open up my terminal, and I'm going to create a second terminal window and then change on over to that complex client directory. So I'll go into complex, and I'll change into the client folder. So here's my client project. We have already built an image out of this folder, and we have not made any changes to our project since then. So we could technically do a Docker tag here and tag the existing image that we already built, but instead, just to show you the entire flow, I'm going to build the entire image from scratch again. So I'll run docker build, and I'll tag this thing with my Docker ID / multi-client, and I'll make sure I get a colon on there, and then we have to put some unique token on the other side of the colon. And so for me, as a version number, I'll just do like, I don't know, version 5 or something, anything you want to do. And then after that, I'll put down a period to specify the build context. Okay, so I'll run that command. The image is rebuilt, and it's now tagged with your Docker ID / multi-client :v5. So now we need to make sure that we push this updated image over to Docker Hub. So I'll copy the entire tag right there, and I'll do a Docker push and copy the tag in. All right, so just like that, we now have a new tagged image over on Docker Hub. So now we need to run a kubectl command that's going to force our deployment to use that new image version. Back inside my terminal, I'm going to delete the second terminal window that I opened, and so I'm left just with the original window that is based on the simple k8s directory. So inside of here, we're going to run a rather long command. I've got a quick diagram to tell you a little bit about what we're going to be writing out. All right, so here it is. Yes, it's rather long. So we're going to use kubectl, and we're going to use the set command. We use the set command to update a property on one of our objects that exist inside of our cluster. The specific property that you and I want to update is the image property. So the image property that is tied to our single container right here. After that, we'll specify the type of the object that we want to update. So in our case, we are not updating a container. We're not updating a pod. We are updating a deployment. That's what we're updating. So we're going to specify a deployment / the name of our deployment, which for you and me is client-deployment right there. After that, we'll then specify the container name. So remember, a deployment creates pods, and inside of a pod, we can have many different containers. Our specific pod template right here only has one container, but we could very easily have other containers inside of here as well. And all those other containers would have their own image property. So we need to make sure that we specify which of all of our containers we want to update. And we specify the container that we want to update by specifying the name. So we're going to say the container name, and for us, the container name is client. We'll then do an equal sign, and then the full image that we want to use. So it'll be your Docker ID / multi-client, and then a colon, and then the version number that you use to tag the image with. So that's the entire command. Let's give it a shot. Back inside my terminal, I'm going to run kubectl set image. Then we're going to do our object type, which is a deployment, / the object name, which is client-deployment. Then we'll put in a space. So there's a space there. Notice how it wrapped the line for me, but there definitely, without a doubt, is a space there. And then I'll specify the container that I care about, which is client. And then the update that we're going to make is to say that we now want to use our Docker ID / multi-client. And then the version we want to use is whatever version you just used a second ago when we rebuilt our image. And so for me, it is v5. All right, so that's it. So we're going to run this command. And we get that our image has been updated. So now we can do a kubectl get pods. And you'll notice how we have a single pod here. And most importantly, it has an age of around 5, 6, 7, or however many seconds, which definitely means without a doubt that our pod was just recreated by our deployment. So now we get to test this out inside of our browser to make sure that the update actually went live. So remember, to access our running container, we need our minikube IP. So there's the IP address. And then remember, the port for our application, or for this particular pod, is 31515, as specified inside of our client node port service file. So inside my browser, I'll open up a new tab. I'll put in my IP address, and I'll go to 31515. And then once here, I should see Fib Calculator version 2. Now really quick, if you don't see version 2, do not panic. The React application we put together has some caching built into it. So if you do not see version 2 over here, then the first thing I want you to do is give it a couple seconds and then do a quick refresh. Failing that, try opening up your Chrome console, expand this tab on network right here. You can select disable cache and then try refreshing again. And then if even that doesn't work, you can always run the set, where's that command? The big set image command here again. Try running that a second time. And then after all that, you should be able to eventually refresh this thing and see version 2 appear. Like I said, sometimes it does take a second or two for it to actually pop up the update inside of here, but you should eventually see it go live. All right, so that's it. That's how we update, or how we tell a deployment that we want it to use the newer version of an image. Now, I think you'll agree with me that this entire process is definitely a little bit of a pain, because we have to rebuild the image, we have to apply a unique tag version on it, and then we have to run that command. But when we eventually set up our entire cluster to be deployed off to either Amazon Web Services or Google Cloud, you and I are going to write out a big long script to facilitate our deployment. And inside that script, we're going to put all of this tagging logic and all the version tagging and all the kubectl set image command stuff as well. And so when we eventually move over to a production environment, all this versioning stuff is going to be completely automated for us, and we're not going to have to do any additional work. So it's really just kind of understanding what's going on behind the scenes. That's the challenging part. Once you understand what's happening, from then on out, life gets pretty darn easy. Okay, so that's pretty much it. Let's take a pause right here, and we'll continue in the next section. When we first started talking about pods and deployments about a dozen videos or so ago, you might recall that I opened up my terminal at some point in time, and I told you that I was going to run a series of commands. And I also told you, don't try to run these commands. I told you, don't run these because you're probably going to see an error message or something like that. And so one of the commands that I ran at that point in time was a simple Docker PS. Remember, the Docker PS commands will print out the status of all the different containers that are running on your local machine. So you saw me run this command, and when I did so, there appeared to be a tremendous number of containers running on my local machine. Now, if you open up your terminal right now and you run a Docker PS as well, you're probably only going to see like maybe 0, 1, 2, or 3 local containers. And chances are there are going to be containers that we had started up in previous sections that you never cleaned up or anything like that. So why am I seeing this output right here of all these different containers? And if you look at the name of them, they all appear to be very clearly related to Kubernetes. So why am I seeing all this output right here? And why are you only seeing 1 or 2 or 3? Well, in this section, we're going to investigate this a little bit. We're going to get a better idea of what Docker is doing for us, both on our local computer and inside of that virtual machine that forms our node. And we're going to get a better idea of how we can kind of reach into the node and play around with the copy of Docker inside there. All right, so first off, a couple diagrams. Now we've looked at some variations on this diagram right here a couple times. And we've gone over the process of what happens when we feed in a config file through kubectl a couple times as well. But I want to give you just one more quick reminder of what's going on. So remember, we take a configuration file that wants to create either a pod or a deployment. We feed that into kubectl. That gets passed off to the master, and then the master reaches into the virtual machine and communicates with the copy of Docker that runs only inside of the virtual machine. And it tells it, hey, Docker client, we need to create a new container. Go off and grab this image and create a container out of it. The Docker client then turns around and says to the Docker server, hey, Docker server, we need to go and grab an image and we need to create a container out of it. And so it's then up to the Docker server to reach out to Docker Hub, download an image, store it inside of some local cache, and then build a container out of it. Again, we've gone over this flow several times. Now, something else that we've discussed a couple times is the fact that we have 2 copies of Docker running on your local machine right now. We have the copy of Docker that's running inside of the virtual machine, and we have the copy of Docker that we installed way back at the we ran Docker for Mac or Docker for Windows. That's the copy of Docker that's associated with this status bar dropdown right here. All right, now I want to show you something really interesting. All right, I'm going to flip back over to my terminal, and inside of this terminal window right here, I'm going to run Docker PS again. When I run that, you're going to see, yep, I've got all this output from Docker right here. And now I'm going to open up another terminal window. So here's just another simple terminal window over here, and I'm going to do a Docker PS over here as well. And when I do it over here, it appears that I'm running absolutely no containers whatsoever. So what's going on here? Well, essentially, I have configured Docker inside of these 2 terminal windows to connect to one of these different Docker servers that's running on my local computer. So whenever I type in a command inside my terminal, I'm accessing the copy of Docker client that was set up with Docker for Mac when I installed it way earlier inside this course. My first terminal window over here, this one where I run Docker PS and I see no running containers whatsoever, this copy of the Docker client, or the Docker CLI, is connecting to the Docker server that is running on my local computer. And again, this is the copy of Docker server that was installed with Docker for Mac. In the second terminal window, I bet you can guess what's going on. In the second terminal window over here, I have configured my local copy of Docker client not to connect to my local Docker server. Instead, I have reconfigured it to talk to the copy of Docker server running inside of the virtual machine. So inside of this very specific terminal window right here, when I do a Docker PS, my copy of Docker client, the Docker CLI, is reaching into the virtual machine. It's getting in contact with the copy of Docker server inside there, and it's asking it, hey, what different containers are you running? And so that's why inside of this terminal window right here, I see this big list of Kubernetes related containers, including the multi-client container right here. And again, all these containers are running inside of my virtual machine. All right, so again, the idea here, all I want you to understand right now is that I have 1 copy of Docker client, and between these 2 terminal windows, I have configured it to either talk to my local copy of Docker server or the copy of Docker server that is running inside of the virtual machine. So let's take a quick pause right here. Now that we understand that, when we come back in the next section, I'm going to show you how you can reconfigure your local copy of Docker client to talk to Docker server inside the virtual machine. And of course, I'll also tell you why we would want to do this at all. All right, so quick break, and we'll come back in the next section. In the last section, I showed you how I had multiple terminal windows open, and between the different terminal windows, I had reconfigured my copy of Docker client. And so in this section, I'm going to show you how you can do the same thing, and then we'll talk a little bit about why you would want to do this at all. All right, so here's what we're going to do. Anytime that you want to configure your local copy of the Docker CLI, remember, that's the thing that we are accessing inside of our terminal. This is Docker CLI right here. If you want to reconfigure your copy of Docker CLI to communicate with a copy of Docker server inside of the virtual machine, we're going to run this command right here. So I'm going to copy that command. I'm going to go over to a new terminal window. And over here, when I do a Docker PS, you'll see that I am clearly connected to my local copy of Docker server. Now I'm going to run that command right there. I'll leave it on the screen so you can read it. You can type it inside of your terminal if you want to. So when I run this command right here, it's going to very temporarily reconfigure my copy of Docker client or Docker CLI to connect to the Docker server inside of my Kubernetes node. So after running that command, I can now do a Docker PS, and I'll see the print up from all the different containers that are running inside of my virtual machine. Now, quick note here, and this is an extremely important thing to understand. Anytime that you run that eval command right there, it is a very temporary reconfiguration of your Docker CLI. So when you run this command, it's only going to reconfigure your Docker CLI in your current terminal window. What that means is, right here, if I do a Docker PS, I clearly am working with the reconfigured version of the Docker client, but as soon as I open up a new terminal window, it goes back to its old behavior. So when you run that command, two things to be aware of. First off, it is not a permanent change. You're not permanently reconfiguring your copy of Docker client. The other thing to remember is that if you decide to close down your terminal window, maybe you take a break from Docker or something like that, or you turn off your computer and close all the programs running on it. If for whatever reason you close that terminal window, you have to rerun this command right here to reconfigure your Docker CLI again. All right, so just to really make sure that's very clear, I'm going to show you one more time. I know this is getting a little bit repetitive, but I can just about guarantee you that at some point in time, you're going to run Docker PS and say, hey, wait, why am I not seeing everything inside the virtual machine? So when I run that command and do a Docker PS, I see everything inside of the virtual machine. As soon as I open up a new terminal window and do a Docker PS again, back to old behavior. So throughout the rest of this course, if I ever say to you, hey, let's see what Docker inside the virtual machine is doing, you need to make sure that you first run that command right there. Otherwise, you're not going to be able to look inside of the virtual machine and figure out what the copy of Docker inside there is doing. Now, just in case you're curious about what exactly this command right here is doing, you can actually take just the minikube docker env command right there and run it by itself. When you do so, you'll see that it's actually just exporting a couple of environment variables. So just so you know, whenever you use a Docker CLI command, like say Docker PS right here, when Docker is invoked, it's going to look at a set of environment variables to decide what copy of Docker server it is supposed to connect to and attempt to execute this command on. So when we run this minikube docker env command, with the eval command especially, it's going to set up some new environment variables that are going to tell Docker CLI to reach into the virtual machine to find the copy of Docker server that is supposed to work with. And if you look at this Docker host variable right here, you might even be able to recognize the IP address. It's actually the IP address of your minikube server. For example, if you do minikube IP right now, you'll see it prints out the identical IP address to what we're telling the Docker client to attempt to connect to. All right. Now, one last thing I want to mention here, it's kind of hard to remember this entire command by itself. It's kind of hard to remember this and have to recall it at some point in the future when you want to reconfigure your shell. I found that a very easy way to remember this command is to instead memorize the command minikube docker env by itself. Remember, that's what we just ran 2 seconds ago to print out all those environment variables. When you run just minikube docker env by itself, it will actually tell you, hey, if you want to configure your shell, or essentially your current terminal window, here's what you need to run. And it's the full-length command with the eval on there as well. So a very easy way of memorizing how to do this is not to memorize the eval part, just memorize minikube docker env. That's all you have to remember. And as long as you can remember that, type that in, and then it will tell you exactly what to type right here. So you can copy paste that in, and boom, you're good to go. All right, so that is what is going on when we run that Docker PS and see a listing of all the containers inside the virtual machine. Now, the very last thing I want to tell you is why we would want to do this, right? Why would we ever want to look at the copy of Docker running inside of the virtual machine? Especially since I told you when we first started looking at Kubernetes that you and I as developers do not mess around with the inner workings of the virtual machine. Remember, I told you we don't mess around with the virtual machine ourselves. We leave it up to the master to change the configuration of the virtual machine or change the different containers running inside there. So let's take a quick pause right now. When we come back to the next section, we'll talk about why we might want to reach into this thing and inspect the different containers that are running and kind of mess around with them a little bit. All right, so quick pause, and I'll see you in just a minute. In the last section, we learned how to temporarily reconfigure a single terminal window to access our Docker server running inside the virtual machine. I want to remind you again, you have to rerun that command every single time that you open up a new terminal window. All right, so I'm going to very quickly paste this inside of here just to make sure it's really clear that I'm going to reconfigure my current terminal window right here. Now, I want to talk to you a little bit about why we would want to do this at all. Why would we want to reach into the virtual machine and take a look at the Docker server and all the containers that are running inside there? Well, I put together a couple of reasons that I think you might want to do this. This is not an exhaustive list by any means, so I just want you to have an additional tool in your little toolkit for working with Kubernetes so that you can understand how to kind of get a better idea of how to play around with all this stuff. All right, so a couple of reasons that you might want to mess around with Docker inside of our node. The first reason is that you can use all the same debugging techniques that we had learned much earlier in this course to inspect containers and get logs from them and do all that kind of stuff when you connect to the copy of Docker running inside the node. So for example, remember right here again, I just reconfigured my shell. So I'm going to do a Docker PS. And when I do so, I can scroll all the way back up to the top and get the ID of my multi-client container right here. So I'm going to copy that ID. Now I can get logs out of that container by doing a very classic Docker logs, and then the ID of the container. Remember, this is something we covered way long ago at the very start of the course. Now in this case, our container has not emitted any logs, so I get nothing back here, but I could do other commands as well, such as, say, executing an arbitrary program or a secondary program inside the container. So for example, if I want to start up a shell inside of that container, I could do a docker exec it, then the container ID, and then I'll start up shell inside there. And so when I do that, I can very simply get a shell and I can start to poke around and get a better idea of the state of my container if I want to. Now, the one kind of caveat to this, the one thing I want to mention is that a lot of these different debugging commands are actually available through kubectl as well. So for example, I can still pull logs using kubectl from a very specific container. And I can start up a shell inside of a specific container using kubectl as well. As a very quick example of that, I'll do a kubectl get pods. I'm going to copy the name of my pod right here, and then I'll do a kubectl logs, and I'll paste the name of the pod. And again, I don't get anything back because the container has not emitted any logs, but it definitely would retrieve logs if any had been emitted. I can also do a kubectl exec it, and then the pod name, and then sh on the very end to start up a shell. And so the same thing right here, yeah, I'm starting up a shell using kubectl as well. So again, you can use all the knowledge that you have of Docker to do a lot of debugging. However, a lot of that stuff is already available with kubectl. So I'm going to kind of leave it up to you if you want to figure out how to do this stuff through kubectl, or if you want to just stick with your knowledge that you've already gained of Docker and use those same techniques as well. Now, the next reason that we might want to mess around with Docker inside of our node is so that we can do exactly what I did a little bit ago inside the course, where I manually deleted a container, and then we were able to observe that, oh, hey, it was restarted automatically. So essentially, you can test Kubernetes' ability to self-heal or restart crashed containers or whatever it might be by reaching into there and deleting a container manually. Now, that's not a great reason to do this, but I just want to say it's something that you could possibly do if you felt like it. Now, the other reason that you might do this is that if you're for some reason having a really tough time figuring out why images are being cached inside of your node talking about Docker images here. And if for some reason it feels like you're not able to update the image that a particular container is using, you can always reach into the container, access the copy of Docker inside there, and say, hey, delete your image cache, and just blow away all the cached images that you have. And so to do that, we could run the same command that we had learned way long ago. We can do a docker system prune -a, and this will remove all stop containers, all unused networks, and all build cache, and all images that are not being used at this point. And so I could just blow away everything inside there if for some reason I felt like there was a big caching issue with what was going on inside of my node. Okay, so that's it. That's a couple of reasons on why you would want to mess around with Docker in the node. Now, I just give these to you as like possibilities. Again, I'm rather convinced that you can think of some better reasons than what I've listed here of messing around with Docker inside the node. But again, I just wanted to give you a couple examples to kind of get your brain going and give you a reason to look into this feature a little bit more. All right, so let's take a pause right here and we'll continue in the next section. At this point, I think that we understand some of the core components of the world of Kubernetes. We understand what pods are, what deployments are, and how we can expose pods to the outside world through the use of basic services like the cluster IP service. In this section, we're going to start taking our previous application, so that multi-container app that was calculating Fibonacci values, and we're going to bring it into the world of Kubernetes. We've kind of already been going down that path with this simple K8s folder, right? We've been setting up our multi-client image a little bit and working around with it, but we're now going to start putting a concerted effort together to take that previous multi-container application we had put together and adopt it into a sort of Kubernetes architecture. Now, I've got a diagram that's going to be a high-level overview of the general architecture that we're going to use. So everything that you see here is in a single node. We're going to first develop all this stuff locally. We're going to set up the entire application on our local Kubernetes cluster. After we get this all put together locally, we're then going to deploy it off to a service provider such as AWS or Google Cloud. When we deploy it out there, we will have the option to expand to multiple nodes. So we won't necessarily just be limited to one single virtual machine for all these different objects that we're going to create. But for right now, we're just going to kind of imagine that it's all sitting on one single node. Now, this diagram is showing the general overall architecture that we're going to use for us moving our multi-container app into the world of Kubernetes. You'll notice that there are some very familiar pieces in here. So we've got the multi-client set of pods, all being managed by a deployment. We've got the multi-server. Remember, that's the Express API being managed by a deployment. And then you'll notice that I've also added in Redis as a pod this time around and Postgres as a pod this time around as well. So back on the multi-container deployment on Amazon Web Services, when we used Elastic Beanstalk, we delegated to these outside services provided by AWS to manage our Redis and Postgres needs. But now that we're moving over to Kubernetes, we're going to put these things together in a production environment ourselves, rather than relying upon some outside service to do it for us. The overall purpose of the app is going to stay the same, so it's still going to be all about calculating some Fibonacci values. I know it's kind of a silly example, but it works and it allows us to have a couple of different services that work together in a nice fashion. Now you will notice that inside this diagram, there are a couple of new terms as well. So for example, on the far left-hand side is something called an ingress service. You'll notice that rather than having the node ports on our deployment for multi-client that we had previously, we now have a cluster IP. And it looks like just about every deployment that we put together, with the exception of the multi-worker right here, has a cluster IP kind of somewhat attached to it. So of course, we're going to talk about what an ingress is and what a cluster IP is as well. The other new piece of terminology that you'll notice inside of here is something called a Postgres PVC. PVC stands for Persistent Volume Claim. And of course, we'll talk about what that means when we get to setting up our Postgres stuff as well. All right, so that's the idea. We're going to take our previous application and we're going to move it into the world of Kubernetes. Now here's the general series of steps that we're going to take. So in a development environment, we're going to first create a config file for every last thing that you just saw in that diagram. So we're going to have configuration files for the ingress service, for this cluster IP, for this cluster IP, for this one, and we're going to have config files for every single one of these deployments as well. And we'll also have a config file for this persistent volume claim thing down here too. So in total, we're talking about like 10 or 12 or something like that different config files. It is going to be a lot of typing, but we definitely are going to learn a lot about these configuration files along the way. Now, once we put together all these config files, we're then going to test everything out locally on Minikube. So we're going to make sure that everything works locally first, and we're going to use it as our development environment. We're going to be as kind of as confident as we possibly can that when we eventually push this up to a production environment, everything will work the way we expect. After that, we're going to build a GitHub and Travis deployment flow, very similar to the one we had done previously for both the single container and multi-container applications. But of course, there will be some edits to it to make sure that everything is set up for a Kubernetes deployment as opposed to the rather easy and straightforward Elastic Beanstalk we were doing before. And then, of course, the very last step is to make sure that we can actually deploy this entire thing to a cloud provider like AWS or Google Cloud. And yes, we're going to go through that entire series of steps together and make sure that people can actually visit our application in a meaningful way. All right, so we definitely have our work cut out for us, no two ways about it. So when we come back together in the next section, we're going to flip back over to our complex multi-container project, and we're going to start setting up config files for everything inside of here. So quick break, and I'll see you in just a minute. In the last section, we spoke about how we're going to take our multi-container project and update it to use Kubernetes as opposed to the Docker Compose or Elastic Beanstalk setup that it currently has. Now you will notice that in the last lecture, I posted the zip file for the complex project. I put it there just in case you made any changes to the project. That is a backup of my exact files as they stand right now. So I took my exact complex folder directory with the server, the client, the worker, the whole 9 yards, and I put it into that zip file. So again, if you made any changes to the project whatsoever between the last video that we were working on it and right now, I highly encourage you to download that zip file and use that as the starting point for all this Kubernetes stuff. Now in this section, we're going to take the complex project or the multi-container project, and we're going to start it up with Docker Compose. The reason that we're going to do this is to just make sure that everything is still working the way we expect. Because if we start building out all this Kubernetes stuff, but some of the underlying project code got changed by you at some point in time, or it's in a broken state, doing the Kubernetes stuff is going to be basically impossible, completely impossible. So we just need to make sure that the code that you're using and the code that I'm using is still working and 100% up to date. All right, so you'll notice that I'm inside of my complex project folder right here. The other thing that I want you to triple check, make sure that you are not using a copy of Docker that has been configured to run inside of or to access the Docker server inside of your node. So you can very easily do that by doing a Docker PS. And you should see that you have very few or absolutely no containers running whatsoever. If you see a ton of printout, that means that your Docker client is still configured to access the Docker server inside the node. We do not want to start up Docker Compose inside of the node whatsoever. If you are still using the updated copy of Docker or the reconfigured version, remember all you have to do to get back to the non-configured version is open up a new terminal window. That's pretty much it. Just open a new terminal window and do a Docker PS again, and you'll be back to using your local copy of Docker server. Okay, so again, I'm inside of my multi-container project directory. I see the docker compose.yaml file right here. I'm going to run Docker Compose up and rebuild all these images. And again, we're just doing this to make sure that all of the existing code works as we expect. So I'm going to do a Docker Compose up -- build because I want to explicitly rebuild everything. And I'm going to let that run. It's going to take a couple minutes to rebuild everything and launch it all. Now you'll notice in my case, I kind of just very recently rebuilt all this stuff, so it launches very quickly. I do want to remind you that the very first time you launch all these containers, if you cleared out all the cached version of the containers and whatnot, it might crash a little bit the very first time you launch it. So I do encourage you to stop Docker Compose immediately after it starts up and do a Docker Compose up a second time. And the second time, you don't need to add on the -- build flag. All right, so I'm going to launch that. I'm going to wait just a second for the development server to start up. And then you'll recall that we can access all this stuff on localhost port 3050. I already opened up my code editor inside that complex directory. Here's the Docker Compose file. Here's the Nginx server that we are using for routing inside of our application. And you'll recall that we had set up localhost 3050 as being the central point to access everything inside of here. So I'm just going to very quickly test this out by opening up my browser and going to localhost 3050. And again, I should still see all of my numbers here, any previous values that I had entered, unless you had, of course, deleted or completely stopped and deleted the Redis and the Postgres containers. And just to make sure that everything's working the way I expect, I'm going to enter in a new index here of 12. I'm going to submit it. I'll then refresh, and I'll see 12 added here, and I'll see a calculated value for 12 down there as well. Okay, so hopefully you see something like this. Again, if you don't see everything updated and still working like so, then I really encourage you to go back to the previous lecture, download that zip file, and use that as the starting point for all this Kubernetes stuff, just to make sure that you and I are on 100% equal footing. Okay, so let's take a pause right here. When we come back to the next section, we'll get started with taking all of our existing images and migrating them into the world of Kubernetes. So quick break, and I'll see you in just a minute. In the last section, we tested out our multi-container application with Docker Compose just to make sure that everything was still working the way we expect. I'm now going to close down Docker Compose and return back to the command line. Now from this section on, we're going to start to make changes to our project inside of the complex directory. So if you want to keep a record of all the stuff that we had done for Elastic Beanstalk and for Docker Compose and whatnot, feel free to make a backup of this folder right now. I, in particular, already made a copy of this folder. I made a copy and called it Complex Elastic Beanstalk, just to serve as a backup of sorts. Now, of course, I can rely upon Git as a backup as well, just to make it easy for you to refer to all of my code at some point in the future. I made the easy backup folder right here. All right, so I'm going to go back into the complex directory, and then I'm going to start up my code editor inside this folder. Now we're going to first begin by cleaning up our project directory a little bit. We're going to delete some of the different files and folders that are not going to be required for this new Kubernetes version of this application. So the first thing I'm going to do is find the travis.yaml file, the Docker Compose, and the Docker run files. And I'm going to delete all three of those. We do not need these files anymore because we're going to rely upon Kubernetes to run our application both in a development and production environment. And for the travis.yaml file, we're going to essentially recreate that thing from scratch when we eventually try to take this application to Travis again. Now I'm also going to delete the nginx folder. We previously had a nginx image to serve as kind of the primary routing inside of our entire cluster of containers, but now for routing, we're going to rely upon something called the ingress service, which we're going to talk about at great length in a little bit, but for right now, just know that we don't need this nginx image anymore. So I'm going to delete that thing as well. All right, so now I have just client, server, and worker, and nothing else. Now the first thing I'm going to do is create a new folder inside of here called K8s, like so, and we're going to use this folder to house all of the different configuration files that we're going to create for our project. In total, we're going to have one separate configuration file for each of these different objects that you see on the screen. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 configuration files. Yeah, that's a lot, but hey, we'll get through it. So let's first begin by putting together a configuration file to create our multi-client deployment. We've already put together a configuration file for this on the project we were just working on a second ago as we were first learning Kubernetes, but we're just going to recreate the thing from scratch right now just to get some of the common typing that we have to do inside of our head. All right, so inside of my K8s folder, I'm going to make a new file called client-deployment.yaml. And then inside of here, we'll put together all the configuration required to create this deployment with 3 child pods running the multi-client image. So at the very top, we'll start off by designating the API version that we want to use, which is going to be apps v1. We'll specify the kind of object that we're going to create inside of this file. It's going to be a deployment. And then we'll add on some metadata, in this case, just the name of the deployment. And it's going to be our client deployment. Next up, we'll add a spec that's going to configure this deployment. So we're going to say that we want 3 replicas of the multi-client image, or really the multi-client pod running. And we want those 3 replicas to be managed by this deployment. After that, we'll put down our selector. I'll say match labels, and then I'm going to use the same key value pair as a label that we had used previously, which is to say component web. In other words, this means that the component of our application that this deployment is going to be managing is the web or front end side of things. After that, we'll specify the pod template. Now remember, the template right here is going to be on the same indentation layer as the selector above it. So for the template, I'll provide some metadata that will provide a label of component web. Remember, the selector out here and the label inside the template is how the deployment is going to identify the different pods that it's supposed to manage. Next up, we're going to add a spec. And again, this is going to be on the same indentation level as metadata. And then we'll specify all the different containers that are going to run inside this pod. In this case, we have just one container. It's going to have a name of client. The image we want it to use will be your Docker ID, multi-client. And then finally, we'll specify a port to open. We'll use a container port of 3000. And that's going to be the port that is mapped up to the multi-client image. All right. So that's pretty much it for our client deployment. Let's take a quick pause right now. When we come back in the next section, we're going to very quickly put together a new configuration file for this service right here. And we'll talk a little bit about exactly what a cluster IP is, because previously we had only used a node port. So quick break, and I'll see you in just a minute. In the last section, we put together our multi-client deployment config file. Now, we had already written out all the configuration for this before, and it's essentially a clone of what we already had. But again, I just wanted you to get used to some of the pieces of terminology inside of here, because you're going to be writing quite a bit of these configuration files over time. All right, so now that we've got the deployment put together, we're going to start working on the cluster IP service. You will recall that the previous deployment we had worked on used a node port service. So the first thing we're going to do is figure out exactly what a cluster IP is. All right, so first off, I want you to recall that in the world of Kubernetes, we use a service anytime that we want to set up some networking for an object, such as a single pod or a group of pods that are managed by a deployment. Now, we made use of a node port, which is going to expose a single pod or a cluster of pods to the outside world. And that's why you and I were able to type in a IP, or specifically the IP for our Minikube virtual machine, and then a port in the 30,000 range. It was completely the node port that allowed us to access our running pod inside of our browser. Now, the cluster IP is a little bit more restrictive form of networking. The cluster IP is going to allow any other object inside of our cluster to access the object that the cluster IP is pointing at. But nobody from the outside world, so in other words, people like you and me or anyone inside their web browser, can access the object that the service is married up to or pointing to. So what does that mean practically? Well, it means that when we assign a cluster IP to any of these deployments that you see here, anything else running inside of our cluster can access whatever object the cluster IP is pointing at. So in other words, this cluster IP right here is going to provide access for everything else inside of here to the Redis deployment. It's what's going to allow the multi-worker pod to eventually connect to the copy of Redis that it's running here. If we did not have this cluster IP service, then the Redis pod would be completely unreachable, and nothing inside of our cluster would be allowed to access that running pod. So that's what the cluster IP is all about. It provides access to an object, most commonly a set of pods, to everything else inside of our cluster. Now, the one thing I want to be really clear about is that a cluster IP is not like a node port in that it does not allow traffic to come in from the outside world. So this right here, this would not be allowed. This does not work. We cannot use a cluster IP to get access to a deployment from outside of our cluster. All right, so that's what a cluster IP is for. In general, we're going to use cluster IPs anytime that we have a service that is, or excuse me, not a service, but an object that is only supposed to be accessed from people already inside of our cluster. Now, the one thing that you will notice is that, of course, we want the multi-client and the multi-server to be accessible from our users, but the way that is going to happen is through the ingress service. Traffic is going to come into this ingress, and then once traffic has come in, it is then effectively inside of our cluster. And so from that point on, our cluster IPs will be accessible only through the ingress service. We'll talk more about the ingress service later on because obviously that's a totally different piece of networking that we have to put together. Okay, so that's pretty much it on cluster IP. Let's take a quick pause right now. When we come back in the next section, we'll put together our config file to create a cluster IP for our multi-client deployment. In the last section, we spoke about the purpose of a cluster IP service. So we're now going to flip over to our code editor and create a new config file that's going to expose access to our set of multi-client pods to every other object inside of our cluster. So over inside of my code editor, I'm going to find my K8s directory, and I'm going to make a new file called client cluster IP service.yaml. Then inside of here, we'll put together a little bit of configuration that's going to look very similar to the config file for the previous service we had created. One was the node port. This one is a cluster IP. At the end of the day, their config files look awfully similar. All right, so inside of here, we'll first start off with an API version of v1. We're going to create an object with a type of service. For our metadata, we're going to provide a name of client cluster IP service. And then for our spec, that's going to configure the way that this service behaves, we're going to specify a type of service of cluster IP. And take note of the capitalization here. We got capital C and capital IP on the end. Next, we need to provide a selector so that this service that we are creating knows what set of pods it is supposed to be providing access to. So in our case, the cluster IP that we are working on right now is going to provide access to our multi-client set of pods. So I need to make sure that we provide a selector, so a selector that's going to properly select our client deployment. If you look inside of our client deployment, you will recall that all of those pods have a label applied to them of component web. So the selector inside of our service will be component web. Finally, we're going to configure the different ports that the cluster IP service are going to expose and be available on. Now the ports rule down here is going to follow the exact same nomenclature as the node port stuff that we had worked on previously. So you remember looking at this diagram, this was the nomenclature that we had for the node port service. So with the node port, we had to provide a port, a target port, and a node port. And each of those different properties had a slightly different purpose. Now in the case of a cluster IP, which is what we're making here, there is no node port property because this cluster IP is not addressable or accessible from the outside world. We are only going to have a port and a target port. The port property is going to be how other pods or other objects inside of our cluster are going to access the pod that we are kind of governing access to. And the target port is going to be the port on the target pod that we are providing access to. So for us, we're going to provide a port of 3000 and a target port of 3000. Now you'll notice that I just left these things here the same. If we wanted to, we could say that you can get access to port 3000 inside that container by trying to access something like, I don't know, 3050 if we wanted to. So now if any outside object wanted to access the multi-client pods, they would have to try to go through port 3050. But honestly, I can't think of any good reason in this particular case that I would want to do some mismatching of ports here. So I'm just going to leave them as the same and say that to get at port 3000 inside the container, you're going to get at port 3000 on the service. So if you want to, you can kind of do some redirecting of ports here, but again, I don't really see a good reason to in this particular case. All right, so that's it for our cluster IP service. So let's take a quick pause right here, and we'll continue with our next deployment in the next section. Rather than moving on to our next config file, I think that it would be kind of nice to take these two config files we just put together and load them up into Kubernetes, just to make sure that everything that we've done so far is on the level and that we don't have any typos or anything like that in there. Now, I do want to remind you that when we load up both these config files through the kubectl apply command, we're not going to be able to very easily test out the multi-client deployment or the client deployment right here, just because the service that is governing access to it is not allowing outside traffic. So we will not be able to test this out inside of our browser just yet, but we can at least start up the deployment and look at it in kubectl and say, okay, our pods are actually running. So let's get to it. We're going to load up both these config files right here. Now, the first thing I want to do is to make sure that we delete our old deployment, the previous deployment that we had put together as we were first learning a lot of this stuff. So to delete the old deployment, I'm going to list it out with kubectl get deployments, and then I will delete it with kubectl delete client deployment, or excuse me, delete deployment client deployment. There we go. Again, we list out delete, the type of object we want to delete, and then the name of the thing that we want to delete. So I'll run that. Now I can do a kubectl get deployments, and node resources are found. Now don't forget, we had also created a service as well. It was a node port that was providing access to the set of pods that were created by that deployment. So to get a list of all the services we have created, I'll do kubectl get services. And now we can very easily see that, yes, there is in fact the client node port there. So we can delete this thing in a very similar fashion. I'll do kubectl delete service client node port, like so. Oops, typo there. There we go. So now if I do another get services, I'm only going to see the original Kubernetes service. And again, we're not touching that. That's something internal to Kubernetes, and we don't need to mess around with it at all. All right, so now we're ready to apply those two config files. Now, we could use the same technique that we had previously used for loading up config files, where we did something like kubectl apply -f. And then remember, we're currently inside the complex folder, but all of our config files are inside of K8s. So we could do something like K8s, and then, what was the first one called? Client deployment. But there's actually a little shortcut that we can use anytime that we want to apply a group of configuration files. So rather than spelling out the entire path right here, I'm going to instead confirm that the K8s directory is right there, and then I can apply every file inside there with apply-f, and I'm just going to provide the K8s directory. When I do this, kubectl is going to look into that folder. It's going to find every config file in there, and it's going to apply all of them at the same time. So if I run that, I'm going to see that we have both IP service created, and in the case of the deployment file, it looks like I probably made a little typo at some point in time. Let's check that out really quickly. See inside there, I said metadata label. Oops, it should be labels, plural, like so. So I'm just going to make that very quick change. And then if I try applying that thing again, I get both of them created. Well, at least the first one was unchanged, but the second one was created. So now we can do a kubectl get deployments, and we'll see that we have 3 pods created tied to our client deployment. And of course, if we do a get pods, we'll see all 3 of those different pods running. Finally, we can do a services, and we'll see that we have the cluster IP service created for our client as well. Cool. So we're going to make use of this kubectl apply on an entire directory quite a bit, since you and I have like 11 different configuration files at least to manage throughout this application. All right, so let's take a quick pause right here, and we'll continue in the next section. In the last couple of sections, we finished up our deployment configuration file and the new cluster IP service to go along with it. We're now going to continue by putting together 2 more almost identical configuration files, this time all centered around our Express API, or the multi-server image. Now we're going to make sure that we do a very similar cluster IP service this time around, because we do not want the Express API to be directly accessible from the outside world, as would normally be the case with a node port service. Remember, we use the cluster IP anytime that we want to make a set of pods only accessible to other things inside of our node. The ingress service that we're going to eventually put together qualifies as another thing inside of our node. All right, so one quick thing I want to remind you about here is that our multi-server image is always going to be listening for incoming requests on port 5000. And that was something that we had really hard-coded into the image itself and the actual server that's running inside there. So when we create our cluster IP service, we're going to make sure that it's going to forward traffic onto port 5000 on each of those different pods. And again, just to keep each port the same on both sides, we're going to say that you can access the cluster IP by accessing 5000 as well. Just as I said previously, there's really not a great reason at first glance to, like, for some reason, change the port that the cluster IP accepts traffic on. So we're going to make sure that it's 5,000 in both cases. All right, so let's get to it. I'm going to flip back over to my code editor. Inside of my K8s directory, I'm going to make a new file, and I'm going to call this server-deployment.yaml. And then inside of here, we're going to put together some configuration that's going to look very, very similar to what we did in our client deployment just a moment ago. So we're again going to say API version, apps v1. We're going to have a type of deployment. For our metadata, we will provide a name of server deployment. And then we'll start to add on the spec that's going to customize exactly how this deployment behaves. So for my replicas, let's make sure we got the spelling correct. Again, this is the number of different pods that we're going to set up. We're just going to arbitrarily say that we want 3 pods running the multi-server image. We don't really know a whole lot about how to most appropriately scale these sets of pods yet. So maybe 3 is a good place to start. Maybe it's not. I don't know. We'll find it out when we actually deploy this thing and start to test our cluster with a little bit of traffic. Next up, we're going to specify the selector that the deployment is going to use to find the set of pods that it's supposed to control. So we're going to say that we want to match a set of labels, and then again we'll do a component, but this time rather than doing web as the value for the component key, I'll do server, like so. And so this is very clearly indicating that the component inside of our application that we are working on right here is the server. I want to remind you that the labels we put together can be anything you can possibly imagine. So we could just as easily do something like part of app API or something like that. But I personally enjoy this kind of component and then piece of the application terminology. I think that it's rather clear what this key value pair is indicating. Okay, so now that we got that put together, we're going to go back out in indentation to be on the same indentation layer as the selector and replicas, and then we will put together our pod template. So we'll first begin with our metadata that's going to specify our set of labels. And again, the labels that we apply to this thing must at least match up with whatever we put inside of the spec for the deployment itself. So for labels, I'll say component server, like so. All right, I'm going to indent back out a little bit more. So now I am on the same indentation level as metadata, and we're going to provide the spec that's going to customize the exact behavior of each of the pods that gets created. Now we're going to again provide a list of containers that this pod is supposed to run. Just as before, we are only going to have one single container inside of this pod. We don't have any other containers that need to run along with the multi-server image. So I'll give a name of server. The image is going to be my Docker ID / multi-server. And then the last thing that we're going to do for right now is to add on the list of ports that we want to make available. So for ports, I'm going to say that we want to have a container port accessible of 5,000, like so. All right, now I want to give you a quick reminder. The multi-server image that we put together does expect to get a handful of key value pairs along with it, or environment variables, that tells the multi-server or the Express API exactly how to connect to our Postgres instance and the Redis instance as well. So everything that we put together inside this file at this point in time is definitely stuff we have to add in here, but we are going to eventually come back and add on a series of environment variables that we want to make sure get injected into the container that is created with this image. And remember, the entire goal of that is that we're going to tell the Express API how to connect to Postgres and Redis. All right, so we are going to come back to this file, but for right now, I want to just focus on finishing up this very specific piece of our application setup for right now. And I don't want to think just yet about how we're going to involve Redis and Postgres in here just yet. Okay, so let's take a quick pause right here. When we come back to the next section, we're going to put together our configuration file for the cluster IP service. So quick pause and I'll see you in just a minute. In the last section, we put together our deployment file for the multi-server set of pods, and we made sure that we specified that port 5000 should be accessible on the image that gets created inside of each of those pods. So we're now going to create a second configuration file that's going to serve as what's going to create and maintain the cluster IP service. So I'm going to, again, flip back over to my code editor, and inside of my K8s directory, I'm going to put together a new file that I will call server cluster IP service.yaml. All right, and I'm gonna, or actually I don't need to. I was gonna say I was gonna type out the name of the file right here just so you can see the whole thing, but you can actually see the whole name right here on the tab inside of my code editor, just in case you want to reference the exact name that I'm using. All right, so inside of here, we're going to put together another config file for a service of type cluster IP. This is, again, going to be just about identical to the previous cluster IP service we put together, but let's go through typing it all out again just to kind of commit this stuff to memory. It'll be pretty quick. So I'm going to provide an API version of v1. I'll provide a kind of service. For our metadata, we're going to specify the name of this service or this object, and I'm going to use a name of server cluster IP service, like so. And then we will provide a spec that's going to customize exactly how this server behaves, or excuse me, how this service behaves. So we're going to specify a type of service of cluster IP, and then we need to provide a selector that's going to tell this service exactly what set of pods it's supposed to provide access to. And so, of course, the cluster IP that we're putting together right now is supposed to provide access to all the multi-server pods. In just the last section, when we put together the server deployment file, we had assigned each of those pods a label of component server. And so inside of our server cluster IP service, we're going to want to specify a selector of component server. So back over here, I'll provide a selector of component server. And then finally, very similar to what we did last time, we're going to make sure that we specify the ports that this service is going to kind of mitigate control over or manage control over. So just as before, we're going to just send everything through. And as a reminder, the multi-server image listens for traffic on port 5000. So we're going to provide our ports with a port of 5000 and a target port of 5000 as well, just as we did inside of our previous service. Okay, so that's it. That's all we have to do to put together our cluster IP service that's going to govern or manage access to our running Express API. So let's take a quick pause right here. I want to address one little side topic, and then we'll continue with a couple more config files for the rest of all the objects inside of our application. So quick pause, and I'll see you in just a minute. When we first started working on taking our multi-container application and importing it into the world of Kubernetes a couple sections ago, I had told you that we were going to create one separate configuration file for every object that you see in this diagram right here. I think in total we had something like 11 or so. So that means that we're going to have 11 separate files sitting inside of this K8s directory, and each one of those separate files is going to create a separate piece or a separate object that's going to be running inside of our overall cluster. Now, at some point in time, it might seem like having to work with all of these different configuration files might be a little bit overwhelming. Everything that we've done up to this point has very clearly said that we're going to make a separate file for each object. But if it feels like that's just too many files for you to have to kind of manage and deal with, I want to tell you about one different way in which you can organize all of these different configuration files. So, rather than putting a separate file for every separate object we create, we can actually combine different sets of configuration down into a single file. So as an alternative way of organizing your config files, rather than saying, okay, I need a file for cluster IP and a file for deployment, we actually can create one single file that contains all the configuration for both a cluster IP or a service and the deployment that it is associated with. There's no limit to the number of different pieces of config that we can stick into a single file, so you do not necessarily have to say, oh, this service is going to be in the same file as this deployment. We could just as easily say one single file is going to hold all the config for both these services and both these deployments. I'm going to give you a very quick example of how you would combine these different config files together, and then I'll tell you why we are not doing that inside this course. Okay, so let's say, for example, that we want to kind of co-locate all the configuration for our deployments and services that are tied to each one. So in other words, we might want to kind of consolidate the server cluster IP service and the server deployment config files down to one single file. So to do so, I could create a new file inside my K8s directory, and I'll call it something like, I don't know, server config or something like that. So server config.yaml. Then inside of here, I'm going to go back over to my deployment for the server. I'm going to copy this entire thing, and then I'll paste it inside of the server config file that I just created. And then likewise, I'm going to go back over to the cluster IP service for the server that we just put together a second ago. I'll copy this entire thing, and I'll pull it over to the server config.yaml file. And then down at the very bottom here, I'm going to put down // or not slashes, but dashes, I suppose. So 3 dashes in a row like so. And then after that, I can paste in all the configuration for the other object that I'm trying to create. So essentially, anytime that you want to kind of condense down all this config and put multiple objects worth of configuration inside of a single file, you're just going to paste everything inside of here and separate each one with the -- like so. Now, for some of you watching this video, you might think, oh, that's great. I can make a single file that houses everything that's related to this piece of my application right here. But others of you might be thinking, well, how would I ever know where the configuration for this service is located? I would have to very actively understand that every service is tied to the related deployment. Now, that's really a question of preference. You don't have to co-locate all this configuration. I personally think that it makes a ton of sense to separate all the configuration out into separate files, as we are doing right now, because it very clearly tells you how many different objects exist in your entire cluster, and the naming scheme that we're using right now also makes it extremely clear where the configuration for any given object can be found. For example, if you put this diagram or a diagram like this right here inside the README of your project, and another engineer comes and works on your project and says, oh, I need to change a port related to the cluster IP service for the multi-client pod, they could very easily look at your list of config files right here and say, okay, client cluster IP service, well, of course, the configuration for that thing is going to be inside this file. And they instantly know where to look to find the configuration for any given object. If it wasn't for that, if you had combined everything into kind of single files or condensed everything down, they would have to understand that this cluster IP service and the deployment for the multi-client pods are in the same file. And so you would have to have some naming terminology for all of your config files that makes it really clear that some particular file contains all the configuration for the multi-client pods, its deployment, and the service related to it as well. And so it's a little bit harder to come up with a naming scheme or a naming convention that makes it really clear that, hey, everything related to multi-client is inside of XYZ file. Now, that's just my take. As I said, half of you might think that combining this stuff down into a single file makes a lot of sense, and the other half of you might think, no, that doesn't make any sense at all. I want to do everything inside of separate files. So like I said, I prefer to keep everything in separate files, but for you, totally up to you. Of course, throughout the rest of this course, I really recommend that you follow the same strategy as I and use a separate config file for each separate object. Okay, so that's my spiel on combining together config. Now I am going to delete the server config YAML file I just created because I had only made that as a very quick example to show you how to combine stuff together. So I'm going to make sure that I delete that file, and I'm now left with just 4 configuration files, the 2 client ones and the 2 server ones. All right, so let's take a quick pause right here and continue in the next section with our next piece of configuration. In this section, we're going to very quickly put the configuration together for our multi-worker deployment. After that, we're going to make sure that we take all of our different config files that we've put together and throw them all back into kubectl through that apply command and just get kind of a general idea of where all of our work is at. So let's put the configuration together for the multi-worker pod. As you might guess, this file is going to look very similar to the config that we put together for the other 2 deployments. So inside my K8s directory, I'm going to make a new file called worker deployment.yaml. Then inside of here, we'll put together config very similar to the other deployments. We'll say API version is going to be apps v1. The kind of object that we are creating is a deployment. We'll give a metadata section to this thing with a name of worker-deployment. And then we'll provide a spec to this thing as well. So for replicas, we're going to start off with just a single replica or a single pod running the multi-worker image. Remember that if there's anything inside of our application that really needs to scale out and have multiple instances, it probably is the multi-worker, because that was the image or the container inside of our application that was doing that Fibonacci calculation, and that was the absolutely slowest part of our entire application. And so at one point in time, or at some point in time, we might want to come back and put a little bit more work into that thing to make sure that it is scaled properly. But for right now, we're going to start off with just a single replica so that we can eventually see that, yeah, this thing needs to be scaled, and we can figure out how to do that at that point in time. All right, so after that, we'll provide our selector. We'll say that we want to attempt to match a label on some other object inside of our cluster. And for this one, we'll give a component of worker, because that's really its job. It is a worker container inside of our application. After that, we'll put together our template for the pods that are created. Remember that the template property goes on the same indentation layer as selector. We'll provide a metadata to the template where we'll provide the different labels that need to be applied to every pod that gets created. And of course, we're going to provide a label that matches the selector that we had specified just a second ago. So under labels, I'll say component worker. After that, I'll unindent back out to the metadata section, or metadata kind of indentation layer, I suppose, and we'll provide a spec that's going to configure exactly what this pod is running. So we're going to say that we want to run a single container, but remember, it is plural, containers like so. And then the single container that we want to run is going to have a name of worker. It's going to use the image of your Docker ID, multi-worker. And then just as before, we are going to eventually need to stuff in some environment variables into this thing to tell it how to connect to Redis. But for right now, we're just going to kind of ignore that for a second. We're going to first set up Redis and make sure that's working correctly. And then we're going to come back to both our worker and Express API deployments and add in the environment variables at that point in time. Now, the other thing I want to mention here is if you look at this diagram, remember there is nothing inside of our worker image or the worker container that's running here that needs to be accessible from anything else inside of our cluster. In other words, there's no other object whatsoever, no other service, no other image, no container, no nothing that needs to directly connect to the multi-worker and try to get some information out of it. The multi-worker is going to connect to something else inside of our application, but nothing is going to make an unprompted request into the multi-worker. And as such, the multi-worker does not need to have any port assigned to it, and it does not need to have any service assigned to it either. We only make use of services when we want to have requests going into a set of pods, or into a single pod for that matter. And because that's not the case here, no need for a service, no need to worry about any ports. Okay, so with that in mind, that's pretty much it for this file. No ports required. So we're just going to finish it off like so, and we do not need to create an associated service file. So let's save this as is. We'll take a quick pause right here, and when we come back in the next section, we're going to take the 3 config files that we just put together in the last couple of videos and throw them into kubectl through the apply command. So quick break, and I'll see you in just a minute. In the last couple of videos, we put together a set of 3 different config files, so 1 for the worker and 2 for our server. We're now going to flip back over to our command line and use kubectl apply to take those 3 new config files and apply them to our cluster. We're just going to make sure that there's no distinct error messages or that we didn't make any big typos or anything like that. Now, when we launch these different deployments, it's entirely possible that they're just going to crash and burn because we have not yet set up any environment variables to tell the worker or the server how to connect to Redis or Postgres, because we haven't even set those things up yet. So if the deployments or the pods that they are running just crash and burn horribly, that's totally fine. What we're doing right now is just checking to see if we have any typos or anything like that. So I'm going to flip over to my terminal. I'm going to make sure that I'm inside of my complex directory, and then I'm going to apply the entire K8s directory again. So remember, we do not need to pass in 1 file at a time. We can pass in a whole directory. When we apply that directory, we're also going to be reapplying the 2 client files that we had already applied previously, but that's totally okay, because remember, when Kubernetes gets a config file, it's going to look at the name of the object we're trying to create and its type. And if an object inside of our cluster already exists with the same name and the type, an additional object will not be created. Kubernetes is just going to try to update that existing object if there's any difference inside of the config file. So what I mean to say by all this is that whenever we make a change to our config file, or anytime that we create a new one or whatever it might be, we can pretty safely just take the entire k8s directory and apply everything in there and generally be okay. Now, there definitely are some side effects to that later on when we start adding in a couple more advanced objects that we're going to do much later in the course. But at least for right now, when we're only working with deployments and services, kind of free form, you can just throw everything inside of your config directory into kubectl and you're going to be okay. All right, so enough talking. We're going to do kubectl apply f k8s, like so. Now you'll notice that Kubernetes very correctly noticed that there are already 2 objects inside the cluster with the type and name of both these services right here, or both those objects, and the config associated with both of them has not been changed by any stretch of the imagination. So those are totally unchanged. However, the 3 other objects here are being created. Let's now do a kubectl get pods. And so we will see a list of all the different pods that have been created. It looks like we have the server and the worker running here successfully. So even though I kind of thought that they were going to crash and burn, it looks like they're doing okay. We can do a get deployments and see that we now have a total of 3 deployments. And then finally, we can do a get services and see that we have both the original client cluster IP service and the new server cluster IP service. Now, as a quick reminder, we could very quickly use the kubectl logs command to try to pull some logging information out of these new pods and kind of get a better sense of whether or not they are working correctly. We could also choose to reconfigure our Docker client to directly access the containers that are running the multi-server and the multi-worker images and pull logs that way. It's totally up to you. But just because it's a little bit easier, I'm going to pull logs using the kubectl CLI. So I'll first print out my list of pods again, and then I'll just take the name of one of these random one of the random pods right here. I saw the word deployment and confused myself for a second, but we're good. So I'm going to take the name right there, I'm going to copy it, and then I'll do a kubectl logs, and then the name like so. All right, so we can see that in fact, Node.js was executed, and that is our default npm start command. That's what we expect to see. But then very shortly after that, we saw a refuse to connect right here. Now, the refuse to connect is coming directly from us trying to connect to Redis, but no copy of Redis is available. You'll notice that it did default to using port 5432. It only defaulted to that because the Redis library that we are using inside of that image defaults to use port 5432. So even though we didn't specify a port yet for this server to connect to, it just defaulted to 5432. And of course, when we eventually add in an environment variable to specify the port, even though it has a default, we're still going to make sure that we very directly and distinctly say it's supposed to be port 5432. All right, so it looks like everything is running as well as can be expected. So we're going to take another quick break right here. When we come back to the next section, we'll put together another set of config files for Redis, and then we'll eventually move on to Postgres as well. So quick pause, and I'll see you in just a minute. In this section, I've got some really good news and some bad news. So the good news is that we get to put together our configuration for the Redis deployment that's going to manage a single Redis pod. The bad news is that that means we have to write out 2 more configuration files, very similar to the ones we've already put together. So I know writing out all these configuration files is getting very tedious, but we're almost at the end here. We just have to do the Redis deployment, its cluster IP service, and then the same thing for Postgres and its service as well. And then after that, we're done with these very repetitive config files, and we get to look at some more interesting config files that are going to do some more interesting things inside of our cluster. So let's get to it. We're going to create our deployment config file for Redis and its associated cluster IP service. All right, inside of my code editor, I'll find my k8s directory, and inside there, I'll make a new file called redis deployment.yaml. So we're going to start off first with the deployment. Now, the deployment that we're going to put together is going to look essentially identical to the other ones that we've already written so far. So let's get through it as quickly as we can, but do make sure that you type out everything correctly because any little typo is going to eventually result in some error message down the line. All right, so I'll do an API version of apps v1. I'll give this object a type of deployment. I'll set up a metadata that's going to provide a name of Redis deployment, And then we'll start putting together some configuration that's going to exactly configure how the deployment is created and how it behaves. So for my spec, I'm going to give a replicas of 1. We only want to have one single copy of Redis at any given time. Now, Redis is very interesting in that we can set it up in a sort of cluster mode where there will be multiple copies of Redis that kind of communicate with each other and enhance the overall stability and throughput of our application. But this is, of course, much more about Kubernetes than it is about Redis. So we're not going to worry about setting up Redis in any sort of like cluster mode or anything like that. So we're just going to have one standalone copy of Redis. All right, we'll also give it a selector. It's going to look for any set of pods out there that has a label of component Redis. I'll then unindent back out to be on the same indentation level as selector, and we'll provide our pod template. So for the pod template, we want to give it some metadata. Notably, we want it to have a set of labels of component Redis, like so. I'm then going to unindent again so that I'm on the same indentation level as metadata, and we'll provide the pod a spec. So it's going to have a single container, but remember the keyword right here is containers, plural, even though we only have one. So we'll give this thing a name of Redis. It's going to use the image Redis. No Docker ID required this time, like your Docker ID / because we don't have our own custom version of Redis. We are using the copy that is included in the public repository over on Docker Hub. We'll then set up the different ports that need to be mapped to the container. In the case of Redis, the default port that it uses is 6379. And there's really no good reason for us to try to change that. Totally fine to use the default port. So I'll set up a container port of 6379, like so. All right, again, I got to ask you, please double check all the indentation and all the spelling inside this file, because if anything inside of here is wrong, like any little typo whatsoever is going to eventually result in an error message. Like literally, if I change anything inside of here, like if I delete a P in component or something like that, something down the line is not going to work as expected. So please double check your spelling inside this file. All right, so that's the deployment. So we're now going to create a cluster IP so that our server pods and the multi-worker pod can eventually connect to this Redis instance that's running inside of the pod, inside of a container, inside of the pod. So back inside of my code editor, I'll find my K8s directory. I'm going to make a new file called Redis cluster IP service.yaml. And then inside of here, we'll put together the config to make a new cluster IP service. And again, it's going to be identical to the other ones we've already put together. So let's get through this quickly as well. We'll do our API version of v1. We are making a service. It's going to have metadata with a name of Redis service. Actually, I think that, what was the terminology we've been using? Cluster IP service. Let's make sure that we stay very consistent here. So I'll do Redis cluster IP service, like so. I'll then give it a spec with a type of cluster IP. We'll make sure that we provide the selector so that this service knows what set of pods it is managing access to. So it's going to be component Redis. And then finally, we need to designate what set of ports this service is going to manage. So I'll say ports. Any outside object that is trying to get at our Redis pod is going to access this thing on port 6379. And then after it goes through the service, we're just going to let it stick with 6379 and have that port be what it connects to inside of our container. So I'll do a target port of 6379 as well, like so. Again, no good reason to try to redirect the ports here. There are situations where you would want to do that. For example, if we have an Nginx server that is supposed to be serving up web traffic on like port 80 or something like that, but for whatever reason we have configured Nginx to listen on port 3000, which is actually something we kind of did on the React application, but the React application is not directly receiving traffic. It's kind of backed behind that ingress thing that we're going to eventually set up as well. But if that were the case, then we could do that little bit of port redirection and not have to reconfigure our image or anything like that. Okay, so this looks pretty good. Now the last thing I want to do is load this up into kubectl as well with the apply command. So I'll flip back over to my terminal. There's the K8s directory. I'll do a kubectl apply -f K8s. We're just going to throw everything inside there. we should probably see a bunch of different objects that are going to end up unchanged, like so. But then the two new config files that we just made will be reflected as objects created inside this log. And so just as before, we can do a quick git pods and verify that, yep, we've got a single copy of Redis up and running. And we can also do a git services and verify that our Redis cluster IP service is up and running as well on port 6379. Okay, so this looks good. Now we've only got one last set of config files for Postgres, along with this associated cluster IP. So let's get through that in the last section. I know this stuff is so tedious with all this writing of identical files, but we're almost done with that. So let's finish up these last two config files in the next section, and then we get back to some more interesting topics in the world of Kubernetes. So quick pause, and I'll see you in just a minute. In this section, we're going to get through our last set of boring config for the Postgres deployment and its associated cluster IP service. So I'm sure you don't need any clever or witty comments from me at this point. I'm sure you just want to get this stuff done, so let's get to it. I'm going to flip on over to my code editor. Inside of my K8s directory, we'll do our Postgres deployment.yaml file. Now, again, this is going to be a file that's very much identical to the Redis stuff that we just put together and even the other different objects we had put together before that. I still do not recommend that you ever do a copy paste of these config files just because it's so incredibly easy to forget to update some specific property. Far safer to just rewrite it, but that's just my personal opinion. All right, so we'll do our API version of apps v1 for our deployment. This is going to be an object with a type of deployment. We'll set up our metadata, if I can spell it correctly, with the name of Postgres deployment, and then we'll set up our spec that's going to configure the deployment itself. So I again want to only have one replica running of my Postgres container inside of its given pod. Just very much like our Redis deployment that we just put together, we technically can create Postgres in a sort of cluster of different instances that are going to all work together to increase the availability and bandwidth of our database. However, again, that's something that's kind of outside the realm of Kubernetes that we're talking about right now, so we're just going to focus on running a single replica as it stands. After that, we'll put down our selector. We're going to say look for a label that is matching component Postgres. We'll then set up our pod template. So we'll give it a metadata property with labels of component Postgres. And then again, I'm going to make sure that I unindent back to be on the same indentation level as metadata. We'll define our spec for all the different pods that get created by this deployment. I'll say here's our list of containers. I want it to have a name of Postgres. I want to use the image Postgres. And then finally, we're going to set up the ports here as well. So the default port with Postgres, which we are using, we're not going to reconfigure or anything like that. We'll set up a container port of 5432. Again, default port for Postgres. All right, so that looks good. Now remember, very similarly to all the like Redis and Express API stuff that we had done previously, to get our Express and our worker pods up and working correctly, or more specifically the containers inside there, they need to have that set of environment variables that are going to make sure that they can successfully connect to this copy of Postgres. So we do have to set up a little bit of environment variables, not only inside of this file, but inside of the worker and server deployments as well. We're going to take care of that in just a second, but for right now, I want to first put together the cluster IP service, and then we'll come back and talk about all these environment variables and this PVC thing and all that stuff. Essentially, I just wanted to get the boring parts out of the way here at the very start of these repetitive config files, and then go over to the more interesting stuff like the environment variables and the Postgres persistent volume claim. All right, so that's our deployment. We're going to also make inside of our K8s directory the Postgres cluster IP service.yaml file. And inside of here, completely identical to the Postgres one we just, or excuse me, the Redis one we just put together, I'll do an API version of v1. We are making a service that'll have a metadata name of Postgres cluster IP service, and we'll give it a spec with the type of cluster IP. And then finally, to make sure that, or not finally, we have two other properties due here, but one of the two is going to be the selector. where we'll tell this thing what set of pods it's going to look for. And as usual, we'll give it component along with the name or the label that we had applied to it, which was Postgres, as we can verify back inside of our template section over here inside the deployment. All right, so now the real last step, for real this time around, we're going to set up our ports. We're going to say the default port of 5432 to connect to Redis, and we're not going to do any type of remapping this time around as well. Target port, there we go. All right, so that looks like it's just about it. Now let's take these two new configuration files and we're going to apply them to kubectl as well. And then we'll check out our different sets of pods and make sure that everything is running successfully before we start to come back and take care of the Postgres persistent volume claim thing and some environment variables as well. So at my terminal, still inside of my complex directory, we'll do our kubectl apply k8s. Now we should see that we have the Postgres IP service and the Postgres deployment as well. So just as before, we'll do our get pods. And now one of these names is really long, so it wants to kind of wrap the levels with me. So I can see my Postgres deployment right here. The container is being created. I'll do get pods again, and I can now see that it is in fact up and running for the Postgres deployment. And I'll make sure that I do my get services as well. And somewhere inside of here, Postgres cluster IP service. Very good. And I got port 5432. All right, so I think that we are pretty much all set. So that's just about it on our very basic, very simplistic config files for all the different deployments and associated services. So let's take a pause right here. When we come back to the next section, we're going to talk about some additional work that we need to do to make sure that the server can connect to Redis and Postgres, and to make sure that the worker can connect to Redis as well. And also, let's not forget this little PVC thing down here. Okay, so quick pause, and I'll see you in just a minute. In the last section, we finished up with our Postgres deployment file and the associated cluster IP service as well. So that's pretty much it for the boring configuration files, at least the ones around the cluster IP service and deployments. We're still going to write out a couple of different config files, but they're going to be much different than the ones we've put together so far, because they're going to serve dramatically different purposes than the services and deployments we've taken a look at. In this section in particular, we're going to start looking at what a Postgres PVC thing down here is. First beginning by getting a better understanding on why we need this PVC thing at all. So just so you know, PVC stands for Persistent Volume Claim. Now the word volume in here is the same type of volume that we had worked back with in the world of Docker and Docker Compose a while ago. You might recall that we had previously made use of volumes in order to share the file system of a host operating system or a host machine with the file system inside of a container. And so we had previously used it with Docker Compose when we were working on that Create React app. We had wanted to make sure that every time we changed the source code of our project on our local machine, it somehow updated the files inside of the container as well. Now, to give you a good idea of what a persistent volume claim is, I first want to do a very quick review on what a volume is and why we need a volume at all with Postgres in particular. Because if we just start talking about what a volume claim is without really understanding and remembering what a volume is, a lot of this stuff won't make sense. So in this section, quick review on volumes and why we need one with Postgres. All right. Now I just took the diagram we were looking at a second ago, like this big one right here, in particular the deployment and Postgres pod piece, and I blew it up to be its own kind of diagram right here, as you see. So we still have the deployment, which creates a pod, and inside that pod, we have a single Postgres container. And inside that container is a file system totally isolated to just be accessible by the container itself. Now I want you to recall that Postgres is a database, and the Postgres database, very similar to many other types of databases, though not relevant for Redis because that is specifically an in-memory data store, Postgres takes in some amount of data and writes it to a file system. So we can imagine that a request to write some data or essentially save some data with Postgres comes into the container. Postgres is going to process it and then eventually say, okay, I want to store this information on a file system or a hard drive of sorts. So inside that container, we can imagine that there is that file system and some amount of data is being stored on it. Now here's the thing to keep in mind about any file system that is created or maintained inside of a container. If we ever had a situation where if any reason you can possibly imagine, this Postgres container or the pod kind of wrapping it and managing it crashes, then everything over here gets 100% lost, including the file system that exists inside of the Postgres container. So if we just use our copy of Postgres as it stands right now, like this single deployment with this pod inside of it and no associated bells or whistles or volumes and stuff associated with it, if we just write data to Postgres and then that pod or that container eventually crashes, that entire pod is going to be deleted by the deployment. And a brand new pod is going to be created in its place. And this new pod is going to have absolutely no carryover of data. So none of the data on the file system of the original container gets brought over to this new container or the pod that wraps it. So essentially, the instant that the deployment starts up a new pod, we lose all of the data sitting inside of our database. And as you might guess, that is 100% not something we want to ever deal with. We never want to experience any type of data loss with any database, such as Postgres. So that's the issue. If we just let Postgres save all of its data inside the file system maintained by the container, we're going to lose it as soon as this pod crashes or the container crashes. And we have to absolutely assume that that might happen at some point in time. So how are we going to solve this? Well, recall that is where volumes come in. Now, when we had previously used volumes, it was all in the context of kind of being allowed to make changes to our source code files and have them show up inside the container. But we can also make use of volumes to have a consistent file system that can be accessed by a database such as Postgres. So we can now imagine that with a volume in place that is running on a host machine, if we have a request to write data that comes into the container, Postgres is going to think that it's writing it to a file system that exists inside the container, but in reality, it's going to be a volume that actually exists outside on the host machine. The result of this is that if our original pod or the Postgres container inside of it crashes for whatever reason whatsoever, the deployment is going to delete that thing and then create a brand new pod with a brand new copy of Postgres inside of it. But we're going to make sure that this new copy of Postgres that gets created gets access to the exact same volume. And so we'll have access to all of the data that had been written by the previous copy of Postgres that already existed. So that's the idea behind a volume, and that's how we're going to allow ourselves to save some amount of data with a database, but not have to worry about all the data inside there being deleted anytime that the container has to be restarted or crashes or whatever reason, whatever might happen. Now, one quick thing that I want to mention here, you'll notice that inside of our Postgres deployment, you'll recall we put down replicas of 1 right here. Now, I want you to recall that I told you, yeah, we can set up Postgres to have like some amount of replication or clustering that's going to improve the availability and performance of our database. Just to make sure it's really clear, if we just like bump that up to replicas like 2 right there, we would end up with a situation like this, where we have 2 pods that might be accessing the same volume. Having 2 different databases access the same file system without them being aware of each other and have them very distinctly cooperating with each other is a recipe for disaster. So at no point in time are you ever going to want to just arbitrarily dial up replicas to 2 like so and attempt to have 2 copies of Postgres accessing the same volume. Now, that's not just isolated to the world of Postgres. Many other databases, you're going to find the same problem. So for whatever reason you want to scale up your copy of Postgres and make it more available by having more copies of it running or whatever it might be, you have to go through some additional configuration steps besides just incrementing that replicas number right there. So again, I just want to make sure that was really, really, really clear. Okay, so now that we recall why we make use of volumes and why a volume is so important to use with a database, let's continue in the next section where we're going to start to talk about exactly what a persistent volume claim is and how it's going to assist us in setting up a volume for our Postgres pod. So quick break and I'll see you in just a minute. In the last section, we spoke about how we might use volumes as a way of persisting data outside of a container when that data is something that we care about and we want to have be persisted across restarts or termination of a given container, specifically or most especially ones that are running a database of some sort. Now, in this section, we're going to start talking about volumes in the world of Kubernetes. The first thing I want to clarify is a little piece of terminology. It's actually the word volume itself. I want to tell you a little bit about what the word volume means in the world of Kubernetes. All right, so first things first, there's a little discussion about terminology. In the last section, I was using the word volume over and over and over again. When I was using the word volume in the last section, it was kind of as a generic term in container terminology world. And it was a reference to some type of data storage mechanism that allows a container to store data outside of its own little file system. However, in the world of Kubernetes, the term volume is a reference to a very particular type of object. An object in the same sense that a deployment is an object or a service is an object. So in the world of Kubernetes, we can write a configuration file that will create something called a volume. In Kubernetes, that object is something that allows a container to store some persistent data at the pod level. In addition to the use of volumes, we also have access to two other types of data storage mechanisms, both something called a persistent volume claim and a persistent volume. So in this section, I want to expand upon what a volume is in the world of Kubernetes just a little bit so that you understand that when we use the word volume with Kubernetes, it's a reference to a very particular thing, and it's very different than referring to something called a persistent volume or a persistent volume claim. Now, we're not going to make use of volumes for everything that we're doing. We're not going to use volumes at all. I just want you to understand that this is a completely separate thing. And so when you start to look at documentation and you see documentation that says, oh yeah, create a volume, you have to create a distinction between what a volume is and a persistent volume is. Otherwise, when you're reading that documentation, you're going to get really, really confused. Okay, so with that in mind, this section, we're going to look at a diagram that explains exactly what a volume object type is in Kubernetes. All right. So I want to again consider our Postgres deployment. Let's imagine we have a deployment that manages a single pod, and that pod has a single Postgres container. When we create a volume in Kubernetes, we are creating a little kind of data storage pocket that exists or is tied directly to a very specific pod. So you'll notice in this diagram, I'm reflecting this volume right here that's going to store some amount of data as being kind of like inside the pod. It's essentially kind of like belongs to or is associated to the pod in some fashion. Now this volume can be accessed by any container inside of the pod. So for example, if we had a Postgres container running, it could store all of its data inside of this volume that belongs to the pod itself. Now the benefit to using this volume here is that if this container, like this one specifically, ever dies or crashes and gets restarted as a completely new container, like so, let's imagine that we get a second Postgres container and the old one gets killed, so I'm going to mark it as red right there. Then this new Postgres container has access to all of that data in that volume. And so that might sound like exactly what we were just talking about in the last section. We're essentially saying, oh yeah, new container gets created. Well, the new container gets access to that same volume and it has access to all the data that the previous container had access to as well. However, here's the downside. The volume is tied to the pod. And so if the pod itself ever dies, the volume dies and goes away as well. So a volume in Kubernetes will survive container restarts inside of a pod, but if the pod itself, for whatever reason, ever gets recreated or terminated, deleted, whatever happens, then the pod and the volume inside of it, poof, totally gone. And then, of course, the deployment would kick in and recreate that pod with a volume inside of it. So as you might guess, in the world of Kubernetes, a volume is really not appropriate for storing data for a database. It definitely works in the sense that the container can restart, but we still are weak or we're still kind of vulnerable to anything going wrong at the pod level itself. All right, so that's why we're not going to use volumes. And just so you know, in real life, as I say volume, I'm doing like, double quotes around myself to say, specifically a Kubernetes volume. That's why we are not using a Kubernetes volume. All right, so now that we've clarified that little piece of terminology, we're going to come back to the next section and we'll talk more about exactly what a persistent volume is and a persistent volume claim. So quick pause and I'll see you in just a minute. In the last section, we spoke about what a volume is in the world of Kubernetes. We're now going to start to talk about these two other types of objects that we can create as well, a persistent volume claim and a persistent volume. We'll first begin by comparing and contrasting the differences between a persistent volume and a volume. So, quick diagram to figure out what the differences between these two are. All right, so in this diagram, on the left-hand side, we have a Postgres deployment with a volume. That's exactly what we were talking about in the last section. We had said that a volume is going to be some long-term storage that is tied to a pod. Whenever the pod is created, the volume is created. If a container crashes for any reason, the volume will stick around, the volume will persist. And so we had said that if we end up with a new Postgres container for whatever reason, no problem, it can freely connect back to this existing volume that had been created. And so we can kind of imagine that the old container might fall away and it gets replaced with this new one, still gets access to all that volume data. However, if the entire pod crashes for any reason, everything inside the pod is lost, including that volume. All right, so that's a volume. That's what we spoke about in the last section. So now let's compare and contrast that against a persistent volume. With a persistent volume, we are creating some type of long-term durable storage that is not tied to any specific pod or any specific container. So you can kind of imagine that the persistent volume is outside the pod, completely separate from the pod. If this container crashes for any reason, or if it needs to be recreated for any reason, no problem whatsoever. The old container will fall away, and the new one can connect to that persistent volume that exists outside the pod. Now let's consider the other case, the case in which maybe a pod needs to be deleted or recreated for some reason. So we can kind of imagine that if this pod crashes entirely and gets recreated, no problem whatsoever, the old pod falls away, it completely disappears, but the persistent volume is still going to stick around. When the new pod is created with a new copy of Postgres, that container is going to be able to connect to that persistent volume that exists outside of the pod. So that's a big difference between a normal volume and a persistent volume. Essentially, we're talking about the life cycle of the volume itself. With a normal volume, it's tied to the life cycle of the pod. With a persistent volume, it's going to last for all time, or essentially until you and I as developers or as the administrators decide to delete it for some reason. But with a persistent volume, we can recreate a container, we can recreate a pod, no problem. The volume is still going to stick around with all the data that you would expect to have. All right, so that's the differences between a persistent volume and a volume. So let's take another quick break right here, and we'll talk about what the differences are between a persistent volume and a persistent volume claim. So quick pause, and I'll catch you in just a second. In the last section, we spoke about what a volume is compared to a persistent volume. We're now going to pivot a little bit and talk about how a persistent volume claim compares to a persistent volume. Now, these two topics right here and their relation with each other is kind of hard to understand at first glance. So I'm going to give you a very quick analogy or a very quick story to help you understand what the difference is between a volume claim and a persistent volume. After I give you the analogy, we'll then kind of take this little short story and pivot it over to the world of Kubernetes and apply some real terminology to it. So in this section, let's get to it. We're going to look at a very quick little short story to help you understand the difference between a persistent volume and a persistent volume claim. So here's my short story. I want you to imagine that you are walking down a sidewalk and you are in the process of building out some custom computer. You are building a computer from scratch, and so maybe at this point in time you have a case and a motherboard and a processor, some RAM, and a graphics card. And the last thing that you need might be some type of hard drive. So you're walking along with your custom PC and you see a big billboard that says, come on down to the computer store. We have 2 really great hard drives that are available. We have a 500 gigabyte option and a 1 terabyte option. So you look at this billboard right here and you say, you know what? Between these 2 options, I think that 500 gigabyte hard drive would be perfect for my custom computer. So you take your custom computer, you continue walking down the sidewalk until you get to the computer store. Now at the computer store, you talk to a salesperson and you say, hey, you know, I just saw that billboard where you were advertising the 500 gigabyte option. I would love to have one of those hard drives. So the salesperson says, not a problem. And they turn around and they go to some storeroom or some like inventory store inside the computer store, and they look through all the different pieces of hardware that they have available. Now you had asked for a 500 gigabyte hard drive, so the salesperson says, great, this is perfect. I can meet your request right now. I've got a 500 gigabyte hard drive ready to go. And so they throw that thing over to you, and you now have a 500 gigabyte hard drive that you can put into your computer. All right, so that's the entire short story. That's kind of scenario one. Now, I want to very quickly go through the same scenario again, but we're going to imagine that rather than asking for a 500 gigabyte hard drive, maybe this time around you ask for a 1 terabyte hard drive instead. So we're going to do a second flow through this diagram. And imagine that you instead decide you want the 1 terabyte drive. So in this case, you are again walking down the sidewalk, you see the billboard, and you see that there is a 1 terabyte hard drive storage option. You say, oh, that's perfect. I would love to have a 1 terabyte hard drive. So you walk down to the computer store a second time, and you say to the salesperson, hey, I would love to get one of those 1 terabyte hard drives. And the salesperson says, okay, sure, let me just check the storeroom really quick. So the salesperson goes back to the storeroom, and they look at all the hard drives that they already have in stock. So these hard drives right here inside the storeroom are essentially hard drives that have already been created. They are in existence already. The salesperson looks through all the stock that they have, and they very quickly realize, oh no, there is no 1 terabyte hard drive on stock, on hand, ready to be sold. But the salesperson is not going to give up very easily. The salesperson says, you know what, I'm going to make sure you get what you asked for, because we were advertising that as an option. So the salesperson picks up the phone and very quickly makes a call out to the hard drive factory. They call the factory and they say, hey, look, I got someone right here. They want a 1 terabyte hard drive. I need you to create this thing right now and ship it on over. And so the factory puts that hard drive together, lickety-split, just as fast as you blink, and they ship it on over to the computer store. And so now the salesperson has your 1 terabyte hard drive that was fabricated on the fly just for you. And they hand the hard drive over, and you are now a happy little camper because you have the 1 terabyte hard drive that you were asking for. All right, so that's the entire story. 2 run-throughs. Now there's a couple of very quick important points that I want to highlight here. The first important point is that we had a billboard that was essentially advertising storage options that were available. The second important thing is that for those 2 storage options, some of them were ready to go and pre-assembled. So there were some instances of 500 gigabyte hard drives that had already been created and were ready to be handed off to you, the customer. There were also some storage options that had been advertised on that billboard that were not ready to go and had to be essentially fabricated or created on the fly to meet your demand. So whether it was a hard drive option that was ready to go or one that had to be fabricated on the fly, no big difference to you, the customer. Either way, you got what you were asking for. All right, so that's the 2 big points I want you to understand. So we're now going to look at another copy of this diagram that has some Kubernetes terminology applied to it. Okay, so here's the Kubernetes version of this diagram. So first off, you, in the previous diagram, were putting together a computer and you had realized that you needed a hard drive. That's very similar to you and I, as developers, putting together a pod configuration. When you and I put together a pod that we know is going to need a persistent volume, we have to look at a billboard of sorts that's going to advertise a couple of different storage options. So these different storage options that are being advertised are what we refer to as persistent volume claims. So a persistent volume claim is an advertisement. It is not an actual volume. It can't store anything. It's just an advertisement that says, here are the different options that you have access to for storage inside of this particular cluster. You and I, as developers, are going to write out inside of some config files the different persistent volume claims that are going to be available inside of our cluster. So you and I are going to write a config file that says there should be a 500 gigabyte hard drive option available to all the different pods inside of our cluster. And we might also write out a config file that says there is a 1 terabyte option that is available as well. So again, a persistent volume claim is like an advertisement. It's saying, here is something that you can purchase. Here is something you can get for your pod when it is created. Now, when you chose one of those persistent volumes, you went off to Kubernetes with your pod config, and you said to Kubernetes, which was the salesperson in reality, hey, I just saw that 500 gigabyte hard drive option. and you said to Kubernetes, hey, I want that 500 gigabyte option. Give me one of those. And so Kubernetes had to go back into some imaginary store, and it had to look through some number of options of persistent volumes or storage options, instances of storage options that were readily available. And so inside of a Kubernetes cluster, we might have some number of persistent volumes that have been created ahead of time. These are actual instances of hard drives, essentially, that can be used right away for storage. Any persistent volume that is created ahead of time inside of your cluster is something that we refer to as statically provisioned. So a statically provisioned persistent volume is something that we have very specifically created ahead of time. On the other hand, we also had another option that could have been created on the fly. So this is what we refer to as a dynamically provisioned persistent volume. It is another storage option that is not created ahead of time. It's only created when you, putting together your pod, ask for it. So you can totally ask for this 1 terabyte hard drive. You can say to Kubernetes, give me that 1 terabyte option, but that 1 terabyte hard drive was not going to be created until you went ahead and asked for it. So that's the difference between a dynamically provisioned and a statically provisioned persistent volume. Is it created ahead of time, or is it created just when you immediately ask for it? All right, so that's it. That's the big difference between a persistent volume and a persistent volume claim. The persistent volume claim is an advertisement of options. You can ask for one of those options inside of your pod config, and when you do, Kubernetes is going to look at its existing stores of persistent volume, and it's either going to give you a volume that's been created ahead of time, or it's going to attempt to create one on the fly. So there's the entire example. Let's take a quick pause right here. When we come back to the next section, we're going to start to update our config files to create a new persistent volume claim that's going to create a storage option that can be claimed, essentially, by our Postgres pod that we had already created. So quick break, and I'll see you in just a minute. In the last section, we spoke about the big differences between a persistent volume claim and a persistent volume. Remember, a volume claim is an advertisement. It is saying, hey, all the pods inside this cluster, you can choose from a 500 gigabyte option or a 1 terabyte option. When we write our pod config, we are going to say, hey, this pod needs the 500 gigabyte option. And so you can kind of imagine that our pod config is going to be handed off to Kubernetes with this kind of option tied to it. Kubernetes is going to see that option, and it's going to say, oh, okay, I get it. I need to find an actual instance of storage inside of my cluster that meets these requirements. It has to have 500 gigabytes worth of storage. If Kubernetes does not have an instance of storage like that ready to go, then it's going to try to create one on the fly and then attach it to the pod that gets created. Now, I can give you diagrams about this stuff all day and verbal descriptions all day, but to really understand this stuff, you really have to put together a config file on your own. So in this section, we're going to write out a persistent volume claim. And remember, this is going to essentially advertise a possible storage option that can be attached to a pod config. So inside of my code editor, I'm going to find my K8s directory. And inside of here, I'm going to make a new file called database persistent volume claim.yaml. Now, I typed that out rather quickly. Remember that you can always see my file name at the top here inside this tab. All right, so inside of here, we're going to write out a pretty good amount of config. Some of it is going to look very familiar, and some of it is going to be a little bit new. So we'll do the familiar stuff first. I'll say API version is v1. Our kind will be persistent volume claim. We'll do a metadata that has a name of database persistent volume claim, and then we'll add a spec. So the spec is where some interesting things start to come into play. I think you'll agree with me that everything up here looks pretty darn familiar. So for our spec, we're going to give an access modes. Notice how there's an S on there. This is going to be an array, so I'm going to put a dash in like so, and then I'm going to give this a single value. I'll say read, write once. On the next line, I'm going to unindent so that I'm on the same indentation level as access modes. I'll do resources, requests, storage is to GI, like so. Okay, so that's it. That is all the config that we need for our persistent volume claim. Let's take a quick pause right here. When we come back to the next section, we'll talk about exactly what is going on inside the spec section. So quick pause, and I'll see you in just a minute. In the last section, we put together our first persistent volume claim. Now, before we talk about what the spec stuff inside of here is, I want to give you a very quick reminder. Remember that a volume claim is not an actual instance of storage. A volume claim is something that we are going to attach to a pod config. So back in our example over here, we would take this volume claim that says, hey, I can get you a 500 gigabyte hard drive, and we attach it to our pod config. Then at some point in time, we take that pod config and we hand it off to Kubernetes. Kubernetes is going to see that storage option, it's going to see that volume claim, and it's going to try to find either a statically provisioned persistent volume or a dynamically provisioned persistent volume to meet the requirements of that claim. So all the config that you and I have now added in underneath the spec section is saying that if we attach this claim to a pod, Kubernetes must find an instance of storage, like a slice of your hard drive, that meets these requirements. So with that in mind, let's talk about what an access mode is. All right, so access modes. We get 3 different types of access modes. The one that we used is read, write once. Read, write once means that we want to get some instance of storage, like a slice of your hard drive, that can be used by a single node at a time. And to be precise, that single node can use it and both read and write information to that volume. We also get access to an access mode of read-only many, which means that multiple nodes at the same time can read information from this persistent volume. And then finally, read-write many means that we can both read and write information to this persistent volume by many nodes at the same time. Now, again, I want to really highlight the fact that the access mode that we put in right here says, if you attach me to a pod config and then hand me off to Kubernetes, Kubernetes is going to have to find an instance of storage that supports this access mode. All right, so let's now move on to resources down here. Now, I bet you can really guess what's going on here. So with storage, we're essentially saying that Kubernetes is going to have to find a storage option, either one that has been provisioned ahead of time or one that is going to be created on the fly that has at least 2 gigabytes of space. Or to be exact, it has to have exactly 2 gigabytes of space. We could very easily change this number around. You know, we can say 1,000 gigabytes or 4, 6, whatever you want it to be. But for us, 2 is way more than what is needed to put together our very simple Postgres database. In fact, you know, we're going to use like fractions of a kilobyte. So 2 gigabytes is way overkill for our application, but I just want to give you an example with a gigabyte option here. Okay, so these 2 options right here, pretty straightforward in nature. Again, they are saying, hey, Kubernetes, you have to find a storage instance that has this access mode, and it has to have exactly 2 gigabytes worth of storage. Now, there's a couple of other options that we can add into this file that we did not, because we're going to rely upon the defaults. But these other storage options that we did not list out are pretty important to understand. So let's take a quick break. When we come back to the next section, we'll talk about some other possible options that we could put into the spec if you had need to do so. So quick pause, and I'll see you in just a minute. In the last section, we spoke about some of the different config that we put into our persistent volume claim. Now, at the end of the last section, I had mentioned that there are some other possible options that we could put inside of here. We did not put these options in because we are going to rely upon the defaults for each of these. But there's one option in particular that I want to mention because it might be very important for you to use at some point in time in the future. Okay. So I want you to imagine kind of what happens behind the scenes when we hand that persistent volume claim off to Kubernetes. And so if we look back at the diagram over here, remember at some point in time, we hand that pod config off and Kubernetes sees, oh, they want that 500 gigabyte option. And so Kubernetes has to like go and find either that pre-configured, pre-created ahead of time persistent volume or make one on the fly. So think about what's going on behind the scenes there. We're essentially saying to Kubernetes, hey, I need 1 gigabyte worth of storage. Can you get me something that meets these requirements? That's what the persistent volume claim is really doing. So Kubernetes gets that, and then we're going to imagine what exactly happens on your computer when you run this stuff. We can kind of imagine that Kubernetes probably says something like, all right, well, I'm on this developer's personal laptop, or maybe I'm on their personal desktop. Not a lot of storage options available here. Like pretty much all I've got to put any information in is your hard drive. So on your computer, by default, Kubernetes is going to say, you know what, I'm going to make a slice of your hard drive that is 1 GB large. And so we can imagine on your hard drive, we get this 1 GB little piece of your hard drive that is going to be a persistent volume. And that persistent volume gets handed back over to your pod. So on your computer, when you ask Kubernetes for some amount of storage, there's really just one place for Kubernetes to allocate that storage. It's just your hard drive, and there's really not a lot of other options. Now you can actually see in the Kubernetes config where it decides to make this the default, where it decides to say, I'm just going to put it on your hard drive. To do so, you can flip on over to your terminal and run kubectl git storage class. So when you run git storage class, you're going to see all the different options on your computer that Kubernetes has for creating a persistent volume. Right now, we have a single option called standard. It is the default option. So if we do not specify a storage class with our persistent volume claim, the standard option will be used by default. And the provisioner, or essentially how Kubernetes is going to decide how to provision or create this persistent volume, is by using the minikube host path option. I want you to also do a kubectl describe storage class as well, and you'll see some more information about that option right there. So when you do so, it tells you in very broad terms, yes, we have a provisioner that is minikube host path. Minikube host path means exactly what we saw over here. Minikube host path means that when we ask Kubernetes to create this persistent volume, it's going to look on the host machine to Minikube, and it's going to make a little slice of space on your personal hard drive. All right, so at this point, this probably seems, at least somewhat palatable. Like, yeah, Kubernetes needs some space. It's going to try to claim some space off of your computer or your personal hard drive. But things start to get way more complicated when we start to move our Kubernetes cluster from your computer into a cloud environment. So at some point in time, you and I are going to move our application over to a cloud provider. And when we are working with a cloud provider, we get a tremendous number of different options of where some hard drive space, or essentially file system space, can be sourced from. So in a cloud or production environment, if we say, hey, I need 1 GB of storage to Kubernetes, Kubernetes is going to turn around and say, great, which one do you want? I got like 1 billion options available. And so just about every cloud provider that you're going to work with is going to have some different solution for storing information. And you need to tell Kubernetes, unless you want to use the default option, which of these different options you want to use. So if you are hosting an application on Google Cloud, the Google Cloud service called persistent disk is going to be used to store information with your persistent volume. If you're on Microsoft Azure, you can either use Azure File or Azure Disk. If you're on AWS, you will use AWS Block Store. Now, there's many other options that are available in a cloud environment. You can see some of the other options at this address right here. I actually already opened up that page. So on that page, you'll see storage classes. And if you scroll down to provisioner, the provisioner is essentially what determines how the space that you're asking for gets created. And so these are all the different options that you have available. You can look at that list and decide on which one you want. But I can tell you that by default, most of the time, you're probably going to want whatever the default is for your particular cloud provider, which on, say, Google Cloud, it's going to be persistent disk. On AWS, it's going to be block store. Now, when you create your Kubernetes cluster on a cloud provider like Google Cloud or AWS, one of these services is going to be set up by default for you. So in other words, right now, inside of our local environment, we are setting up this persistent volume claim without designating a storage class name. And we did not designate that option because we are relying upon the default. And like I just said, the default for us is to create a little slice on our hard drive to use for this persistent volume. But when you push your application up to Kubernetes on Google Cloud or AWS, the standard option is not going to be minikube host path. Instead, the standard option or the default option for use on AWS or Google Cloud will be automatically configured for you to be either Google Cloud Persistent Disk or AWS Block Store. So long story short here, what I'm trying to tell you is that when you ask Kubernetes for some amount of storage on your local machine, it's just going to take a slice of your hard drive. When you are in a cloud environment, it's going to choose one of these default options for you unless you very specifically tell it to use something else. For most applications, I don't really want to make a broad claim here, but I'm going to tell you that if you've got a normal application that just has a traditional database like Postgres or MySQL, you're probably going to be okay using the default options, which are probably going to usually be Google Cloud Persistent Disk or AWS Block Store. But I just want you to know that this option is available and you can customize where Kubernetes is going to look to create this little file system to allocate to your pod. All right, so enough on all this. I think we've spoken about persistent volume claims enough. So we've now created our persistent volume claim, which is essentially advertising an option that can be used for storage by all the different pods in our application. So last thing we have to do in the next section, we're going to open up our Postgres deployment, and we're going to update the pod config in here and tell it that when this pod is created, it's going to need to look at all the different storage options that are available and advertised by this persistent volume claim and make sure that it says, oh yeah, I want this very specific volume claim that's going to give me a 2 GB storage option. So quick pause and I'll see you in just a minute. In the last section, we finished up our persistent volume claim. I'm now going to flip over to my Postgres deployment file. So I'm going to find the template section of this. Remember, this is the template that is used for every pod that is created by this deployment, and there's only ever going to be one pod at a time. We're going to update this template section and tell this pod that when it is created, it needs to request some type of long-term storage, in other words, a persistent volume, that meets all the requirements that were advertised by this persistent volume claim that we just put together. So inside of my Postgres deployment file, I'll find the template section and then the spec inside there. And inside the spec, we're going to add on a new key value pair. So I'm on the same indentation level as containers right here. And I'm going to say volumes. This is going to be an array, so I'll put a dash in. And then I'll say name of Postgres storage. And then persistent volume claim name, and this is going to be the name of the claim that we had just put together in the other file. Its name was database persistent volume claim. So the claim name will be database persistent volume claim. Okay, so this right here is what sets up the request on the pod to reach out to Kubernetes and say, I need some type of long-term storage that meets all the requirements that are laid out inside of this database persistent volume claim object. And that's what we had just put together over here. So this line alone is what's going to make Kubernetes realize that it needs to go over to either the local hard drive, if we are in the case of your local environment, or some cloud provider in the case of being deployed in production, and say, hey, I need to somehow source or somehow get some slice of storage that has this access mode and storage of 2 GB. So all this is going to do right here is allocate that storage. Once we allocate that storage, once we get it available, we need to actually assign it for use by all the different containers that are in use by our pod. So in addition to this volume section right here, we're also going to add on some config to our container section as well. So inside my container section, I'm going to add in a new line here, and I'm going to get on the same indentation level as name, image, and ports. And I'll say volume mounts. So this is going to say, hey, all right, we just got access to the storage, and here's how I want it to be used inside of my container. So I'm going to add in a dash here because this is an array. We can have multiple volume mounts on a single container. I'll give it a name of Postgres storage. Now this right here is the most important part. Notice how the volume name and the volume mount name are identical. So when you put the name right here, it means go back out to the volumes entry and find some piece of storage that we just asked Kubernetes for. In this case, it's going to find this piece of storage right here, and that piece of storage is going to be used for this particular volume mount. We're then going to put in a mount path. The mount path is designating where inside the container this storage should be made available. So in other words, we're going to put in a little folder reference right here, and then anything that the container stores at that folder or inside that directory will be actually stored inside of our volume. Remember, this is, at the end of the day, pretty darn similar to the Docker volumes that we had used previously. So for the mount path, we're going to designate the data directory that Postgres uses for storing data on the hard drive, because that's the actual data that we want to back up. We want to back up all the data that Postgres is storing on the hard drive. The default storage location for Postgres is var lib postgresql/data, like so. Okay, now for a normal volume, that would be it. So if this was just a normal application where we're just trying to set up some persistent storage, that's really all we have to do. Both Postgres in particular, we're going to put in one additional little option here. So as an additional option, I'm going to also put in subpath is Postgres, like so. The subpath option means that any data inside the container that is stored inside of mount path is going to be stored inside of a folder called Postgres inside of the actual persistent volume claim. So if we ran our application for some amount of time and then saved some data to our Postgres database, and then eventually opened up our persistent volume, we would see that all the data that was saved to this folder is nested inside of a folder called Postgres inside the persistent volume. Now, like I said, this is something very specific for Postgres. It's just because if you try to start up Postgres by default with something that it thinks is a volume mount, it's going to say, hey, I don't want to save data here. And so by having Postgres instead save data into a subfolder inside there, it's going to override that default behavior. Now, saving data into a volume with Postgres is totally fine, totally fine. It's just that Postgres, in some cases, thinks that you're not necessarily working with Docker. It's a long story. Let's just leave it at that. This is just some very particular stuff around Postgres, probably not super interesting to you or what you're going to be working on in your own application. So I'm just going to stop right there. All right, so that's pretty much it. So let's do a very quick review here. We put together the persistent volume claim that tells Kubernetes that we want to find a storage option with these requirements. When we put together our pod template, we said we want to have a volume available that matches these requirements. And then inside the container, we put together some actual options to say, take that volume and make it available inside of this very particular container. So that's the entire story. Let's take a quick pause right here. When we come back to the next section, we're going to try to apply all these updated config files and just make sure that everything is working the way we expect. So quick pause, and I'll see you in just a minute. In the last section, we finished up all of our Postgres persistent volume claim stuff. So the last thing we have to do is apply it to our local cluster. I'm going to flip over to my terminal. I'm going to make sure I'm still inside of my complex directory, and then we'll do our kubectl apply -f. And as usual, we're just going to throw everything inside of the k8s directory into the apply command. So I'm going to run that, and we're going to very quickly see that we have created a new claim and that we have reconfigured the Postgres deployment. So now we're going to get the status of our deployment and all of its pods and just make sure that everything is still working the way we expect. So the first thing I'll do is a kubectl get pods. We're going to see Postgres inside of here, and it looks like it just got restarted and is now running. So that's good. I'll do a kubectl get PV, which stands for persistent volumes. And this is going to list out all the different persistent volumes that have been created inside of our application. And on here, we can see that we have a persistent volume with the name of PVC, blah, 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 blah. It has 2 gigabytes. This is the access mode. And there's a couple other columns on here. I'll probably have to zoom out really far. Okay, on the very far right-hand side, you can see that it has a claim using our database persistent volume claim. And the status of it is bound, which means that it is currently in use. We can now also do a kubectl get PVC, and that will list out all the different claims that we have created as well. So remember, the claim right here is an advertisement. It is saying you can get this thing if you want to. The persistent volume right here is saying here's an actual instance of storage that meets all the requirements that were laid out by the persistent volume claim that we made. Okay, so that's pretty much it. So hopefully now, if we write any data to Postgres and then for some reason kill that pod, ideally it will not wipe out any of the data that had been stored inside the database. Now we're not going to be able to test that yet because we have not yet configured Express or our worker instances to actually save data into Postgres. So that's the last thing that we really need to take care of. Let's take a quick pause right here. And in the next section, we're going to figure out how to add in some environment variables to make sure that our server and the worker can both connect to Postgres and Redis to save some amount of data. So quick pause and I'll see you in just a minute. One of the last things we have to do to set up our application in Kubernetes is set up some different environment variables. So as a quick reminder, we've got a handful of environment variables that need to be assigned to both the multi-server and the multi-worker. The multi-worker needs to know how to connect to Redis through the environment variables of Redis host and Redis port. The multi-server needs to know the same thing, and the multi-server also needs to have a set of environment variables to tell it how to connect to Postgres as well. So in this section and the next couple, we're going to describe and discuss how we set up environment variables in Kubernetes. All right, now in this diagram, I took these same environment variables and I did a little bit of color coding. So first off, let's talk about the meaning behind the yellow color inside of here. So this, and this, all the yellow ones are going to essentially be consistent, constant values. And we don't have to do a lot of work to set these up inside of our different deployment definitions. All the yellow ones are going to be pretty darn straightforward. Now there's two red ones on here as well. So the two host values, these are also going to be constant values that do not need to change over time or anything like that. But I want to remind you about the purpose of the host environment variables. These are essentially URLs of sorts that are going to tell multi-worker and multi-server how to connect to Redis and Postgres in the first place. In other words, how it can actually reach out to the running Postgres server or the running Redis server and make a connection to them. So with that in mind, I want to remind you about the kind of overall architecture of our application. Remember that we've got our Redis pod right here and Postgres pod right here. And we had said that the multi-worker and the multi-server are going to connect to both those different pods through the use of that cluster IP service. So we need to understand how we can tell multi-worker to connect over to this Redis pod somehow through this cluster IP service. And we're going to do this by providing a value to the Redis host environment variable and the PG host environment variable as well. So let me just tell you, let's get down to basics here. It's a real straightforward thing. Essentially, all we have to do is say, okay, we want to form a connection from our deployment of multi-worker over to the Redis pod that is being managed by the cluster IP service. So all we have to do is provide a host name of the name of that cluster IP service. If you open up your code editor and find the cluster client cluster, no, not that one, where is it? There it is, Redis cluster IP service right here. Remember, we had given it a name of Redis cluster IP service. That's going to be the host name. So you can kind of imagine that we're going to connect to http:// Redis cluster IP service. Now, there's not going to actually be the HTTP on there. I just put it on there to make you understand that this is kind of like a URL, and to connect from one pod over to another, we just provide the name of that cluster IP. All right, so that's not too bad. So in total, all the first set of environment variables, like all these up here, they're going to essentially be constant values. And we just have to go around to our different pod deployment configurations and add in a little bit more config to say, hey, here's an environment variable of like Redis host, and here's the value for it. Same thing for the port, same thing for the user, everything straight down. Now, the one value in this entire list here that's going to kind of stick out like a sore thumb that we're going to do a little bit of additional work on is going to be the PG password. So PG password is a password to our Postgres database. And without a doubt, we probably do not want to stick this as a constant value or just in plain text inside of our Kubernetes config files. And so we're going to do a little bit more extra work above and beyond for the PG password, and we're going to learn how to manage secrets or secret variables inside of our Kubernetes cluster. But we're going to first do all the setup for all these other ones, and then we'll tackle the PG password at the very end. So let's take a quick break right here. When we come back to the next section, we're going to start setting up our environment variables for the multi-worker and multi-server. In this section, we're going to update our config files for the multi-server and the multi-worker and add all these different environment variables. Again, we're going to leave off the PG password for right now. We're not going to worry about that one just yet. We're going to come back to it at the very end. All right, so we're going to first open up our multi-worker config file, the deployment for it, and we're going to add in a little bit of configuration to that. So inside of my code editor, I'll find the worker deployment file. Then inside of here, I'm going to scroll down to the pod template. So here's my template section. I'm then going to find the container definition, and we're going to add on a set of environment variables that are going to be passed into this container when it is created inside of the pod. And so on the container definition, I'll add on an env environment, or excuse me, an env key. Env is short for environment variables. We're going to designate a couple here. So env is going to receive an array. So I'm going to put in a dash like so. Then for every entry inside this array, we're going to have a name and a value property. And I bet you can guess what these are going to do. Name is going to be the name of the environment variable, and then value is going to be the value for it. So for our first named environment variable that we're going to pass into the worker, we'll pass in our Redis host. And again, this is going to be some type of reference telling our multi-worker container how it can reach out and connect to Redis. So what we want to put in here is the name of the cluster IP service that the worker needs to connect to get at the Redis pod. And again, in this case, it's going to be Redis cluster IP service, because that's what we provided as the name for that cluster when we put it together, or that cluster IP, when we put it together inside of our Redis cluster IP service file. So this is the string right here. That's what we care about. So for the value, I will put in Redis cluster IP service. And then next up, we're going to also designate the Redis port. The port value here is going to be 6379. That is the default value for the Redis connection port. It's also what we wired up inside of our Redis cluster IP service as both the opening port and the target port in there as well. So this, again, is going to be a hard-coded value. We're just going to throw it directly in here as 6379, like so. Okay, so that's it for the worker deployment. That's all the environment configuration we need. So I'm going to close that file, and then we're going to also open up our, where is it? The server deployment right there as well. So in the server deployment, we're going to add in a set of environment variables to the server. So I'm going to find the server container configuration. And inside of here, we're going to do our env block as well. Now this one's going to have significantly greater number of environment variables. So we're going to do a little bit of typing here. Let's see. We'll start off first with a name of Redis host. The value, again, is going to be the name of our Redis cluster IP service, which was Redis cluster IP service. We'll do another array entry. So notice how I put another dash right here. This is going to be our Redis port. We'll have a value of 6379 over here as well. Next up, we'll do our PG user. So this is going to be the default username for Postgres. And we just use the default of Postgres, which is technically not good form, not the best way to make use of Postgres here, but totally fine for our purposes. Next up, we'll do our PG host. So the PG host is the connection string. We're essentially telling multi-server how to reach out to our Postgres instance. And so very similar to what we just did with Redis, we're going to do the same thing with Postgres as well. We're going to provide the name of the cluster IP service that is managing access to the Postgres pod. So I'm going to open up the Postgres cluster IP service config file right here. I'll find the name, and that's going to be the host name that we want to attempt to connect to get access to that database. So for my PG host, I'm going to put in Postgres cluster IP service like so. All right, so what do we have next? I think we have our PG port. The value for that, we are using the default of 5432, no changes there. Remember, we also set up our Postgres cluster IP service to make that port available. And I think probably the last one, actually, I think we got two more here. What do we have? I just want to double check the diagram and make sure I'm not missing any in here. So we got the port, I think it's the database, right? Yeah. All right, so we're going to do our PG database. And again, we are using the default Postgres database of Postgres. Again, very much like the PG user, using the default database, not quite the best way of doing things, but for our purposes, it is good enough. All right, so I think that's it in terms of the initial set of environment variables. So let's take a quick pause right here. When we come back to the next section, we're going to talk a little bit more about the PG password, and we're going to make sure that when we put this into a config file, we are not writing out the password in plain text. We're going to make sure that we store it in a much more secure fashion. So quick pause, and we'll take care of that in the next video. there's one last environment variable that we have to set up, the PG password. This environment variable is a password that's going to be used to get access to our database. Now, one thing I want to be really clear about right now is that the password is tied to Postgres itself. This is not a password related to Docker or Kubernetes or anything like that. We are talking about just getting access to Postgres. We need to make sure that we add in this environment variable and pass it to the multi-server. But like I said in the last video, chances are that we do not want to write out our password in plain text and store it inside of our config file. So rather than adding in our password as plain text or anything like that, we're going to use a new type of object inside of Kubernetes that we have not yet discussed. So the new type of object we're going to use is something called a secret. So it's a very similar type of object in the sense that we had previously created a pod, a deployment, a service, and so on. The purpose of a secret is to securely store one or more pieces of information inside of your cluster. So a good example of a use of a secret be for a database password, an API key, or maybe an SSH key, or any similar type of secret piece of information that you do not want to have easily exposed to the outside world, but you do want to make available to running containers inside of your application. And so our database password perfectly qualifies as something that we would want to store inside a secret. Now, the secret is only about information that you want to very much protect. So in our example of our environment variables here, storing the Redis host right here would have not been a very good use of a secret, because the Redis host is always going to be the name of our service. And the name of our service is very plainly legible and readable inside of our Redis cluster IP file right here. So not a good reason to try to store the Redis host, for example, inside of a secret. Probably the same thing for the port. Now, maybe the PG user would be something to store inside of a secret. Maybe the PG database would be as well. But for our example here, we're just going to worry about encoding our PG password and storing it inside of a secret. All right, so how do we create a secret? Well, a secret is an object, very much like a pod, a deployment, a service. And so we have said a billion times throughout this course that we always create an object through the use of a config file. However, you and I are not going to use a config file to create a secret. Instead, we are going to run an imperative command that's going to create the secret for us. So why are we using an imperative command here as opposed to a config file? Well, when you create the secret, you have to provide the data that you want to encode. And so if we had to write out a config file that said, hey, here's our secret, like in plain text, here's the PG password, then it would kind of defeat the purpose of having a secret anyways. So we're going to create our secret with a single command that's going to be imperative in nature. And that means that we're going to have to run this command locally on our computer to create the secret. It also means that when we eventually take our application to a production environment, we're going to have to make sure that we create the secret manually in the production environment as well. Everything else that we've done with the config file, such as our deployments and our services, do not need to be manually created in a production environment. All we have to do is apply the config files that represent each of them. So again, our secret being imperative in nature, we're going to have to make sure that we manually create this thing in any environment that we eventually take our application to. So to create the secret, we're going to run a rather long kubectl command. I'm going to zoom in on this thing and then we'll go over it step by step. So we're going to use kubectl create. Create is an imperative command that we can use to create a new object without necessarily using a config file. You will see a lot of documentation and a lot of blog posts out there talking about kubectl create. Remember, we have not been using this command throughout this course because we've been taking the more declarative approach of using those config files. We're then going to designate the type of object that we want to create. So of course, we want to make a secret. And then we will designate the type of secret. Now, our type of secret is generic, which indicates that we are saving some arbitrary number of key value pairs together. There are two other types of secrets that you might create. The first one is a Docker registry. So you would put in Docker registry. The other type of secret you can make is TLS. And TLS is related to, say, HTTPS setup. And we would use the TLS right here to store a set of TLS keys. Now, the vast majority of the time, you are going to use the generic. We would use the Docker registry one anytime that we want to set up some type of authentication with a custom Docker registry that we would be storing our images in. Now, you and I are storing all of our images in Docker Hub, so no custom authentication is required. So we do not need to make a secret of type Docker registry. And then as far as that TLS secret, we actually might be setting up some HTTPS stuff later, so we might end up using that other type of secret at some point in time, but we'll see. Okay, so after generic, we'll then put down a name for the secret. The secret name is very important. It's very similar to the name property, so we've added to all of our other objects. The name property is going to be how we refer back to the secret at some point in time in the future when we actually want to consume it and make use of this secret inside of a pod config. Then the last two arguments on here are going to be from literal. So when we use -- from literal, that means that we're going to write out the information to be stored inside the secret in this actual command, as opposed to trying to write the secret information into a file and then load up all that secret data from the file. So because we are using from literal, we're going to add on our information as a key value pair at the very end of the command. You and I want to encode some environment variable called PG password. So we'll probably end up doing something like PG password equals, and then our actual password, whatever it might be. You know, for us, we'll probably keep it something simple like password 123 or whatever it might be. Okay, so that's the entire command. So let's flip over to our terminal. We're going to write this thing out. And again, I want to remind you that we're going to have to run this command locally in our machine. And when we eventually move off to production, we're going to have to run the same command again to create a secret on that new environment as well. So let's get to it. I'm going to flip back over to my terminal. I'm going to run kubectl create secret. We're going to make a type of secret called generic. The secret name will be PG password. Notice how we're doing this in lowercase here. So this is not the actual environment variable. It's not the actual secret. It's just the name of the secret. So we're going to eventually have to reference this thing in the future and say, hey, go pull some information out of the secret called PG password. We'll then do -- from literal. I'll zoom in here just to make sure it's nice and legible. There we go. So -- from literal, and then we're going to put down the actual key value pair that we want to encode. So I'll do PG password equals, I don't know, 12345 ASDF, whatever you want it to be. It's totally up to you. All right, so that's the entire command. So I'm now going to run this, and we'll see that the secret was created. And now just to verify that, yep, it was successfully created, and to look at the secret, we'll put in kubectl get secrets, like so. And it's going to tell us, all right, we've got a secret called PG password, and there's one key value pair inside there. And the key value pair is the PG password that we put in right here. All right, so that's it. We've now created a secret that is going to store our Postgres database password. So now the last thing that we have to do is wire up this secret to our server deployment. So we need to make sure that our server container knows about the secret and receives it as an environment variable. And then the other thing that we have to do that might be a little bit less obvious is that we have now created a database password that is something different than the default Postgres password, which is by default something like, I don't know, PG password or whatever it is. I forget it off the top of my head. So we need to make sure that we also update our Postgres deployment as well. We're going to update our Postgres container definition and tell it about the password that it should be using as its default check. So we want to override the image's default password that it sets up when it creates a copy of database inside that container and say, hey, use this password instead. And so anytime that someone tries to connect to the database, it's going to try to authenticate that connection with the password that we provide to it. So 2 places to wire up this secret. Let's take a pause right now, and we'll take care of both these things in the next section. In this section, we're going to wire up our Postgres secret that we just created in the last section to our server deployment and our Postgres deployment as well. So we're going to first start inside of our server deployment.yaml file. I'm going to scroll down to my list of environment variables because we want to provide this password as an environment variable. So at the very end of this list, I'm going to add on a new name. The name is going to be PG password. Now, something to make clear here is that this is the name of the environment variable. So this is how our secret or our encoded password is going to show up inside the container. The name of PG password right here is not at all related to the secret. And in fact, it could be something totally different. It could be my password or whatever we want it to be. But in our case, our copy of the multi-server image is going to be looking for a PG password environment variable. And so that's why we are going to use specifically PG password as the name. Then, rather than specifying a value property, we're going to provide a value from property. So we're essentially saying, get the value for this environment variable from some configuration that we're going to put in here. And so we're going to put in a secret key ref, and then we'll provide a name. The name is going to be the name of the secret that we want this environment variable value to come from. So the name of our secret that we just put together was PG password, all lowercase right there. So as my name, I'll put in PG password. And then we also have to put in a key. Remember that a secret can store many key value pairs. We only put one key value pair in here, but we could have very easily added in several other key value pairs as well. And so we need to point out the key value pair that we want to shove into this environment variable. So the key that we want to reference is PG password. So for the key, I'll put in PG password, like so. So now that we put the name and the key right here, Kubernetes is going to automatically open up this secret with the name of PG password. It's going to find the key value pair inside of there equal to key. So that's this one right here. It's going to find the value associated with it, which is 12345 ASDF, and it's going to pass that into our container as the environment variable called PG password. Now, one thing that's a little bit unclear here, or I feel like might be a little bit confusing, is the fact that our name of the environment variable and the key inside the secret are identical. So again, we could have very easily changed, say, the key right here to be like my password without any issue whatsoever. We would have just needed to make sure that the key that we provided right here, rather than PG password, it would have had to have been my password as well. All right, so I'm going to change that back like so. Okay, so that's how we wire up a secret as an environment variable. So our server now knows about the password to use for the database. So now the last thing we have to do is to make sure that our Postgres database knows about the password that it should be using. So we're essentially going to override its default password. All right, so for this, we're going to find our Postgres deployment file. We're going to scroll on down to our container definition right here, and we're going to add on a env property to our container definition, like so. Now, please triple check, make sure that env is on the same indentation level as the name, image, ports, and volume mounts properties. If you want to be real safe, you could actually just add it up right here and not have to worry about matching the indentation at all. Just a quick reminder, all these key value pairs inside of a YAML file do not need to be ordered in any specific fashion. Okay, so for env right here, I'm going to pass in a name of PG password. So now we are setting up an environment variable of PG password that we're going to pass into the container. If the container or the image Postgres right here sees an environment variable of PG password, it's going to use that as the default password as opposed to the, or excuse me, as the password as opposed to the default password of whatever it usually is. And again, I forget what it is off the top of my head. Okay, so we're going to create the PG password environment variable, and then we're going to say you're going to get the value for this from a secret key reference. And again, it's going to have a name of PG password. And the key that we want to reference inside of that password or that secret is PG password right there. So we will provide a key of PG password, like so. All right, so that's pretty much it. So we have now set up a custom password for our database. We have told our copy of Postgres to make use of that password anytime someone tries to connect. And we've also told our server pod, or more specifically, the multi-server container that gets created, what that secret password is. So that's pretty much it. Now, the very last thing that we are going to need to do is to apply the changes that we just made to these configuration files. So I'm sure you recall how to do that. We'll flip on over to our terminal, and we'll do a kubectl apply -f K8s, like so. Now it looks like I've got a little bit of an error message here. You'll notice that it says cannot convert int64 into string. I know exactly where that's coming from. This was a expected error, don't worry about it. So we'll take a quick pause right here. When we come back to the next section, we're gonna fix this thing up very quickly. So quick pause and I'll see you in just a minute. In the last section, we tried to apply our updated configuration files, but we very quickly got an error message that said something like cannot convert int64 into string. So this is an error message that I personally just wanted you to see because I can almost guarantee you'll see this when you start putting together your own application. We're seeing this message right here because inside of our server deployment file and our worker as well, we provided some environment variables as integers. So right here, our Redis port has an integer value, or essentially a number, as 6379, and the PG port is 5432, also a number. Whenever we provide an environment variable, we have to provide it as a string. So for the value of 6379, all we have to do is wrap this with a quote like so, and the same thing on the PG port as well. That's all we have to do. Then inside of our worker deployment, we'll find the Redis port of 6379. Again, we cannot have an environment variable in here as a number. We have to provide it as a string, and so the simple workaround is to just wrap this thing with a set of quotes like so. All right, now that we've made those changes, I'm going to save both those files, and then we'll flip back over to our terminal and try to apply these config files again. So I'll do a kubectl apply-f K8s. Now I'm going to tell you if we get any errors this time, I was not planning on it, so if we see an error message, we're going to have to go back and figure out what's going on and try to fix it. All right, so I'm going to run that, and it looks like everything worked out just fine. You'll notice that the server deployment has been configured. It looks like our worker deployment has also been configured. Now, I'm looking for Postgres in here. Where's our Postgres deployment? It looks like the Postgres deployment is unchanged, which is not quite expected. However, you know what probably happened is it probably applied the config during our last apply in the last section. So I think it's totally fine to see that the Postgres deployment is unchanged there. Unfortunately, I've already cleared my console log, so I can't scroll up and verify that Postgres did get configured successfully. Nonetheless, we'll be able to test this out soon enough inside of our browser and be able to verify that everything worked correctly. So let's take a quick pause right here and we'll continue in the next section. There's just one last little piece of configuration that we have to do to set up our application. All right, my friends, we're almost done with doing our local setup of Kubernetes. We've set up our deployments, we've got the cluster IPs, our persistent volumes, secrets, environment variables, the whole shebang. The very last thing we have to do is somehow allow traffic to get into our application. Now you'll recall that we had previously allowed people to connect directly to the multi-client pod over here through the use of a node port. But a node port is only really good for use inside of a development environment, and we certainly want to eventually take this application into production. So rather than using a node port, we're going to start to wire up an ingress service to our application. Now, in this section in particular, we're going to get a couple of words in on exactly what an ingress service is. But before we do, I want to tell you about the third type of service that we had very quickly mentioned exists, but didn't really go into a lot of detail on. And that's a service called a load balancer. So we're going to very quickly give you a brief overview on a load balancer type service and talk about why we're not going to use it. And then we'll move on to talking about ingresses and all that whatnot. All right, so for services, remember these are objects that are meant to set up some type of networking inside of our cluster. We've made use of a cluster IP, which allows other pods to get access to a particular service or a particular set of pods. We've got the node port, which we just discussed again, and the load balancer. Now, this is a legacy way of getting some amount of traffic into your application. You're going to see a lot of documents or blog posts refer to load balancers, but whenever you do, check the date on the blog post. It might be a little bit dated. An ingress is the newer and supposedly better way of getting traffic into your cluster. But again, quick discussion on a load balancer and why we're not going to use it. All right, so a load balancer actually does two separate things inside of your cluster. First off, to create a load balancer type service, we would make a configuration file of type service and a subtype of load balancer. When you set that up, you're going to essentially allow access to one specific set of pods inside of your application. Remember, the goal of a service is to kind of manage access or provide networking to reach a set of pods. And so a load balancer only is going to give you access to one set of pods. In our case, our application has 2 set of pods that we want to expose to the outside world, which is 100% common. Your application might need to have a very similar type of setup. So a load balancer would not be able to give us access to both the multi-server set and the multi-client as well. Now, when you make a load balancer service, you are not only getting access to a specific set of pods. When you make a load balancer service, Kubernetes is going to actually do something in the background for you as well. It's going to reach out to your cloud provider, so be it AWS or Google Cloud or whoever else you might be using, and it's going to create a load balancer using their configuration or definition of what a load balancer is. So in the AWS world, you might get a classic load balancer or an application load balancer. There's one other third kind of load balancer that escapes me off the top of my head as well. Kubernetes is going to tell AWS, hey, I need like a application load balancer or a classic load balancer. So it's going to set up this external resource outside of your cluster, and then it's going to automatically configure that load balancer to send traffic into your cluster and access the load balancer service that has been set up to govern access to this very specific set of pods. So that's what a load balancer does. Again, kind of a more legacy thing. Supposedly, some people say it's deprecated, but it's really hard to look at the Kubernetes official documentation and see something that specifically says deprecated. So I'm not 100% sure if it is deprecated, but certainly older way, and again, not really appropriate for us because, again, we've got these 2 different things that we want to expose to the outside world. So with that in mind, we are going to be using an ingress service instead to get traffic into our cluster. So let's take a quick pause right here. In the next section, I want to give you a couple quick notes on ingress, some high-level things that you just need to be aware of. So quick pause, and I'll see you in just a minute. In the last section, we had a quick discussion about load balancers, and we discussed why they're not quite appropriate for our application. In this section, we're going to move forward and talk about ingresses. This is a type of service that is going to eventually get some amount of traffic into our application and allow our outside users to access all the different pods that are running containers that they need to get at to actually access our app. All right, so quick diagram here. So as you might guess, yep, traffic's going to come in. It's going to hit this thing called an ingress, and then it's going to be sent off or routed off to either our client set of pods or the server set of pods. Now, in the world of Kubernetes, there are several different implementations of an ingress. We are going to be using a very specific implementation called an Nginx ingress. Now, before we talk about exactly what this Nginx ingress is, how it works, all that kind of stuff, I want to have a very important discussion with you. Really critical that you pay attention to this, because if you don't, it's going to make things really, really confusing when you go and start to look up documentation. Okay, so here's the very important note, the very important thing you gotta understand. So you and I are going to be using a project called Ingress Nginx. That's the name of the project. This is a community-led project, and by community-led, I mean that it is a part of the official Kubernetes organization. So it's led by people from Kubernetes, full endorsement of the Kubernetes project, a lot of backing, a lot of strength behind this project. I put the link to the GitHub repository for it right here. So you can try to visit that repository, and you're going to see, okay, here's the page, documentation. You see some stuff called like Nginx Ingress Controller. Now, in addition to this ingress called Ingress Nginx, there is a completely separate project, totally separate, that does almost the exact same thing with almost an identical name. So a separate project out there is called Kubernetes Ingress, and this is also an Nginx-based ingress. It is a project led by the company Nginx. It does like the same exact thing, almost identical name, but it's 100% separate, totally separate. And so right here, this is the GitHub repository for it. I'm going to go there as well. And if you scroll down to the README, you're going to see that this repository also has a title of Nginx Ingress Controller. Well, here's the project that we're using, and it's also called, very helpfully, Nginx Ingress Controller. So yeah, like these things are nearly identical in looking, but they are very much separate projects, and they work differently. So whenever you are looking up documentation, you got to be like 100% certain that you're looking at documentation for the Ingress Nginx project. So in general, I recommend that you go to this GitHub repository, probably even bookmark it right now. And anytime that you need to look up documentation, come to this repo, make sure you're looking at Kubernetes Ingress Nginx, and then try to access documentation from this page. Because otherwise, you might accidentally fall into looking at documentation for the other project, the Kubernetes Ingress project. All right. So I know this is really confusing, but again, I wanted to make a really big deal about this and make sure that it's 100% clear that, yes, these are two separate projects. We are not using this one. We are using this one. So with that in mind, let's take a quick pause right here. We're going to come back to the next section with one or two other brief notes. In the last section, we spoke about how there are two Ingress projects out there that have very, very similar names and are very similar in nature, but again, they are completely separate things. In this section, I want to do a very quick follow-up on Ingress Nginx, which is what we are using. So very important note here. I want you to understand one other very important thing. The setup of this Ingress is going to be slightly different, or in some cases, very different, depending upon the environment that you are using it in. So if you are deploying this Ingress Nginx thing in your local environment, or Google Cloud, or AWS, or Azure, it's going to be very different in each of these different environments. In this course, you and I are going to set up Ingress Nginx on our local machine, and we're also going to be setting it up on Google Cloud. So that's kind of like a big reveal here. Yes, we're going to deploy our Kubernetes cluster to Google Cloud and not AWS, even though we used AWS previously in this course. So that might be a little bit of a surprise. You might be a little bit disappointed to hear that we're not using AWS, but there are some extraordinarily good reasons that we are using Google Cloud over AWS. And I'll tell you in great detail what those reasons are when we start moving over to production. So this is the other note that I want to throw out there, just to make sure you are 100% aware that this Ingress stuff, as you probably are able to tell, it's a little bit finicky right now in the world of Kubernetes. You got these identical projects. The setup is very different depending upon the environment. So hopefully we're going to get through this stuff together without too much pain, but we'll see what happens. So with the second note in mind, let's continue the next section, and we're going to get started on our Nginx Ingress setup. In the last section, we had a quick discussion around the differences between Ingress Nginx and Kubernetes Ingress. We're now going to continue and start to talk about how this Ingress stuff works behind the scenes to somehow get some amount of traffic into your application. So let's get to it. Now, I want to first begin by giving you a quick reminder of how we've been doing things throughout this entire course. Throughout the entire course, we've been making config files that contain the desired state of our application. So, for example, we've been writing config files that say that we want to be running 3 pods or 3 replicas, each of which run the multi-client image. We then feed that into kubectl, and that creates a deployment object. And it's up to that deployment object to look at our current state, and then look at our desired state and figure out some migration path or some way to get from the current state to the desired state. And so after the deployment jumps into effect and starts working, it's going to eventually create 3 new pods, each of which are running the multi-client image. Now, the reason I'm giving you this reminder about how all this stuff works is that this deployment object right here is what we refer to as a type of controller. In Kubernetes, a controller is any type of object that constantly works to make some desired state a reality inside of our cluster. So in the world of ingresses, and as we start to talk about ingress, the exact same strategy right here all applies 100%. You and I are going to write some config file that describes a set of routing rules to take incoming traffic and send it off to the appropriate services inside of our cluster. We're then going to feed that config file into kubectl, and kubectl is going to create something called an ingress controller. So it is a controller. It is something that's going to look at our current state. It's going to look at the desired state and then create some infrastructure that's going to make our desired state a reality. So in the case of our particular ingress controller, which is, as you might guess, using Nginx behind the scenes, when we feed in this config file, the controller is going to create a pod running Nginx that's going to have a very particular set of rules to make sure that traffic comes in and gets sent off to the appropriate different services inside of our cluster. So you can kind of think that this entire setup around ingress looks a little something like this. We have our ingress config over here, which is our config file that describes all the routing rules that we want to have inside of our application. That's going to be fed into kubectl, where an ingress controller is going to be constantly working behind the scenes to make sure that all of the routing rules that we define inside the ingress config are actually implemented and met. And so it's going to be up to the ingress controller to create something, who knows what it is, but something inside of our cluster that will take the incoming traffic, read some parameters in that traffic, and then send it off to the appropriate service. So the big takeaway right here, the only thing I want you to understand right now is that you and I are going to create something called an ingress config, which is going to be a set of routing rules. We're going to feed it into kubectl, which is going to create this ingress controller. And the ingress controller's job is to look at the ingress config, or that set of routing rules, and make that a reality. The ingress controller has to create some infrastructure inside of our cluster to make sure that we're actually obeying those routing rules. And so the ingress controller is going to make, again, something that accepts incoming traffic. Okay, so that's the kind of high-level description of what's going on here. Now, in the case of the project that we are using, Ingress Nginx, things are going to work very similar to this, but just a tiny bit differently. And so infinitesimally differently that I almost don't even want to tell you that it's working differently. But I am anyways, just so you understand how things are working behind the scenes. So with the very particular project that we are using of Ingress Nginx, the ingress controller and the thing that actually accepts traffic and routes it off to the appropriate location is actually the same thing. So with the very particular ingress project that we are using, the ingress controller and the thing that routes traffic is the same thing. So we can kind of imagine, again, that you and I are going to make a ingress config, or a set of routing rules. We're going to feed it into kubectl, and then the project that we are using, Ingress Nginx, is going to create a single deployment whose job is to both read in the ingress config and simultaneously create a pod that meets all of those different routing rules. Now, again, this is a very tiny distinction, and I only mention this to you because we are going to look at some of the behind-the-scenes setup of Ingress Nginx inside of our project, and you're going to notice that there are not like the 3 separate things that I show you right here. In our project, there's only the 2 separate things as shown in this diagram right here. Okay, so with that in mind, let's take a quick pause. We're going to come back to the next section, and there's just a little bit more around some behind-the-scenes action for this ingress stuff that I want to show you before we start going through the setup. So, quick break, and I'll talk to you in just a minute. In the last section, we spoke about the 3 separate pieces of setting up ingress inside of Kubernetes. So we've got the ingress config, we've got the thing that actually implements that configuration, and then we've got the thing that actually takes incoming traffic and sends it off to the appropriate service. So I now want to take this type of approach right here and apply it to the actual application that we are looking at. Now, there is going to be one little twist here. Remember that I had told you just a little bit ago that the setup of all this ingress stuff changes a little bit depending upon your environment. So we're going to look at a diagram here that describes how all this stuff is set up specifically on Google Cloud. So the actual implementation when we set this up locally is going to be just a little bit different, but the Google Cloud implementation is probably the easiest to understand and kind of wrap your head around. So here's what's going to happen. Again, you and I are going to make an ingress config file, and that's going to describe all the routing rules that should exist inside of our application. This config is going to be fed into a deployment that is running both our controller, the ingress controller, and an Nginx pod. And that Nginx pod is what's going to actually take incoming traffic and route it off to the appropriate location. Now, specifically on Google Cloud, there's some other pieces in here that get created at the same time as well. So when we make an ingress on Google Cloud, we are going to get a Google Cloud load balancer created for us. This is a cloud-native load balancer, identical to the one that you would use with any other type of application that you might happen to create on Google Cloud. In fact, you can open up a new tab right now and search Google Cloud Load Balancer, and you'll see some marketing page here for Google Cloud Load Balancing. So this is the actual object behind the scenes that's going to be created by Google Cloud to somehow get traffic into our cluster. Once that load balancer is in effect, inside the cluster itself, the deployment that gets created is going to get a load balancer service attached to it. Yes, the same load balancer service that we had discussed a little bit ago. So even though we had spoken about this thing and we had said, oh yeah, the load balancer service is kind of a little bit legacy and we don't really use it anymore and we prefer to use Ingress, well, behind the scenes on Google Cloud, the load balancer service is still being used. And you wouldn't quite know it unless you actually looked at some of the source code or config files that set all this stuff up. So incoming traffic will come to the Google Cloud load balancer. That load balancer is going to send that traffic to a load balancer service inside the cluster, which is going to eventually get that traffic into the Nginx pod that gets created by our Ingress controller. It's then up to that Nginx pod to eventually send that traffic off to the appropriate service inside of our application, either the multi-client or the multi-server. Now there's one last little piece of the puzzle here that I just want you to be aware of. By default, when you set up all this Nginx Ingress stuff, there's going to be another deployment set up inside of your cluster, something called a default backend. The default backend is used for a series of health checks to essentially make sure that your cluster is working the way that it should be working. Now, we're going to be making use of the default backend inside this course, but ideally, like in an ideal world, you would actually replace the default backend pod right here with your Express API server. And so anytime that the Nginx pod needs to check the health status of our application, it would be ideal to tell it to reach out to the multi-server as opposed to the default backend. And I'll show you very quickly how you could do that later on. But for right now, I just want you to be aware that there is going to be this additional deployment inside of our application. Okay, so that's it. That's what's happening behind the scenes. Now, one last quick thing here, something that you might be a little bit curious about. So at this point, we've said, oh yeah, we're actually using this load balancer service, and the load balancer service is getting traffic eventually into an Nginx pod. So why, oh why, would we not just do this stuff manually to a degree? Why are we going to go through all this extra setup of this Ingress stuff and the Ingress config and a whole bunch of additional setup on top of that when we could take a much more straightforward and simplistic approach? Something like this right here. Why do we not just set up our own load balancer service manually that points to our own custom copy of Nginx? We've already made use of Nginx quite a bit throughout this course, so why do you and I not just make our own kind of custom Nginx server that sends traffic off to the appropriate set of pods? Well, the reason that we are still going to make use of Ingress Nginx as opposed to setting this stuff up manually is that when you make use of the Nginx Ingress project, it actually has a bunch of code added into it that is very much aware of the fact that it is operating inside of a Kubernetes cluster. So as one little example, there's many examples of this, but I'm going to give you one very quick example. When you make use of the Nginx Ingress project, rather than taking incoming traffic and sending it off to the cluster IP and allowing the cluster IP to load balance that request off to some random pod inside of here, the Nginx Ingress project is not actually going to send traffic over to the cluster IP service and allow that to do some amount of load balancing. Instead, the cluster IP service does still exist, and it still is working to essentially keep track of all these different pods, but anytime we get an incoming request to the Nginx pod right here, the Nginx pod is going to actually route the request directly to one of these different pods, completely bypassing that cluster IP service. The reason that this is done is to allow for features like, say, sticky sessions, which is a reference to the fact that we sometimes want to make sure that if one user sends 2 requests to our application, we want to make sure that both those requests go to the exact same server. And there's some cases where that feature is extremely handy and actually 100% necessary to have. So that's just one example of why we are making use of this Ingress Nginx project as opposed to kind of doing our own build-it-yourself solution. So you certainly can do a build-it-yourself solution. It's just going to lose out on a couple of these extra features that you get for free when you make use of the Ingress Nginx project. Okay, so enough on all this. I think we've had enough discussion around the theory, and all that's really left is going through the setup process. So let's take a quick pause right here. In the next section, we're going to start setting up Ingress Nginx inside of our project. In this section, we're going to start setting up Ingress Nginx on our local project. We're actually going to follow the setup directions that are tied directly to the GitHub repository. So to get started, I'm going to first navigate to this address right here. So github.com Kubernetes/Ingress Nginx. And then once here, I'm going to find the link to the documentation at the very top. So this link right here. Then once on the home page, I'll find the deployment tab at the very top, and we're going to walk through this installation guide together. Now the installation guide is a little bit confusing, which is why we're going to walk through it together. So the first thing that we want to find is generic deployment. We have to go through this mandatory command right here for any of the other deployment targets. So even if we're trying to deploy to Azure or GCE or AWS, whatever it is, we have to execute this mandatory command right here. So we can take that command, copy paste it, and then run it inside of our terminal. But before we do, I want to very quickly show you what is going on behind the scenes with the command. So I encourage you to copy the link that's listed right here. You'll notice that at the very end, it's actually a YAML file. So it's a config file very similar to all the config files that you and I have been creating throughout this course. Then inside of my browser, I'm going to visit the link to that config file like so. And so you're going to see something very quickly pop up. This is all the config that is going to be executed when we try to set up this Ingress Nginx project locally. Now, there's a couple of different objects inside of here that are going to be created that I just want to very quickly point out to you. You'll notice that the first thing that is created right here is something called a namespace. A namespace is used to kind of isolate the different resources that we are creating inside of our Kubernetes cluster. It's something we'll discuss just a little bit later on. Immediately after that, we'll see a deployment with the name of default HTTP backend. So again, this is a little deployment right here that is going to be created for us that's going to essentially serve as a health check and tell the Nginx pod that, yeah, our cluster is working the way that is expected to work. We can certainly omit this step right here and skip the default HTTP backend if we want to. The only thing that we have to do is to make sure that we instead point it at some other image that's going to, first off, serve a 404 page at the root route, and second off, serve a 200 on the /healthz route. So again, we could certainly implement these two steps right here inside of our multi-server pod if we had wanted to. That means that we would not have to create this default backend. But again, we're going to make use of the default backend just to save ourselves a tiny bit of work. Now, as you scroll down a little bit further, you're going to see that we get a service created for the default backend. After that, you're going to see a couple of different things called config maps. Config maps are essentially objects that hold some amount of configuration that can be used throughout our cluster. We're not going to be too concerned with that stuff right now, so I'm going to keep on going. Past the service account, service account, past the cluster role. We're going to go down towards the very bottom and eventually find the deployment with the name of Nginx Ingress Controller. So again, in just this project that we're making use of, just this Ingress Nginx project, the Ingress controller and the thing that is accepting incoming traffic is actually one singular object. So just with this one particular project, those two things kind of get merged together or sandwiched into this one single thing. And so if you look at the config for this object right here, you're going to see inside the containers definition that it's essentially starting up a copy of Nginx, but simultaneously, it's also going to read in some amount of config that tells this copy or this controller exactly how the Nginx copy should be configured. So that's all going on inside this config right here. You'll also see that there's some configuration that customizes that liveliness probe on the healthz route and also sets up the 404 somewhere inside of here on the root route as well, although I'm not immediately seeing it. Okay, so enough of that. Let's go back over to the installation guide. Again, I'm going to copy the entire mandatory command, and then I'll go into my terminal, and I'm going to paste that and run it like so. Now we're going to very quickly see a huge variety of different objects be created. So we'll just kind of leave that for right now. Before we continue, we have to go through one other setup step, specifically for Minikube. So back up here, I'm going to click on Minikube. And then it tells us that for standard usage, which is what we are doing, all we have to do is run this command right here, which says Minikube add-ons enable ingress. So I'm going to copy that command, go back over to my terminal, and I'm going to make sure I copy it this time. There we go. And then we should see that ingress was successfully enabled. Now the very last thing that I want to show you, you'll recall that I just told you that on Google Cloud, a load balancer service is actually going to be created. And that load balancer service is going to simultaneously create the external load balancer for us as well. So as a little sneak peek, if you want to, you could scroll on down to the configuration for GCE right here. And then again, you can copy the link to the config file for GCE. And then if you open that up in a new tab again, this is what is going to be created specifically on Google Cloud. And so as you'll notice, it is in fact a service that has type load balancer. And so specifically on Google Cloud, a load balancer is created to route traffic into your application through the use of a load balancer service. I thought that was just a little bit interesting because, even though we're saying, oh yeah, load balancers are a little bit dated as a service in the world of Kubernetes, even this newer feature of Ingress is still using a load balancer behind the scenes. So again, I just thought it was a little bit interesting. All right, so that's all we had to do to set up the Ingress locally. So let's take a quick pause right here. When we come back to the next section, we're going to start to configure our Ingress resource. So quick pause, and I'll see you in just a minute. In the last section, we set up Ingress Nginx on our local machine. Now the last thing we have to do is create a new config file that's going to specify the different sets of routing rules that we want to use inside of our application. We're going to use the exact same routing rules that we had used back on some of our previous projects, specifically the Elastic Beanstalk one, where we set up our own custom Nginx server. So if you recall, back on that project, we had said that anytime we had some amount of incoming traffic, we looked at the path of the request. And we had said that if the request started with /API, we were going to automatically send that request off to the server. Otherwise, we would send the request off to the client, assuming that it needed to access some of the client-side resources. So we're going to set up a Ingress config file right now that's going to implement this routing rule set. So inside of my code editor, I'm going to find my K8s directory, and inside there, I'm going to make a new file called ingress service.yaml. Then inside of here, we're going to write out our config file that, as usual, is going to look very similar to a lot of the other config files we've already put together. So I'm going to specify an API version. This one is going to have a longer version on it that we've not used before. We'll say extensions v1 beta 1. The kind of object we are going to create is an ingress. We'll then set up our metadata. So we'll give it a name of ingress service. And then unlike previous metadata fields that we set up, this one is actually going to have a couple of other metadata properties as well. So I'm going to add on a new thing to this called annotations. Annotations are essentially additional configuration options that are going to specify a little bit kind of higher level configuration around the ingress object that it gets created. So the first thing we're going to do here, we're going to add on kubernetes.io/ingress.class of nginx, like so. So this configuration rule right here is essentially telling Kubernetes that we want to create a ingress controller based on the nginx project. Then immediately after that, we're going to add in another configuration rule that's going to specifically configure how our copy of nginx behaves. So I'm going to say nginx.ingress.io/rewrite target / like so. So this additional annotation right here, again, this is going to configure how the actual copy of nginx behaves. This rule in particular says that if we end up matching a route like /API right here, after deciding to send it to the server, that configuration is going to first do a little bit of a rewrite on the request. And essentially, it's going to remove the /API part. Now, again, we did a step like this very similar back on the Elastic Beanstalk project that we put together. We had said that we probably did not want to put some configuration inside of our server that very tightly coupled it to the routing that got the request to the server in the first place. So we had decided to remove the /API out of the incoming request, just so that we did not have to write /API on every different route on the server itself. Okay, so that's exactly what this line of configuration is doing right here. So now after that, we'll unindent and we'll add in a spec. So for the spec, we're going to add a series of different rules. In our case, we're going to have just one rule. So I'm going to put in a single dash like so. And then I'll say HTTP paths. This is going to be an array as well. So I'll do a dash and I'll say path / backend is going to be service name of our cluster client cluster IP service, which has the name of client cluster IP service. and a service port of 3000. I'll then add in another path here of /API/. I'll give it a backend as well. This is going to have a backend that points at the, where is it? Server cluster IP service right here, which has a name of server cluster IP service. And a service port of 5000. Okay, so let's talk about exactly what's happening here. Now we discussed the annotations, and then we very quickly dove into all the different rules. So our rules are saying that there are two possible paths that we can match traffic to. If someone ever comes to the path of just / by itself, or any route that looks like / followed by anything besides /API, then we want to send that request to whatever set of pods are governed by the service of client cluster IP service. And again, we just referred to the name of that other service as we had designated it inside of our client cluster IP service file. Then if a request came in with a leading route name of /API, we wanted to instead send it to the set of pods that are governed or managed by the server cluster IP service. So essentially, we're setting up the exact same relationship that you just saw in this diagram right here. The Nginx configuration that we're putting together is going to send all this incoming traffic to either the multi-client set of pods governed by this cluster IP service, or the multi-server set of pods governed by this cluster IP service. We don't have to actually specify the IP address of these servers inside of our cluster. We just refer to the name of the service. And then all this Nginx ingress stuff is going to figure it out from there. You'll notice that we also had to specify the port for both these services as well. Okay, so that's pretty much it for this config file. Now, the description that I've given you of this config file is pretty light at this point in time. Like, I haven't really told you about why we have multiple rules in here or this HTTP flag or stuff like that. We are going to actually come back to this file over time and make a couple of additions to it over time. So don't worry, we are going to come back to this file and have some further discussion about what's going on inside of here. Now, the last thing I want to do is take this file and apply it with kubectl, which should set up some networking inside of our application. So I'm going to flip on over to my terminal, and I'm going to do a kubectl apply -f, and then as usual, we'll just apply everything inside of the K8s directory. So I'm going to run that, and somewhere inside of here, we should see ingress service created right there. So let's take a quick pause right here. When we come back to the next section, we're going to do a little bit of work to make sure that the ingress is up and running as we would expect. So quick pause, and I'll see you in just a minute. In the last section, we finished up our ingress Nginx configuration, and then we applied it using kubectl. We can now test out our application inside the browser because we should have just created everything that's going to essentially get traffic into our application and then route it off to the appropriate service. To test this stuff out, we're going to flip over to our terminal, and we're going to get the IP of our Minikube virtual machine. So I'm going to run Minikube IP, and then I'll copy this IP address, and I'll visit it inside of my browser. Now this time around, we do not have to specify a port on this IP because the service that we have created is automatically listening on both ports 80 and 443 for us. And by default, your browser is going to default to either port 80 or 443, depending upon whether or not you are using a HTTPS connection. All right, so when I go there, you're going to very quickly see a big security message appear on the screen. Now, I've already bypassed that warning message, but when you first navigate to this IP address, it's going to tell you, hey, danger, there's a security issue here. At the bottom left-hand side of that config or that error message, you'll see a little like get more info button. Go ahead and click on that button, and then you can click on proceed anyway. So at present, our Nginx configuration is attempting to force anyone who comes to our page to use a HTTPS connection as opposed to HTTP. By default, the Nginx ingress is going to use a kind of dummy certificate. So if you click on not secure up here and then click on certificate, you'll see that it has a name of Kubernetes ingress controller fake certificate. And as you might guess, a fake certificate is not going to be accepted by Chrome at large. So the error message that you're seeing is going to be something that we're only going to have locally in development. When we eventually push this off to production, we're going to fix this error message, but for right now in development, we're just going to let this sit as is. You only have to click past that error message screen one time. After you click there at least one time, you should be able to refresh the page, and you're not going to see the error again. You're just going to see the HTTPS error, which is something that we can essentially palette right now for development purposes. Okay, so that's pretty much it. We should now be able to test out our application by entering in some index. I'll submit that, I'll refresh the page, and then I should see all my numbers appear. So if you see all this stuff appear correctly, that means that your entire Kubernetes cluster is completely set up and ready to go for development purposes. So I think that we've got a great project here so far. Let's take a pause right now. When we come back to the next section, we're going to start thinking how we can migrate this project to a production environment. So quick break, and I'll see you in just a minute. Our application is more or less now complete in a development environment, and we get to now start thinking about moving this over to production. We're going to start discussing that in just a moment, but before we do, I want to show you one last thing that might help you out with Kubernetes in a development environment. I did not show you this feature earlier on very much on purpose because it can kind of throw you a little bit off base if you know about this feature too soon. So this is why I kind of waited to the very end of the development side of things to show you this. All right, so I'm going to flip over to my terminal really quick, and I'm going to run the command minikube dashboard, like so. So I'm going to run that command, and then you'll very quickly see a message that says opening Kubernetes dashboard in default browser, and you'll get redirected over to your browser as well. So the page that's popped up here, you might notice is hosted on our minikube IP address at port 30,000. This is a dashboard that will show you information about everything that's going on inside of your Kubernetes cluster. And so it's actually a little bit of fun to scroll through here and take a look at all the different deployments, pods, all this different stuff that has been created and is in service to somehow create and manage your cluster with all your different containers in your entire application. So you can click through here a little bit and get a better idea of what's going on. You'll notice a couple of different pieces of terminology that we haven't quite spoken about just yet, such as, say, daemon sets and replica sets. And just so you know, as a quick side note here, we very specifically did not talk about replica sets or replication controllers because they're kind of deprecated, and the recommendation is to use deployments instead of replica sets or replication controllers. So just so you know, some of these pieces of terminology you'll see in here, we very purposefully did not cover because they are things that you're not quite supposed to use or seen as the best way of doing things with Kubernetes anymore. Anyways, I thought you might just find it a little bit interesting to click around here a little bit and take a look at some of the different services and pieces of data that exist in here. Now, I had said that I kind of purposefully did not show you this stuff earlier. The reason for that was that you can actually edit or even create different objects using this dashboard. But remember, anytime we create an object in Kubernetes or anytime we want to change something, we do not do imperative edits if we can ever avoid it. And so if you click create up here, yeah, you can enter in a YAML file, but you don't really have a good record of what that YAML is. You can also, say, go to maybe pods over here and click on a pod, and you can click on edit and make discrete changes to the YAML file or the config file directly right here. But again, if you make changes on the dashboard, they do not get somehow persisted back over to the folders and files that we've created inside of our project directory. So whenever possible, we always change the config files and not the actual configuration directly on this dashboard. So again, that's why I kind of wanted to hold off showing you this stuff right at the beginning, because I didn't want you to kind of get into a habit of manually changing or creating different objects on here. We always want to prefer using config files inside of our project directory to manage these different objects. Okay, so again, you can take a look at this dashboard and just get a better idea of some of the different pieces of information that are displayed on here. Otherwise, let's take a pause right here and we'll continue in the next section and continue thinking about how we're going to move our application over to a production environment. So quick pause and I'll see you in just a minute.